Hi, in this video we are going to talk about overview of sorting algorithms. Sorting is one of the most fundamental problems in computer science. It's used as a prerequisite in many algorithms. So there exist many sorting algorithms, and in this video we are going to cover an overview of most of these algorithms. Let's first talk about simple sorting problem. We are given a binary array or an array of two types of elements. We need to sort it. We have talked about this problem in a separate video, and this problem is solved using partition algorithm of quicksort. So it's efficiently solvable using partition algorithm, quicksort. And partition algorithms of quicksort are Lomuto, Hoare, and naive also is there. The advantage of naive is it's stable. Lomuto is slower than Hoare. Both of them are faster than naive because naive requires extra space, but naive is stable. Let us now talk about next problem. We have an array with three possible values. For example, sorting an array of zeros, ones and twos, or sorting an array around a range, or you have an array where elements occur multiple times and you want to put all occurrences of an element together and you want to put all the smaller values on left of it or right of it. So all these problems are sorting an array with three types of values. We have a separate video with detailed explanation of this problem. You may refer that video for more details. This problem can again be solved using quicksort partition algorithms. We can either use naive partition or Lomuto partition or Hoare's partition. Naive is stable, Hoare's is fastest. Let us now talk about the next problem where you have an array of size n and range of these values is small. For example, if you have an array of size 1000 and values in this array are range from 100 to 200 only. So you want to sort such an array. For such problems, we have an algorithm called counting sort. Counting sort sorts an array of size n in big O of n time under the assumption that all the values are in a small range. So if your range of values is having k values total, for example, if the range is from 100 to 200, you have total 100 possible values, so k is 100. So this counting sorts takes big O of k time, k extra space, and big O of n plus k time. This is the time complexity and extra space requirement of counting sort. Counting sort is a good algorithm when your range is really small. Consider small ranged items, but range is slightly bigger. For example, range is n square or n cube. Say you have 10,000 elements and your range is from 0 to 1 lakh, right? So counting sort in this case is going to take 1 lakh extra space and 10,000 plus 1 lakh extra time to run this algorithm, right? For such scenarios, we have better sorting algorithm. There is another sorting algorithm called Radix Sort. Radix Sort sorts an array where range is from 0 to n square or 0 to n cube, or the total range is size is n square or n cube. This also sorts your array in big O of n time and big O of n extra space. So this is a better algorithm when you have slightly higher range. The next problem is you have an array where data is uniformly distributed across a range. So you might be having a small range or a big range, but your data is uniformly distributed. For example, if your range is floating point numbers 0.0 to 1.0, say range is this, and you have thousands of elements, which are uniformly distributed in this range, right? What it means is you have 100 elements from 0.0 to 0.1 and 100 elements from 0.1 to 0.2. So if that is the case, you can use bucket sort. Bucket sort is the algorithm which is used when your data is uniformly distributed. You can use bucket sort to sort such an array in linear time on average. So for uniformly distributed data, we can use bucket sort, which is fastest of all the sorting algorithms for this particular case. Let us now talk about next point. When memory writes are costly. When memory writes are costly, you have two choices. There are two algorithms which can be used to optimize the memory writes. Memory writes can be costly in cases where every write reduces age of your memory. For example, EEPROM. For such cases, we have two algorithms, selection sort and cycle sort. Selection sort is a popular simple algorithm, very simple algorithm that does minimum number of swaps compared to other standard algorithms like insertion sort, quick sort, merge sort, and worst case time complexity of selection sort is n square. So it does minimum swaps compared to other standard algorithms but takes more time than many other algorithms. There is another algorithm, cycle sort, which is also worst case n square, but it is optimal in terms of memory writes. It is even better than selection sort, right? So selection sort is good compared to other standard algorithms, but cycle sort is optimal. We have discussed cycle sort in a separate video. It's the optimal algorithm in terms of memory writes. Let us now talk about next problem. Suppose in a special situation, you are allowed to swap only adjacent elements. In that particular case, in that particular situation, you can use bubble sort. Bubble sort is a sorting algorithm that swaps only adjacent items. There is an optimized version of bubble sort that works better in general compared to bubble sort, and that sorting algorithm is called cocktail sort. Cocktail sort is simply an optimized version of bubble sort. Bubble sort travels from left to right, cocktail sort travels from both the sides. The next special case is when your array is small, when you have a small number of elements to sort. For such cases, we have two algorithms, two general purpose algorithms, selection sort and insertion sort. And among these two, insertion sort works best. Insertion sort is considered the best algorithm when you want to sort small number of elements, say only 10 or 20 elements, right? And most of the standard algorithms, standard library implementations, general purpose library implementations, they switch to insertion sort when the number of elements are really small. So we have insertion sort for this case when the number of elements are really small. Let us now talk about the last point. When available extra memory is small. You have an array to sort and you want to sort it within an embedded system, or maybe you are programming in kernel for a small device. Many standard algorithms like quick sort, merge sort, they need extra space. Quick sort needs extra space for recursion calls, merge sort needs extra space for recursion calls and for merging, right? Although there are versions of merge sort which can be optimized and which can be done in place, but if you talk about typical implementation, merge sort needs extra space. And even when there are optimized versions, your optimized merge versions, you need extra space for recursive calls in both quick sort and merge sort. Although that extra space is only log n, that can be optimized to log n. In quick sort and merge sort, it's anyways log n. But they need extra space, and they need extra space especially for function call stack or maybe your user created stack. So in situations where you do not want extra space at all, when you have very small amount of memory available, there is an algorithm for this purpose called shell sort. Shell sort is a sorting algorithm which does not use extra memory. So you can say now there are other algorithms as well, insertion sort, selection sort, they also do not use extra memory. So shell sort is better in terms of time compared to them. It takes n log square n time, right? Or you can say big O of n into log n square. So this much is the time taken by shell sort. This is the optimal implementation. The simple implementation is n square in worst case, but it can be optimized to work in this time. So this is the best algorithm with big O of one extra space and this much time when you have very small memory to work upon. We have talked about special cases. Let's now talk about general purpose sorting algorithms. The algorithms which are used in library functions, because library functions can be used to sort any type of array. When you talk about sorting algorithms and you say general purpose, where you do not know the range of input or you do not know anything about the data, it can be mathematically proven that we cannot sort random data in time complexity better than n log n time. So you need at least n log n comparisons to sort a random array where you do not know anything about it, right? And you have n log n algorithms like merge sort, heap sort, quick sort. These two in particular are n log n even in worst case. Quick sort is n square in worst case, but works better than merge sort and heap sort on average. So these sorting algorithms are general purpose algorithms because they three are fastest of other sorting algorithms that we discussed for special purpose, and they take n log n time. In general, if you compare these three algorithms, quick sort is the fastest of them all, right? And merge sort has this special thing that it works well for some special cases, like it's a stable sort algorithm. One thing, heap sort is not stable, quick sort is not stable by default. So merge sort is stable and it works really great for linked lists. Heap sort in particular cannot even be simply modified to work for linked lists because it needs random access. Although quick sort also needs random access, but it can work on linked lists with the same time complexity. But heap sort is not possible to work with the same time complexity in excess space. Merge sort, when you talk about linked list, the extra space requirements of merge function simply reduce to big O of 1 by using simple algorithm of merge sort. So it well suits for linked list, it's a stable sort, and it also works good when you have data on tape drive which can be accessed only sequential way, or a general purpose external sorting algorithm. It is also well suited for external sorting. One more good thing about these two sorting algorithms is they both are divide and conquer. This one and this one. They both are divide and conquer. So they parallelize really well. You can reduce the time complexity further by parallelizing these algorithms. There have been implementations like merge sort which are log square n when you have parallel machines to do the sorting, and log n parallel implementations of quick sort. Since they are divide and conquer, they are really well suited for parallel sorting as well. Let us quickly talk about hybrid sorting also. Most of the library functions, they use a hybrid sorting algorithm. A sorting algorithm which is a mix of 2 or 3 basic sorting algorithms. For example, Tim sort in Python. It's a mix of insertion sort and merge sort. It uses merge sort for general input, and if your input is small or it becomes small in the recursive calls, it switches to insertion sort. Intro sort, it's a mix of or hybrid of quick sort, heap sort and insertion sort, 3 sorting algorithms. In general, it uses quick sort. And when your quick sort is doing many unfair partitionings and the number of recursion calls are going beyond log n, it switches to heap sort. And when the array size becomes small, it switches to insertion sort. So it's a mix of 3 sorting algorithms, and insertion sort is used in C++ library. Many languages also have another function for stable sorting, because quick sort is not stable in general if they are using quick sort. So there is a general purpose function also called stable sort. For example, C++ has a function stable_sort. This function is typically implemented using merge sort because merge sort is a stable sorting algorithm. Hi, in this video we are going to talk about sort in C++ STL. Sort is a general purpose library function for sorting any types of input. It is mainly used for sorting data stored in containers which allow random access. And example containers which allow random access are array, normal arrays, vectors, and DQ. These are some containers which allow random access. Random access means you can access ith item in constant time. So sort can be used to sort elements for all these containers. Here is an example of sort function. We have an array with these values 10, 20, 5, 7, and we call the sort function. So sort function in C++, it receives two addresses or two iterators. The first iterator or address is an address of the first element, right? So array name in C and C++, it gives you the address of first element. So your first address is address of 10. And the second address is the address after the last element, right? So this address is after the element 7. So if you talk about vector and DQ, it's going to be v.end, right? v.end because it gives you an iterator pointing to an element beyond the last element. So that is why for arrays, we do not pass array plus n minus 1 because that will give you address of last element. But we pass array plus n. That gives you the address of an element beyond the last element. This sort function is defined in algorithm library. We have two ways to call the sort function. One is just passing two iterators, and this way sorts your input array in increasing order by default. And there is another way where you can specify an order. So I've called two ways here sort by passing two parameters and by passing three parameters. So the third parameter specifies the order in which you want these items to be sorted. It's mainly a function. So your third parameter is mainly a comparison function that decides how elements are to be compared. Greater function in C++ is a general purpose comparison function which reverses the order. So the general order in increasing order, greater function gives you decreasing order. So we now know sorting. We know how do we call it using two ways. Let's guess the output of this program. So the first sort will change this array to 5, 7, 10, 20. Right? And then you print content of this array. So you will get output as, so output of this program is going to be 5, 7, 10 and 20. Now you call this sort again with greater function as a parameter. So what greater function will do? It will cause this sort to compare elements in such a way that greatest element comes first. So output of this part after calling this function is going to be 20, 10, 7, 5. So this part sorts your array in decreasing order, right? That's what you get here. And this is done because of the sort call. And this sort call changes your input array to increasing order. And that's why you get this output. Let us now talk about an example to sort a vector. We are given a vector and we want to sort it. So this vector initially contains 4 elements, 5, 7, 20, 10. We call the sort function. In sort function, we can call two ways. First way is passing two iterators, where the first iterator points to the first element and second iterator points to an element beyond the last element, right? So we pass v.begin and v.end here. In case of arrays, we pass the address of first element and address of an element after the last. So v.begin and v.end, and by default we get the elements in increasing order sorted. So this line prints the output as 5, 7, 10, 20. Here we have called the sort function again, but we have passed another parameter, third parameter, which specifies the order of sorting. And greater function is typically used to reverse the default order. Default order is increasing order and greater is going to change it to decreasing order. So the output after the sort called is 20, 10, 7 and 5. So when you pass the greater function as an argument, it reverses the order and you get the array in decreasing order. So this for loop prints this part and this for loop prints this part as an output. We have talked about simple sorting where we were sorting in increasing order and decreasing order. Let us now talk about an example program where we want to specify our own order. I've considered a structure which represents a point in 2D space where x and y coordinate values, and I have written my own comparison function here which is used to sort these points in increasing order of their x coordinates. Right, so this is my own comparison function and this is structure. We are going to sort an array of this structure. So we create an array of this structure and now we call the sort function using same parameters, array and array plus n, address of first element, address of an element beyond the last element, and we pass our own comparison function. The third parameter. After sorting, all the elements of this array will be sorted according to increasing order of x value. So when you print the output, you are going to get the output as, so you have three values. So the first smallest x value is 28. So you will get 28. Then the second smallest value 310. Then the last value 54. So your points are sorted in increasing order of x values. Now say you want to modify your order and you want to sort them according to y values. What changes you will make in this program? You will simply modify your my comparison function and you will put y here. And the output is going to change. The output is going to change and this time we are going to get values in increasing order of y values, right? We are going to get 54 first, then 28, then 310. Now say we want to further change our program. We want to print all the points in decreasing order of y value. So what changes you will make? You will change your comparison function to this form. Now it will sort all your points in decreasing order of y. So what will be your new output? Your output is going to be 310, the largest y value, then the second largest y value 28, and then the third largest y value 54. This is output of this modified program. Let us now talk about time complexities and internal working of sort function. Sort function internally uses quick sort, and if you talk about more details, it is a hybrid of quick sort, heap sort and insertion sort. By default it uses quick sort, and if quick sort is doing unfair partitioning and going to take more than n log n time, it switches to heap sort. And when your array size becomes really small, it switches to insertion sort. So worst case performance and average case performance of sort function is n log n. Also the number of comparisons it does, it's n log n. So it's an n log n algorithm which is an optimal time for any general purpose sorting function, and it internally uses intro sort. Hi, in this video we are going to talk about sort in Java. In Java, sorting is implemented in two classes. One is arrays class and collections class, and this is similar to other algorithmic functions like binary search. Binary search is also present in both the classes. So arrays class has sort implementation for normal arrays, and collections class has sort implementation for collections. Now which collections allow sorting? The collections which are list interface implementing classes like array list, linked list, vector. So we can use collections.sort for all the classes which implement list interface. Now when you talk about sort function in arrays class, there are two types of arrays in the arrays class, arrays of primitives and arrays of non-primitives. Arrays of primitives are arrays of int, char, and the other arrays are arrays of objects like string, integer, student, where student is your user defined class. Please note that collections are there only for non-primitives. So array list and linked list, they cannot be made of int, char types. We can make an array list or linked list only for non-primitive types like string, integer, student. So when you are sorting an array of non-primitives, it is preferred to have a stable sorting algorithm. Let's understand stability with an example and importance of it when you are sorting an array of objects. Let's say we have this array of objects where this array has members and every member has two fields, branch of the student and enrollment number of the student. So this array is currently sorted according to all roll numbers, and this array is say all student data at one place. Now you want to segregate these students according to branches. So you sort this array according to branch, right? CS students should come together, EC students should come together. Now when you are sorting this array, one possible sorting is you just randomly put CS students together without following the original order. Your original array is sorting out according to roll numbers. So you don't care about the original order. Say you put CS104, then CS101, or you rearrange the EC students together. But you just do the sorting, the required sorting, which is sorting according to branch. This is unstable. And here is an example of a stable sorting algorithm. What stable sorting algorithm does, it puts CS students together, and together with this thing, it also ensures that original order of two CS students is retained. If one CS student was earlier in the original order, then it remains earlier in the sorted. So CS101 should come first, then CS104. EC102 should come first among all the sorted ECE students. So we have two ECE students, so 102 comes first and then 107. This is stable sorting algorithm. So Java's idea is this: if you have primitives, int, char, long type, right, these types, then stability is not required. It's obvious, right? I mean, if you have two integers, 10 and 10, you can put any 10 first, right? It doesn't matter because they don't represent any object. But when you have non-primitives, then stability might be needed. So Java has a simple rule. They use a stable algorithm when an array of objects is sorted, array of non-primitives is sorted, and they use unstable algorithm, which is slightly faster because it doesn't guarantee stability for primitive types. And the algorithm that is used for primitive types is dual pivot quicksort. Please note that I am mentioning this dual pivot quicksort because it is mentioned on Oracle documentation pages, and these are mentioned as of July 2020, and they may change the implementation later if better sorting algorithms come up. So they use this algorithm for primitives, and this is slightly faster because this algorithm does not have to guarantee stability. And for non-primitives, they use an algorithm which is based on merge sort. And this algorithm is adaptation of Tim sort algorithm. Tim sort is an algorithm which is used in Python sort functions. So this merge sort based algorithm ensures stability. You know, right? Quick sort by default does not ensure stability, and merge sort ensures stability. So they use merge sort based algorithm for non-primitives, whether it is collection. So the same algorithm is used for collections because they are only for non-primitive types. And for arrays of primitives, they use dual pivot quicksort, which is slightly faster. Let us now talk about arrays.sort. Arrays.sort is used to sort normal arrays, not collections. Like collections like array list, linked list, they are sorted using collections.sort. Arrays.sort is used to sort normal arrays, and these normal arrays can be of non-primitive types or primitive types. Here is an example to show the working of arrays.sort for primitive types. So we have integer array ARR1, which has elements 5, 20, 12, 30, and ARR2, which is a character array. So we are sorting both the arrays. We are first sorting ARR1 using arrays.sort. So what we get as an output, we get 5, 12, 20, 30. We have printed array 1 first. Then we are sorting array 2, which is an array of characters. So what it does, it sorts the array and you get the output as AA, BB, C. So even if your array has duplicates, this sort function works. Now an important thing about arrays.sort for primitive types. When you are sorting an array of primitive types, arrays.sort does not allow you to provide a custom comparator, right? You can only sort primitive types in natural order or increasing order, or you can say non-decreasing order if there are duplicates. So only that sorting is allowed by arrays.sort. And if you wish to sort the array in decreasing order, then probably you can first call arrays.sort and then you can reverse the array. Please remember, this natural order sorting restriction is only for primitive types. If you want to sort non-primitive types like your own user-defined class, for all those cases, for all non-primitive types, you can provide a custom comparator. In fact, collections.reverse order also works. So if your class objects are comparable, you can pass collections.reverse order to sort them in reverse order. We are soon going to discuss sorting for non-primitive types as well. Arrays.sort has one more version where you can sort a sub-array of the given array. And this version receives two parameters, from index to index, or you can call start and end index. So if you are passing a start index, the start index is included for the sorting and end index is not included. So it sorts the array from start to end minus 1. In this example, it's going to sort 1, 2, 3, these three elements, right? 1 to 4 means 1, 2, 3, right? Start to end minus 1. So what do we get after sorting? We get 5 and then these three elements are sorted, 10, 20, 30 and then 8. These elements, the remaining elements are not touched. So we can sort a subarray also using arrays.sort function. Let us now see an example where we sort an array of non-primitive types or an array of objects. So we have a class point which has two members, x and y. We have a constructor of this class that initializes x and y. Then we have a compare to function, and this compare to function is there because this class implements comparable interface. What it means is this class has itself a way of defining order of elements, right? It implements comparable. So you can simply sort this array of points by calling arrays.sort with ARR, and this will sort the array in increasing order of x coordinates because our compare to function works on the x coordinate of the point. And what it does, it simply subtracts p.x, the other parameter, from this .x. See, when an object is comparable, it means it can be compared with other object. So the other object is p, right? You have compare to function, the other object is p, and to define the natural ordering, which is increasing order, we always subtract the other object from the current object, right? So this is one way of comparing objects, array of objects or non-primitives. The other way is you write a separate class that becomes a comparator, that implements a comparator interface, and this is a place where this class implements comparable interface. So when a class implements comparable interface, means class itself is telling this is how you can compare my objects, right? So this class implements comparable. When we call arrays.sort, it simply uses compare to sort the array of objects according to increasing order of values of x. So what do we get as an output? We have passed three objects, right? Array of three objects. One is 10, 20, 3, 12 and 5, 7. And after you call sort, you are going to get them sorted by x coordinate. So you are going to get 3, 12, 5, 7 and 10, 20. And if you pass collections.reverse order after array, what collections.reverse order is going to do? It's going to reverse the order of compare to function, the natural order of the class objects, and it's going to give you the items in the reverse order. 10, 20 is going to come first, then 5, 7, then 3, 12. So this is one example where your class implements comparable interface. Now we are going to talk about an example where we write a class that implements comparator. Let us now talk about an example array such that this array is an array of objects of a class that does not implement comparable interface. Since the class itself does not tell you how to compare its object, what are we going to do? We are going to write a separate class, which is a comparator class, right? Why comparator? Because it implements the comparator interface. And when it implements the comparator interface, it must provide implementation of the compare function. So we have written a compare function, and please note that compare2 was taking one parameter because it was comparing current object with other object. Here we are comparing two objects. So what are we doing? We are doing p1.x minus p2.x. That is what he done to get the natural order, right? So what this function does, it basically ensures that when you are sorting an array of objects of point type, you get the items according to x coordinates in natural order. So we have created an array of objects here, and now if you see the arrays.sort call, we are passing an object of myCMP, right? When you pass an object of myCMP, this compare function is used to compare the objects of this class point. So when these points are sorted using this compare function, we get the output as 3, 12, 5, 7 and 10, 20. They are sorted according to x coordinates. We have printed the array here after sorting. In the beginning of this video, we talked about primitive type sorting. We mentioned that we can sort primitive types only in ascending order, and if we wish to sort them in decreasing order, we need to reverse the array. There are other ways also to handle primitive types. There are wrapper classes, right, which are not primitive types. Like for int, we have integer. So instead of creating an array of primitive type, we can change the array creation itself. We can create an array of integers, and then we can use collections.reverse order to sort this array in decreasing order. If we do not use collections.reverse order, then it will work like primitive type. It will sort the array in increasing order. But if you use collections.reverse order, you can get the array sorted in decreasing order, like in this code. So we have passed array, we have passed collections.reverse order. When we print the array, we get the array sorted in decreasing order. In fact, we can sort the array according to our own custom comparator. Now please pause this video and try to write down a program that sorts an integer array in such a way that all even numbers come first, then all odd numbers appear. Here is a program that sorts the integer array in such a way that all even numbers come first and then all odd numbers. So if you pass this array, your output is going to be 20, 10, 12, all even numbers in the same order as they appear in the original array, and then 5, 3, 5 and 3. Why is the order maintained? We discussed in the sorting video that if you're sorting non-primitive types, then the sorting is stable, and if you sort the primitive types, then sorting is not guaranteed to be stable. And the algorithm uses dual pivot quick sort, and here the algorithm uses merge sort based on merge sort. So we have stability in the merge sort and it's not there in the quick sort. So we get items in the same order because we have non-primitive type, integer is a non-primitive type. And let's see how does this code work. So what we have done here is we have passed an object of myCMP, and myCMP is a class that implements compare interface. And what does it do? It compares the remainder a_2 minus b_2. And if the remainder is 0, then this element is going to be preferred. And if the remainder is 1 with a and 0 with this, then the other element is being preferred. Right? In case of equal remainders, their stability is maintained. So this is an example code where we can sort even the wrapper types according to our own custom comparator, even if we do not have our own custom comparator support for primitive types. So we have two options. If we wish to sort in decreasing order, we can either use our own reverse function, or we can create a non-primitive type. And if you create non-primitive type wrapper class, then you can sort in decreasing order, you can sort in your own order as well. Hi, in this video we are going to talk about collections.sort. Collections.sort is used to sort collections, especially list collections. Collections.sort has this syntax where it says it accepts only list collections. Now what are list collections? List collections are the collections that implement list interface. And the popular collections that implement list interface are array list and linked list. So we can use collections.sort to sort an array list and sort a linked list. Here is an example code. We have created an array list here, right? And we have assigned it to a list variable of list type. Then we have added 3 items to it, and then we are sorting it using collections.sort. Please note that to use collections.sort, we must import java.util.collections. So here I have imported java.util.star to avoid writing multiple import statements, because to make this program compile, I need to import java.util.list, java.util.arraylist, and then java.util.collections. So I've written java.util.star. So we added 3 items, we sorted it, and after sorting we are printing it. So what are we going to get? We are going to get 5, 10, 20, which is natural order of these integers. Then we are sorting this list in reverse order. So what are we going to get? We are going to get the reverse order. We are going to get 20, 10, 5. Right? That's what is printed here. Now an important note, wrapper classes, they implement comparable interface. So wrapper classes like integer, character, they have implemented comparable interface. What it means is they have a compare to function inside them, which can be used to compare two integers to decide which one should go first. And collections.reverse order, it uses this compare to function and returns a comparator which does the reverse of what is written in the compare to of these classes. That's why it reverses in the, it sorts in the reverse order. Here is an example of collections.sort for sorting a list of items of user defined type. So I've created a user defined type point here, and this class has 2 members x and y. This class has a constructor, and this class implements comparable interface. So when a class implements comparable interface, you can use binary search on the objects of this class. You can use sort on the objects of this class. You don't need to do any extra work if you want to sort this array according to the same order as the compare to function implements. So here we are sorting the array of points according to x coordinate, and it's already implementing the comparable interface for this. So we can simply call collections.sort for this list. When you call collections.sort for this list, collections.sort uses this compare to function to sort the items. And what are we going to get the output? We are going to get 210, 510 and 1030, because 2 has the smallest x coordinate value, then 5, then 10. So that's why we are getting this output when we are printing the points after sorting. So we have sorted the list first, and then we are printing the list here in this part of the loop. So this is the for loop. Then we have end of main program and end of our main this class GFG. So this is an example of sorting a list of collections where your collection is of data type that implements comparable interface. Let us now talk about another example program where we use comparator interface to sort a collection. So we have the same point class. This time the point class does not implement comparable interface. So objects of this class are not comparable. And if we want to sort objects of this class according to x coordinate, then we need to do something extra. So extra that we have done here is we have written a separate class that implements comparator interface. So this is our separate class. I've called it myCMP. You can call it anything. You can call it point comparator. That would be a better name. So this class is used to sort the array of point objects according to our own criteria. And the criteria that we have used here is we are subtracting p2.x from p1.x. So the point is very clear. We want to sort the points according to x coordinate, increasing order of x coordinate, natural order, right? So what we do now to sort this collection or this list of points, we pass the list and we pass an object of myCMP. Now if you sort this way, and after that if you print the objects, if you print the points, you are going to get the points in sorted order according to x coordinate. So your output is going to be 220, right, the smallest x coordinate, then 510, then 1030. In all the examples that we have discussed, we have used array list. And in all the codes, if I simply replace array list with linked list, all these codes will still work the same way. That's the beauty of collections. That's the beauty of using interfaces and generics. So collections.sort is based on generics. It's for non-primitive types, and it's a part of collections. So if you see the Java documentation of arrays.sort, and if you see the Java documentation of collections.sort, you will notice that there are multiple declarations of arrays.sort for different data types. So there are two versions in arrays.sort, one that sorts the whole array and one that sorts a subarray. So these two versions are declared for all primitive types, right? And then there are versions for non-primitive types. But in collections.sort, there are mainly two declarations. One that does not take a comparator and one that takes a comparator. One thing is, in collections.sort, we cannot use sort function to sort a sub collection like we can do for sorting a subarray. That function is not there. So we have only two functions in collections.sort, and these two functions serve the purpose for all data types for all collections that implement list interface. Hi, in this video we are going to talk about stability in sorting algorithms. This is an important criteria to analyze algorithms. We want to know which algorithm is stable, which one is not. Let's see what it is. Let's understand this with this example. We are given an array of students. This array is already sorted in alphabetic order of their names. So it's lexicographically sorted by the names of the students. Anil comes first, then Ayan, then Piyush, then Ramesh. So they are increasing order of their names. We want to sort this array in increasing order of their marks. And in the sorted array, we want to make sure that if two students have the same marks, then they appear alphabetically in our output. This property is called stability. What it means is, if two items have same value, right, then they should appear in the same order as they appeared in the original array. So if you want to sort them in increasing order of marks, you will notice that there are 4 marks, 80, 50, 80, 50, 80. So you know for sure your output is going to have 4 students, where the first student has marks 50, second has marks 50, third has 80, fourth has 80. Now if you are using a stable sorting algorithm, then this algorithm will also ensure that the two people who have the same marks 50 appear in the same order as they appeared in the original array. Also, the two people who have same marks 80, they also appear in the same order in our output array as they appeared in the original array. So our stable sorting algorithm will sort it this way. Anil and Piyush, they have same marks. So stable sorting algorithm will ensure that Anil appears first, because it appeared first in our original array. Then Piyush appears. So 50-50 marks. Our first requirement is simple, to sort the students in increasing order of marks. That can be done by any sorting algorithm. But a stable sorting algorithm will ensure this order, that Anil appears first. Now if you look at Ayan and Ramesh, Ayan should appear first in your output. $80 and then Ramesh should appear. That is what a stable sorting algorithm would do. It not only sorts the array, but also ensures original order if two items have same value for the field for which we are sorting. Now stability is important only when you have objects of this form, where objects have multiple fields and you are sorting them for 1 or 2 fields, and you want other fields to follow the original order. Stability is not important if you are sorting an integer array, for example. It's not an array of objects, it's simply an integer array. No associated objects are there. Then stability has no use. It's useful when you have objects with many fields, more than 1 fields, and you are sorting them according to a set of fields. 1 field or 2 fields or 3 fields. So it is stable. An unstable algorithm can produce any output because the first requirement, the main requirement of sorting is to sort them in increasing order of marks, right? Other things are not important for unstable. Unstable does not care about stability. So an unstable algorithm can put Piyush first. And then can put Anil. And here maybe it does the same order. Or maybe reverses the order, because the unstable algorithm does not care at all what is the order. It might be same, it might not be same. So this is unstable. Why is it unstable? Because Piyush is appearing first here after before Anil, and they both have same marks and they appeared in different order in the original array. So that is why this algorithm, this output is an output of an unstable algorithm. Here are some examples of stable and unstable sort algorithms. Bubble sort, insertion sort and merge sort are stable. Selection sort, quick sort and heap sort are unstable. I'll just cover one example of both the algorithms to give you an idea why these two are stable and unstable. I'll cover bubble sort and selection sort. These other algorithms we'll discuss about their stability while we are discussing them individually. Let's talk about bubble sort. How bubble sort works? It always compares adjacent elements. Right? It always compares array I with array I plus 1. If array I is smaller than or equal to array I plus 1, then it does not do anything. And if array I is greater, then it swaps. So what it means? If two same items appear one after the other, it's not going to swap them, right? So that is why bubble sort is stable. Why? Because it always swaps adjacent elements, and it's not going to swap the adjacent elements if they are same, right? So it will keep the previous element at its previous position. So bubble sort is stable. Let's now talk about selection sort. Selection sort is not stable. How does selection sort work? You are given an array, it finds the maximum element in this array, right? And after finding the maximum element, what it does? It swaps this maximum element with the last element. Let's take a look at this example. What selection sort will do? It will find the maximum element. After finding the maximum element, what it will do? It will swap the maximum element with the last element. So what will happen? This 3 will come here. This particular 3 might be marks of a student X, Y, Z, and these 3 are probably the marks of a student ABC, right? So what happened? This X, Y, Z appeared before ABC after the swapping. You swapped this 3 with 18. That's what selection sort does. It finds the maximum element, swaps it with the last element, and then finds the second maximum or maximum in the remaining array, and that's how it proceeds. So when it is doing the swapping, it's actually disturbing the original order of values. That is why it is not stable. Hi, let's talk about bubble sort. Bubble sort is a simple comparison based algorithm and takes big O of n square time. Bubble sort has multiple passes. In the first pass, we move the largest element to last position, which is its final position. In the second pass, we move the second largest element to the second last position, which is its final position. We keep doing it until all the elements are moved to their correct positions. Let's now see the working. This is the first pass, this is second pass, and this is third pass. We have this array we want to sort. So what we do is, we compare the adjacent elements beginning from the first element. We compare these two elements, and since this element is smaller than this element, we do not do any swapping. We do swapping when the adjacent elements that we are comparing, they are out of order, which means the element that comes before is greater than the element that comes after it. So 2 is smaller, we do not do any swapping. Now we compare the next adjacent elements, and this time they are out of order. 10 comes before it, so we swap these two, right? And after swapping, next time we compare the next two adjacent elements, which are 10 and 7. And since they are again out of order, we swap these two. So after first pass, we have this array, and you can notice that 10, the largest element, has moved to the last position. It has bubbled up to the last position. So you begin from the first element, compare it with the second element. If they are out of order, you swap them. Then you compare second element to the third element. If they are out of the order, you swap them. Then you compare third and fourth. And if they are out of order, you again swap them. So this is how you ensure your largest element reaches the last position. Now you want to move the second largest element 8 to the last position. So we again follow the same concept. We begin with the first two elements, we compare them, and if they are out of order, we swap them. They are not out of order here. 2 is smaller, 8 is greater. Now we compare the next two elements, 8 and 7. They are out of order, so we swap them. We stop at this point because there is no point comparing 8 and 10 because 10 was the largest element. So we stop our iteration at this point, and now our two elements are fixed. So before this point, only 10 was sorted, and after this pass, 10 and 8 both are sorted. Now we move to the third pass. In the third pass, we want to ensure 7 is at its correct position. So in the third pass, we just need to compare these two elements. And once we compare these two elements, we decide that they are not out of order, so we keep 7 at its correct position. So these three elements are sorted. And once your last n-1 elements are sorted, this element is anyways the smallest element because last n-1 elements are not only sorted, they are the largest n-1 elements. So we need to do how many passes for n elements? n-1 passes. Because in n-1 passes, your n-1 largest elements will move to last n-1 correct positions, and your smallest element, which you want it to be the first position, it will be at the first position. Now please pause this video and try implementing this algorithm. Let us now talk about implementation of bubble sort. So here is simple implementation. We need to do n-1 passes. So we are running an outer loop from 0 to n-2 to have n-1 passes of bubbling. Now this is the code to bubble the largest element to the last position first, then second largest element to the second last position. Now what are we doing in this code? We are running a loop from j equal to 0 to n-2 again. Why n-2? Because we are going to compare array j with array j plus 1. So if we use n-1 here, then what will happen? It will go out of the index bound. So we run a loop for j equal to 0 to n-2 so that we can compare array j with array j plus 1. When j becomes n-2, then you will be comparing n-2th element with n-1th element, which is the last element. We compare array j and array j plus 1. If they are out of order, we simply swap them. Now can we optimize this solution further? Because if you take a look at this loop, I am simply running a loop from j equal to 0 to n-1 every time for every pass. And as we discussed earlier, after we have run one pass, one element is fixed to the last position, which is the largest element. And after we have run two passes, two elements are fixed at their correct position as last two largest elements. So using this fact, can we optimize this loop? The idea of optimization is this: if we are at ith iteration, then I elements are already fixed to their last position and they are I largest elements. So there is no point comparing the current element with those I largest elements. So we run this loop only till n minus I minus 1. That's the optimization we can make in the earlier implementation. Let's now see the working of this optimized code. So what we have here, I stands for the current pass, right? We are going to have n-1 pass. So I is going to vary from 0 to n-2. And for this pass, I equal to 0, we are going to run a loop for j equal to 0 to n-2. And n is 4 here. So n-2 is going to be 2. And for every j, we compare array j with array j plus 1. And if they are out of order, we swap them. So when j is equal to 0, we compare 0 and 1. They are out of order, we swap them. Now when we are j equal to 1, we compare 1 and 2 index elements. They are already in order, so we do not swap them. Now for j equal to 2, we compare this and this element, index 2 and index 3. They are out of order, so we swap them. And this is what happens after the first pass. You can notice that after first pass, your largest element moves to the end. This element is fixed at its correct position. So in the next pass, we need to run loop only from here to here, right? We need to only consider these three elements. So our loop runs from j equal to 0 to j equal to 1. And when you run for j equal to 1, you are anyways going to consider this element, right? So that's how our internal loop decision is made. So we run for j equal to 0. When we run for j equal to 0, we compare these two elements. They are in order, so we do not make any change. So when we run for j equal to 1, these two elements are out of order, so we swap them, right? And we get this array after the second pass. And you can notice that these two elements are sorted. Now we just need to fix these two elements. And to fix these two elements, we need to run the loop only once, right? Because these two elements will be compared only in one loop. So we compare these two elements in the next pass and they are out of order, so we swap them. And this is our final pass. After this pass, we have this array sorted. Let us analyze time complexity of bubble sort. This statement is the statement that executes maximum number of times. For I equal to 0, this statement is going to run n minus 1 times. When I is 0, this expression is going to be n minus 1. So this loop is going to run from 0 to n minus 2, and which means it's going to run n minus 1 times. And for I equal to 1, we have n minus 2 here. So this statement is going to run n minus 2 times. For I equal to 2, it's going to run n minus 3 times. So this is how the statement is going to run for different values of I equal to 0, I equal to 1, and when I is n minus 2. And sum of the series is n into n minus 1 by 2. So the time complexity of this implementation is theta n square. Now can we optimize this solution, especially for the cases when your array is sorted? Because if you take a look at this particular implementation, it's always taking n square time. Can you optimize it so that if your array is sorted or if your array becomes sorted in the middle, it does not do any more work? Let us now see the optimized implementation. In this implementation, we are maintaining a swapped variable. What we do is, we initialize swapped variable as false after every iteration, after every pass. And for the current pass, we check if any swapping happened or not. If any swapping happened, then we make the swapped variable as true. And if swapped variable remains false, it means no swapping happened. And while we were comparing the adjacent elements, we did not find any pair of elements out of order, which means your array is sorted. It has become sorted or it was already sorted. So you need not to proceed further. You can stop here and return from this code. Let's now understand this with an example. Here we have a sorted array. So when you run it for the first pass, when I is 0, you run the loop for j equal to 0 to 3, right? And inside this loop, when you are j equal to 0, you compare these two elements. They are in order, so you will not do any swapping. Your swapped will remain false. Again swapped will remain false. Again swapped will remain false. Again swapped will remain false. Swapped will remain false in all the iterations because you will never do a swapping. And if swapped remains false, you will come out of this whole function, you will break the loop and you are done with the sorting. So if your array is sorted, you can notice that we are running a loop only from 0 to n minus 2, right? 0 to 3, which means it does linear work. So the swapped variable, it enhances the performance, especially in the cases when your array is sorted or almost sorted, or it becomes sorted in the middle. It does not take n square time in all the cases. Let's now talk about stability in bubble sort. Bubble sort is a stable sorting algorithm. If you have two items with same value, it never changes their original positions. In this example, I have taken 3 items with same value, 6, 6, 6, and we are going to see that these 3 6s remain in the same order as they were earlier. So this is 6 number 1, this is 6 number 2, this is 6 number 3, and they are going to remain as it is here. See, bubble sort, how will it work? it will compare these two elements first. They are in order, then it will compare these two elements. They are in order, then it is going to compare these two elements. They are not in order, it's going to swap them. It does the swapping only when the previous element is smaller. There's no equal to sign. So it does swapping of adjacent elements, and that is only done when you have greater element on the left side and smaller element on the right side, not equal. So this is what happens after the first pass. Now when you come to second pass, these two 6s, they are same. So they are not swapped. These two 6s, they are again same, not swapped, right? And we stop our bubble sort here because we did not do any swapping in this pass. We have a swapped variable. So we can notice that bubble sort algorithm never changes order of equal elements. So bubble sort is stable and it also in place because it does not require any extra array to copy the original elements. It modifies the elements within the array only. Let's talk about selection sort algorithm. Selection sort is one of the basic algorithms like insertion sort and bubble sort. It is a comparison based algorithm and has theta n square time in all cases. The good thing about selection sort is it does less memory writes compared to other algorithms. If you compare it with other popular algorithms like quick sort, merge sort, insertion sort, bubble sort, etc., you can notice that this algorithm is going to do less memory writes compared to these algorithms. However, this is not the optimal algorithm in terms of memory writes. There is another algorithm called cycle sort, which is optimal in terms of memory writes. Memory write can be a costly operation in situations like EEPROM. In EEPROM, if we do more writes, age of this memory reduces. So in those cases, we can prefer selection sort over other sorting algorithms. It's a basic simple sorting algorithm and can reduce memory writes. Not only EEPROM, there can be other situations where memory writes are costly. Suppose you are writing data to hard disk. You are sorting some files and you are putting individual files on the hard disk when you are swapping them or when you are putting them into the memory. So this is an advantage of selection sort. Next important point about selection sort is it's a basic idea for heap sort. Heap sort idea is based on selection sort only. It is just that heap sort uses heap data structure to optimize the selection sort idea. Selection sort is not stable in basic form. When we do selection sort, the order of equal elements may change. The next point is it's an in-place algorithm. It does not require extra memory for sorting. Let us now understand the basic idea of selection sort algorithm. With this example, we are going to sort this array in increasing order. So the basic idea of selection sort algorithm is we find out the minimum element, we put it at the first position. Then we find out the second minimum element and put it at the second position. Then we find out the third minimum element and put it at the third position. We keep doing it. At the end, we have the array sorted. Now please pause this video and try to implement this idea. Let us see the naive implementation now. We first traverse the input array, find out the minimum element and put it at the first position in our temp array. And we replace this element with infinite. Now we traverse through the input array again, find out the minimum element again and put it at the next position in temporary array and replace this element with infinite. Now we traverse through the input array again, find out the minimum element, put it here and replace it with infinite. Same thing we do for remaining elements. This is replaced with infinite, comes here, replaced with infinite and comes here, replaced with infinite and comes here. That's how we get the sorted array. Let's see the implementation. We have created a temporary array of same size. Now we are traversing through the input array. This I decides the index where this next minimum has to be put. So first time index I was 0, so we put 2 at index 0. And inside this loop, we find out the minimum element first. Right? We initialize the index of minimum element as 0. Then we traverse through elements from 1 to n-1 and we compare it with current minimum. If it's smaller than current minimum, then you update the current minimum. And after that, we put the found minimum element at index I and we put the value infinite at this minimum element index. And at the end, we copy the temporary array back to the original array so that our original array is modified and we have the sorted array. So we are going to copy these elements here. 2, 5, 8, 10, 18 and 20. So this is our final sorted array. Now please pause this video and try to optimize this solution. In this solution, we are using an extra array temp, right? And this selection sort algorithm should be in place. We should not be using extra array to store the sorted array. Let us now see a better implementation that does not use an auxiliary array. We do all operations within the same array. Let's now understand the idea with this example. In the first iteration, like the naive implementation, we find out the minimum element, which is 2 here. And instead of putting this 2 into a temporary array, we know this 2 is going to be at index 0. So we swap it with the current element at index 0. So 10 comes here, the current element at index 0 comes here, and this element goes to the index 0, right? And now what we do is, we know this element is sorted. This is fixed at its correct position. Now we have this remaining array, and we find out the minimum element in this remaining array. And minimum element in this remaining array is 5. And next position where this minimum element should go is also 5. So we swap 5 with 5 and we have this array now. So these two elements are sorted. Now we again find out the minimum element in the remaining array. And minimum element in the remaining array is 8. And the position where it should be is also the third position. So we swap 8 with 8 itself and we have this part sorted. Now we find out minimum element in the remaining array. Please note that at every point we are maintaining two arrays. One array which is already sorted and one sub-array which is yet to be sorted. And we find out the minimum element in the unsorted part. So minimum element now is 10. And where 10 should go now? It should go at this position. So we swap these two elements. So 10 comes here and 20 goes there. Now we have remaining unsorted array as these two elements. We find out the minimum among these two, which is 18, and we swap it with the position, with its original position. So they are swapped. So we have 18 here now. Now we have only one element remaining. We find out the minimum element in this one element, which is 20 itself, and we swap 20 over 20. We can in fact skip the last execution part of this code or this algorithm because we know it's going to be only one element and there's no point swapping this element with itself. We can actually optimize this to run to n-1 instead of n, right? This is one optimization we can make because this part is not necessary. There's only one element left and it's going to be swapped with itself only. So let's now see the implementation. We are running a loop for I equal to 0 to n-1, where elements from 0 to I are maintained to be sorted and elements from I plus 1 to n-1 are not yet sorted. So we find out the minimum element from the unsorted part from I plus 1 to n-1. We find out the minimum element, we find out the index of the minimum element in a variable called min index. And once we have found the minimum element, we swap it with the array I because we know this element should be going at the array I, and we move the element minimum index to I and I to minimum index. We swap these two, right? That's the simple implementation of this selection sort. Let's now see stability in selection sort algorithm. Selection sort is not called stable because if there are two elements with the same value, it may change the order of these elements. And why do we care about stability? See, these two items values which are there in the arrays, they might represent individual values of the objects. For example, these values are marks of the students and these students are ordered according to maybe alphabetically or institute name. And if there are two students with the same marks, we want to keep them in alphabetic order, right? We don't want to change that order. So if we apply selection sort here, what happens here is this 90 moves to a position after this 90. See, in the first iteration, what we do in this selection sort, we find out the index of minimum element, which is 3, and we swap it with the first element. So this 90 comes here, and that's where this selection sort becomes unstable, right? And rest of the algorithm follows the same process, right? But this is the step where we have instability and these 90s never change their position back again because it has come to the end, its final position. So we do not have stability in selection sort. Let us now see the time complexity of selection sort. So the innermost statement is this statement that executes maximum number of times. Let's now try to find out how many times this is going to execute. When I is 0, it's going to execute n minus 1 times. This condition is going to be checked n minus 1 times. When I is 1, it's going to be checked n minus 2 times. And when I reaches n minus 2, it's going to be checked 1 times only. So this condition is being checked these many times. In the first iteration of I, it's going to check n minus 1 time, then n minus 2 times, n minus 3, and so on, then 2, and then 1. If we sum this series, we are going to get n into n minus 1 by 2, which is theta n square. So this particular statement is being executed theta n square time, and this is the most executing statement of this loop, of this code. So that's why the time complexity of selection sort is theta n square. And in selection sort, it does not happen that there is a best case which is having time complexity less than n square. It always takes n square time. Even if you provide the sorted array, it's going to take n square. Even if you provide reverse sorted, then also it's going to take n square. Let us talk about insertion sort. Insertion sort is a simple sorting algorithm. Like bubble sort and selection sort, it's very easy to write the code, very simple to understand. But like those algorithms again, it's a quadratic time worst case. That's not the best possible time for a sorting algorithm. There exists sorting algorithms that sort an array in big O of n log n time. Algorithms like merge sort and quick sort, they take only big O of n log n time sort this array, and it takes quadratic time. We are going to study merge sort, quick sort in the upcoming videos. The next important point about insertion sort is it is in place and stable. So what do we mean by in place? In place is typically defined this way, that an algorithm is called in place if it does not use any auxiliary array or any auxiliary space in terms of input size. However, there are other definitions, like there are algorithms like quick sort which are called in place, however they use recursion called stack. But here, insertion sort takes big O of one auxiliary space only. It does not take any space, even for recursion, nothing. So it takes only constant number of variables. Stable. Insertion sort is stable. We've discussed stability earlier. So what is stability? When you have two equal elements, their original order is retained. Let's now see the next point. Insertion sort is the most popular and the most efficient algorithm for small sized arrays. When you have small sized arrays to sort, insertion sort is always preferred. So there are sorting algorithms which are used in standard library functions. For example, Python uses timsort. And timsort, what it does, it uses merge sort, which is an n log n algorithm for sorting for general purpose arrays. And when your array is small, or when you are doing merge sort and array size becomes small, it switches to insertion sort. So insertion sort is used in these hybrid algorithms, timsort and introsort. Why am I calling these hybrid algorithms? Because they use 2 or 3 sorting algorithms together. For example, timsort uses merge sort and insertion sort. Introsort uses heap sort, quick sort, and insertion sort. And these both algorithms use insertion sort when your input is small or when input becomes small. Insertion sort requires big O of n time in the best case. And interesting thing about insertion sort is best case happens when your input array is already sorted, and the worst case happens when your input array is reverse sorted. Let us now talk about idea for insertion sort. So what we do in insertion sort, we maintain a part already sorted, right? And when we are at current element, we insert this current element into the already sorted part and we make the sorted part bigger. So when you are at index I, your elements from 0 to I minus 1 must be already sorted. And what you do with element at index I, you put it at its correct position and you increment the sorted part from 0 to I minus 1 to 0 to I. It increases by 1. So see, when you have an input array, this single element would always be sorted, right? First element is only, so there's no point of doing anything about it. It's a single element. So we begin with the second element, and what we do, we try to put it at its correct position in this sub-array, right, from 20 to 5. So 5 goes here. Then we come to 40, 40 is already at its correct position. Then we come to 60, 60 is already at its correct position. Now when you come to the next element 10, see, this part is already sorted from 5 to 60. Now you want to insert 10 at its correct position in this sub-array 5 to 10, right? So where will you put for 10? You will put 10 here, right? So you put 10 here and this part becomes sorted. right? Now you come to next element 30. So this whole subarray is sorted, only 30 is left to be put at correct place. So you put 30 at its correct place and 30 comes here and your whole array becomes sorted. So what we are going to do, we are going to run a loop that begins with the second element, because first element is already sorted, right? So for second element, our I is going to begin from 1, right? Now we are going to consider this 5 and we are going to put it in the sorted subpart or prefix subarray from 0 to I minus 1, which is only single element. And once 5 is placed there, we are going to do the next iteration for 40, right? And we are going to put 40 at correct place, and I equal to 3, I equal to 4, and I equal to 5, right? After I equal to 5, we get this array sorted. So this is how we are going to run a loop. Now it's still not done. There is slight complication. How will you put this element at correct position? These are simple array operations. You need to simply insert an item. So please pause this video and try to write down insertion code yourself. Now you have the complete idea, right? You are running a loop from I equal to 1 to n minus 1, n is the size of the array. And at every index I, your array from 0 to I minus 1 is sorted. And you just need to put this element at correct position here and your sorted part increases by 1. Here is implementation of insertion sort. We have a function that takes an array and size of array as an argument. If you're programming in Java, then you can get the size by doing array.length. So what we do inside this function, we run a loop from 1 to n minus 1. So for this array, the size or n for this array is 6. So we are going to run a loop from I equal to 1 to 5. So what are we going to do in this loop? We are going to begin with I equal to 1, which means this element, and we are going to go till n minus 1. And for every element, we are going to first store it in a variable key, and then we are going to go to its left side and we are going to find its correct position in the sorted array, right? And once we find the sorted array, we increase the sorted array part, right? That's all we are going to do in every iteration. So key is initially part of unsorted, and after this iteration for I, this becomes part of sorted array, right? Our sorted array is going to increase. We are going to maintain sorted and unsorted. So when unsorted array is of length 0, your array is sorted. So when key is 5, right, you begin with I equal to 1. What you do is you want to put it at its correct position, right? So you want to make this sorted part is 520. For that, what you do is you go to the left side and you run a loop. You run another loop from I minus 1, and this loop will run while j is greater than equal to 0 and array j is greater than key. While key, while key is smaller, then only you will run this loop. As long as you find an element which is smaller than key, you will stop. We can better understand by this iteration. See, I is currently here. So what we do in this iteration, we begin from here and we go to the left side and we keep running the loop while elements are greater than the key or key is smaller. So we run the loop for 60, 40, 20 and we stop here, right? We stop at 5. And while we are running the loop, we move all the elements one position ahead. So we move 60 here, 60, this element becomes now 60, right? And since we are going to overwrite it, that's why we have stored it in a variable key, right? Now we move 40 here, now we move 20 here. So these two elements, they both have 20, 20 now. And after this iteration is over, at this location, we are going to write 10, right? That's what we do. At ARR j plus 1, we write 10 because our loop stopped when j was here, right? For 5 it stopped. So we're going to go here and we are going to write 10 here. That's what we do inside this loop. Same thing happened with this case. When I was 1, there is only one element. So we run the loop once, right? And then j becomes 0, right? Negative actually. So we come out of the loop, j becomes minus 1. And what we do after that, we write 5 here. And before writing 5 here, 20 must have been written here by this loop, by this iteration, right? In the single iteration. So this is how this inner loop works. It moves all the greater elements one position ahead to create a space for the new key to be inserted, right? And then after the loop, we insert the key at the created space. And this is how we sort the whole array. Let's now quickly see those cases as well when array I is greater than left of it. See, for example, here 40 is greater than 20. So we don't go inside this loop. And what will happen in this case? See, j is I minus 1, right? And since we do not go inside this loop, we do array j plus 1 equal to key. So 40 is going to overwrite itself, right? Same thing will happen here. 60 is going to overwrite itself. Now let's quickly talk about this condition also. Why don't we have equal to sign here? See, this logic will still work if you have equal sign, but then this algorithm will not be stable. By keeping the greater sign, not considering the equal sign, we make sure that the algorithm is stable. See, there was say 2 occurrences of 5. Say this element was also 5, right? So what will happen? You will stop here. You will not move this 5, right? Because this has come earlier. That's the advantage of not putting equal to sign. This algorithm remains stable. That's why we say insertion sort is stable. If I put an equal to sign there, then it won't be stable, because in that case, if there is a 5 here, then this 5 is going to come here and this 5 is going to move 1 position ahead, right? It will lose the stability. Let us now talk about time complexity of insertion sort. Time complexity of insertion sort in the best case is theta n, and in the worst case is theta n square. And in general, we can write it as big O of n square, right? Big O of n square covers both theta n square and theta n, because big O means upper bound. Let's now see how it's big O theta n in best case, and when does the best case occur? Best case occurs when your input array is already sorted. For example, your array is 10, 20, 30, 50. What happens in sorted array? You never go inside this inner loop. When you run for I equal to 1 in this example, your key is 20 and previous element is smaller, right? So you will not go inside this while loop. Same thing will happen for 30, same thing will happen for 40. You will never go inside this loop because this condition will never be true. So what you will be doing? You will be overwriting every element with itself. 10 will overwrite itself, then 20, then 30, then 50. And that's all is theta n work. You are doing constant work in every iteration, overwriting the element with itself. So the time complexity is theta n. Let's now talk about worst case. Worst case happens when your array is reverse sorted. What happens in reverse sorted is you are doing maximum shiftings in every iteration. When you are here, then 50 will shift it here, right? And you will have, after placing 30 here, you will have 30, 50, and then 20, 10. Then when you come to this element, right, 50 will be shifted here, then 30 will be shifted here, because both are greater than 20. So your array will become 20, 30, 50, and 10. And when you are here at this element 10, again maximum shiftings will happen. You will be shifting all 3 of them. So your array will become then 10, 20, 30, and then 50. So you are doing maximum shiftings. And how many shiftings you do for I equal to 1? You do 1 shifting. For I equal to 2, you do 2 shiftings. And you are going to run a loop from 1 to n minus 1. So you are going to do 1 plus 2 till n minus 1. These many times your inner loop is going to run and shift the elements. And this is n into n minus 1 by 2. Right? The summation of natural number formula for n equal to n minus 1 is this much. So this is clearly theta n square. We can ignore the lower order terms. We can ignore the constants. So we get the time complexity is theta n square in the worst case. And so we can write in general as big O of n square. That covers both of them. In this video, we are going to talk about merge sort algorithm. Merge sort is a divide and conquer algorithm. It first divides your input array or list into 2 parts. Then it recursively sorts these 2 parts, and after sorting these 2 parts, it merges them. The implementation that I've just talked about, it's a typical implementation of merge sort, and there are variants that exist. The good thing about merge sort algorithm is it is a stable sorting algorithm. It maintains the original order of equal items. The next good thing about merge sort is it works in theta n log n time, which is the best possible time you can get on a single processor and for random input. The one bad thing about merge sort is it takes big O of n extra space. It's not an in-place sorting algorithm in its normal form. However, there have been optimizations and variants of merge sort. There is a variant called block merge sort that works in n log n time and in place. But in its typical form, it takes big O of n auxiliary space. The next good thing about merge sort is it's well suited for external sorting. We can bring in parts of input to be sorted in RAM. We can sort those parts, and by sorting the parts we can sort the whole array as well, whole input as well. We don't have to have the whole input in RAM. One more bad thing about merge sort, it is outperformed by quicksort. In general, for arrays, not for lists, for linked lists, for arrays, quicksort in general works better than merge sort. But merge sort is still used a lot in many standard library implementations. Your Perl library is using merge sort. Java 8 uses both quicksort and merge sort depending upon the input type. Python uses a variation of merge sort called Tim sort, which is merge sort plus insertion sort variation. Let us talk about this problem. We are given two sorted arrays. We need to print all the elements of both the arrays in sorted order. Let's understand the problem with these examples. The first array is 10, 15, 20. Second array is 5, 6, 6, 15. So we need to print all these in sorted order. The smallest element 5, then 6 2 times, then 10, then 15 2 times, then 20. In this example we have 1, 1, 2 and then 3. So we need to print all these 4 in sorted order. Now please pause this video and try to write down a function that takes two sorted arrays as input and prints all the elements of both the arrays in sorted order. Here is a naive solution to solve the problem. Let's say we are given this array A as this, and m is the length of this array B as this, and n is the length of this array. What we do first, we create an array of size m plus n, right? We create an array of size 6 in this example. After creating the array, we copy the elements of first array into this array C. So I have created array C of size 6, and first I have copied the array A elements into the array C. Now we copy the array B elements into C. So our C array now contains both array elements, but they are not in sorted order. So what we do, simply we call the sort function on C array and we get the elements sorted order. So we have all the elements of A and B in sorted order in array C, and that's what we wanted. So we can simply traverse through array C and print it. So we'll get the output. Here is implementation of this. So this is C++ style syntax. In Java you can create an array of size m plus n this way. Also in Java you don't have to pass lengths as parameters. You can get lengths m as a dot length and n as b dot length. First thing we do is we run through the array A, we copy the elements of array A to C. Now we run through array B and we copy the elements after index m is the length of array A. This way we have all the elements of A and B in array C. Now we sort this array C, right? And this is syntax to sort in C++, this is the syntax in Java. After we sort, we simply traverse through array C and print the array C. Now what is the time complexity of this? See, you are sorting an array of size m plus n. So this is the majority of the time taken by this algorithm, which is m plus n into log m plus n because of the sorting algorithm. This is big O of m, or you can say theta of m, because it's always going to run m time. This is theta n, this is theta m plus n, but this is big O of m plus n into big O into log of m plus n. So this is the time complexity. We can ignore the lower order terms. That's what we do in asymptotic analysis. And auxiliary space is theta m plus n for this array. Now please pause this video and try to think of a solution that works in linear time, theta m plus n time, and requires big O of 1 auxiliary space. Let us now talk about idea for the efficient solution. The idea is this: we are going to traverse both the arrays simultaneously. We are going to use two index variables I and j. I to access array A elements, j to access array B elements. For example, if you have these two arrays, you will have I and j initially 0, which means you are currently referring to 10 and 5. So what you are going to do is, you are going to compare AI with BJ, right? Then there are two cases that we are going to handle. The first case is when AI is smaller than or equal to BJ, right? Which means BJ is either greater or equal. And the other case is when BJ is smaller, right? And we are going to write some code for these two cases, logic for these two cases, and let's understand the logic. I've written the question mark here for you to write the logic, but we'll easily get the logic by this example. So if I compare 10 and 5, and if bj is smaller, right, bj is smaller here, right, 5 is smaller than 10. So what should we do? We want to print both the array elements in sorted order, right? So what should we do? We should print the element 5, right? And since we have processed this element 5, we need to move ahead in array B. So we print 5 and we make j equal to 1. Now we are again going to compare 10 and 50, and now 10 is smaller. So what are we going to do? We are going to print 10 on the screen and we are going to move ahead in array A. So we print 10 on the screen, make I equal to 1. Now we are going to compare 20 and 50. Now 20 is smaller, so we are going to move ahead in array A and we are going to print 20. Print 20 and move ahead. Now we are going to compare 35 and 50. Now 35 is smaller. We are going to print 35 on the screen and now we are going to make I equal to 3. When I becomes 3, it becomes an invalid index. It goes beyond the last index. So if any of the arrays goes beyond the last index, you need to stop the loop because you can't do the comparisons anymore. So you stop at this point, but you have not processed these two elements yet. So the idea is this. See, once you have traversed both the arrays simultaneously and you have printed some elements, you have printed these 4 elements, whatever remaining elements are there, they are always going to be greater than already printed elements. Like 50, 50 are greater than these 4. And since the array A is sorted, array B is sorted, both the arrays are sorted, whatever array has remaining elements, those remaining elements will also be sorted and they will be greater than these elements which have already been printed. So what all you need to do is, you simply need to run a loop to print the remaining elements. Now you have the complete idea. Please try to fill the gaps here, what you will write here, and then try to write the complete code. So I've written the statements or expressions when AI is smaller than equal to bj. I'll print AI and do I++. That's what we did here, right? In this case, we'll print bj and do j++. Now, why do we have equal to sign here? See, this merge function that we are going to discuss is stable also. If you have 2 elements, right, and if you have, say, this also 50, then array A element would appear first in the output. This will be ensured if I put equal to sign here. See, I can remove equal to sign here from here, then it will not be guaranteed that in case of equal occurrences, array A elements will appear first. And stability is important in sorting. We are going to discuss, we are basically discussing this logic for merge sort, merge function, right? And merge sort is stable. So this equal to sign, that's why it's put where when A is smaller, so that you process array A elements in case of equality also. So now please pause this video and write down the complete code yourself. Here is complete implementation of the algorithm. We have written a merge function that takes array A, array B, M and N as 4 parameters. We initialize I and J as 0. We run a loop while I is smaller than M and J is smaller than M. See, the point is we want to come out of the loop as soon as we reach at the end of any of the 2 arrays, right? So I should be smaller than M and J should be smaller than N for this loop to run. And inside this loop, we have the same logic that we've just discussed. If AI is smaller or equal to bj, then we print AI and move ahead in array A. Otherwise, we print bj and move ahead in array B, right? For example, here we compare 10 and 5. 5 is smaller, bj is smaller, we make j equal to 1. Now we compare 10 and 50. 10 is smaller, we print 10 and make I equal to 1. We compare 50 and 20. 20 is smaller, we print 20 and I equal to 2. We compare 50 and 50. 50 same, right? So we fall into the this if case. See, again I'm telling you, equal case is used to ensure that the first array elements appear first. In the merge sort call implementation, we are going to pass first half of the array and second half of the array to this merge function, right? So we want to ensure that the first half equal elements should appear first. That's why we have equal in the merge. So we are going to print 50 in this case, and we are going to move ahead in array A. So I now becomes 3 and I has reached last index. I has reached beyond the last index. So we come out of the while loop. When we come out of the while loop, we have 2 more loops and we'll always execute one of these 2 loops. We'll never end both of them, right? In this case, we are going to execute this loop while j is smaller than n, right? Because we have right now j as 1, right? And we have elements to process in array j, these 2 elements 50 and 50. So we are going to run an iteration here for j equal to 1, and we are going to print 50, and then we are going to make j equal to 2, right? Then we are going to run one iteration, 50, and make j equal to 3. Now j becomes invalid, so we come out of this loop as well. So this is how this function works. Now how does this function always work? See, if you are at index I in array A and at index j in array B, and these two arrays are sorted, that's our primary condition. Now if I just compare these two elements and I simply process the smaller elements, that will be the next element, because all the elements after this are going to be greater than this, and all the elements are after this are also greater than or equal to this. Here also greater than or equal to this, we allow equal elements also. And if AI is smaller than Bj itself, then it's going to be smaller than all these elements also and all these elements also. So we can safely print AI, and the same thing applies to Bj. That's how this algorithm works. And talking about the time complexity of this algorithm, if you see in this loop, we are either incrementing I or we are incrementing j. And what is the range of I from 0 to m minus 1, and what is the range of j? 0 to n minus 1. So we are incrementing one variable which lies in range from 0 to m minus 1, and another variable which lies in range 0 to n minus 1. So the total range size is going to be m plus n only, and we are going to moving ahead in this range by either incrementing I or incrementing j, right? So the upper bound on this time on the number of iterations is obviously m plus n, and it will not run m plus n all the time. For example, it did not run m plus n all the time. Two elements were there to process, and the remaining elements are processed. So if you see overall the running time of this loop, it's proportional to m plus n, right? Whatever extra elements, remaining elements which are not processed here, they will be processed by one of these two loops. So the time complexity clearly is theta of m plus n. I'm using theta notation because it's exactly m plus n. You are going to run m plus n times, right? Theta m plus n times, 1 or 2 extra do not matter. And auxiliary space is clearly big O of 1, right? We are not using any auxiliary area here. We are simply printing the elements. Let us talk about this problem. We are given an array and 3 indexes in it. Indexes are low, mid and high. We are given that elements from low to mid are sorted and elements from mid plus 1 to high are sorted. For example, low is 0 here, high is 4 here. Elements from low to mid means 0 to 2 are sorted, and elements from mid plus 1 to high are sorted. We need to sort the array from low to high, right? So we basically need to merge the sub-arrays. We need to merge this sub-array with this sub-array, and we get this. In this example, low is 0, mid is 3 and high is 4. So we have sorted array from sub-array from 0 to 3, and 4 to 4 is also sorted. So we need to merge these two and we get this one. So basically we are given 3 indexes in an array, and low need not to be 0. That's why I've used dot dot dots here. And high need not to be the index of last element. That's why I've used dot dots here as well. So I'm given low, mid and high. Low to mid sorted, mid plus 1 to high sorted, and I want to sort low to high. We are also given this, low is smaller than equal to mid and mid is smaller than high. What it means is there is going to be at least one element from low to mid range, and there is going to be at least one element from mid plus 1 to high range. See, we have low to mid, that's why we allow equal to here, right? And mid plus 1 to high, that means we should have the greater sign here to allow one element. Now please pause this video and try to write down a function that takes an array as an argument, takes 3 indexes as argument. Your function may assume that your array has at least 2 elements, right? This condition is followed, right? And the indexes are given in such a way that they follow this rule. You may also assume that elements from low to mid are sorted and mid plus 1 to high are sorted. Your task is to sort the subarray from low to high. Let us now talk about the idea to solve the problem. What we are going to do is, we are going to follow the same idea as we've discussed in merge 2 sorted arrays. There we were given 2 sorted arrays and we want to produce the merge thing on the output screen. Here we are given the same array and we want to merge 2 sub-arrays of it. So what we do here is, to solve it in a similar way, we create 2 auxiliary arrays left and right. Size of left array is chosen in such a way that it can store the elements from low to mid. Right is chosen in such a way that it can store the elements from mid plus 1 to high. Once you create these two arrays, you copy the elements from low to mid to left. You copy the elements from mid plus 1 to high to right. Now you simply need to write the same logic that we wrote in the merged to sorted arrays. The difference here is, there we were printing on the output screen. Here we need to put the merged part back into the original array. So now you have the complete idea what all we need to do in this function. Please pause this video and write the complete function yourself. Here is implementation of the merge function. We are going to use this function as it is in our merge sort implementation. What are we doing here? We are first getting the size of left array. See, if you are given this array, low is 0 and mid is 2, the size of this array is going to be 3, which means mid minus low plus 1. And size of right array from mid plus 1 to high is going to be high minus mid, which means 4 minus 2, 2. So we get the size of left array, size of right array. We create two arrays, left and right. We copy the first n1 elements of our given array to left. We run a loop from 0 to n1 minus 1 and copy the elements starting from index low plus high. See, this is important. Low might not be 0 all the time. The reason is we are going to use this merge function in the merge sort, and merge sort would call this merge function for intermediate subarrays also, where low might not be 0. After copying the n1 elements from array A, first n1 elements from array A, then we copy the remaining elements from array A. So we are going to beginning copying from n1 plus I, right? And I is going to go from 0 to n2 minus 1. So we have first n1 elements in left and then n2 elements in right, and n1 and n2 are these and these values. After you have built the left and right arrays, your logic is same as what we have discussed in the previous video. So I'm not going to discuss this in detail. This is something we have already discussed. The standard merge function. There in the previous implementation, we were printing the elements in the merged order. Here we want to store them in an array A, right? In our original array A. So we are using an additional index variable k, right? Instead of printing left I on the screen, we are going to store left I in ak, and we are going to increment this index k also. Here also we are storing this element right j into ak in this case also, and we are incrementing k++. And whatever elements are remaining in either left or right, those elements are also going to be copied to the array A, right? And k is always incremented. K is all the time incremented in all loops. So if you are given this array, this part of the code is setting up left and right temporary arrays. So after you execute this part, your left and right arrays would be this, and this part is now merging left and right arrays into original array A. So after this part, your A will become this. This was your input A, and now it becomes A. These two subarrays are merged. Now the time complexity of the solution is clearly theta n. N is the number of elements from low to high, right? So we have discussed this in the previous video that this overall runs n times, and this part is also theta n, right? N1 plus n2. Talking about the auxiliary space is also theta n, n1 size of left and n2 size of right. Let us now talk about merge sort algorithm. How does this work? As we discussed, merge sort is a divide and conquer algorithm. We take an input array and we also take two indexes, L and R. L is the first index of this array. If your array is 0 based, then it's going to be 0. R is last index, which is the last index of your array. So 0, 1, 2, 3, 4. So if for this array, L is going to be 0 and R is going to be 4, right? What do we do after taking the input array? We first check this. Does this input array contain at least two elements? Because if there is one element in your input array, then there is nothing required to be done. It's already sorted. To do something on your input array, to do divide and then sort and then merge, we need to have at least two elements. So we put this condition. At least two elements should be there. Then only we perform our merge sort logic. Otherwise, we do not do anything. After checking for at least 2 elements, we find the midpoint of our input. So this expression that I have written here, it is same as L plus R by 2. It's same as. The purpose of writing L plus R by 2 is to avoid overflow. What happens in merge sort and binary search algorithms, if they do this L plus R by 2, and if L and R are high, then there might be overflow for large arrays. If you are not getting it now, we'll discuss it in detail after we discuss the merge sort algorithm. But the idea of this expression, the meaning of this expression is same as this. The only purpose here is to avoid overflow. We'll talk about this in more detail. So we find the midpoint for our input array. That's what we do here. So we have 0 and 4, and mid is going to be 0 plus 4 by 2. Or if we follow the expression here, it's same as R plus L by 2. So we'll get 0 plus 4 minus 0 by 2. Right. So we'll get 2. We get 2 as a midpoint. After finding the midpoint, we recursively sort the array from L to mid. So we have the midpoint M as 2, right? So this is where M is. We recursively sort this half, right? And we assume that our merge sort function works. So this sort is going to sort this array to 5, 10, 30, right? We'll discuss in detail like how does this happen. Actually, it happens due to merge function. But we recursively sort this left half, and after that we recursively sort the right half. So we get 7, 15, right? These two arrays we get. These two sub-arrays of input array are sorted by these two calls. After sorting these two sub-arrays, the half-half sub-arrays, we call the merge function. And what merge function does, it takes this half, it takes this half, and it merges these two. And we have talked about merge function. So what it is going to do, it is going to merge these two sorted sub-arrays of our input array. So what we'll get after merging these two, we'll get 5, 7, 10, 15, 30. And that's a sorted array. So our input array is modified to this thing, right? So we get the sort in this way. So what we do in merge sort, we first check if there are at least 2 elements, right? If there is 1 element, there's no point sorting. After checking this, we find the midpoint, right? After finding the midpoint, we recursively sort elements from low to mid. And then we recursively sort elements from mid plus 1 to R. After sorting these two halves, we merge these two halves. And merge, how does merge work? It takes 2 sorted arrays, which are 2 sorted halves of your input, right? So it considers one sorted array from L2, array L to array M, and other sorted array from M plus 1 to R. And we tell this merge function that this is the point to which you need to consider the left half. And after considering these 2 sorted subarrays, a merge function simply does the merge logic and makes one sorted array. Let us now do a dry run of this algorithm. How does this work? So let's take this input array. We have L is 0 and R is 4. So our function begins its execution from here. So R is greater than L, R is 4, L is 0. So we come inside. When we come inside, we find the middle point. Our middle point is 2 after doing this computation. Now we come here. So our main function, which was called from 0 to 4, is now here. And what it does here, it makes a recursive call. It makes a recursive call for 0 to 2, low to M. 10, 5, 30. Now recursive call function begins with L equal to 0 and R equal to 2, right? Your new values are 0 and 2 in the recursive call. This is 0 and this is 2. So this recursive call also goes inside this if condition because R is greater than L. And what it does, it finds the M, and what is M? M is 1, Right? Here M is 1. Right? It does 0, it considers L as 0 and R as 2 and finds the midpoint. After finding the midpoint, this function also calls merge sort from L to M, which is 0 to 1. L is equal to 0, R is equal to 1 for this particular left call. And this function now begins its execution, and this will begin its execution from the same point. And it checks R is greater than L. So it will find the midpoint. What is the midpoint now? 0 plus 1 minus 0 by 2, which is 0. So you will get the midpoint as 0. So it again makes a call for merge sort with single element. L is 0 and R is also 0. Single element 10. So when this call is made, this also begins its execution from this point. And what happens in this call? It does not go inside this if condition because R is not greater than L. So it stops here, right? So this function call simply finishes and gives the control back to its parent call. So now the control comes to this function call with L equal to 0 and R equal to 1. It was waiting for this to finish. It has finished because it didn't go inside this condition. It calls the other thing. So this parent call now makes a call for M plus 1 to R. So L is now M plus 1, which is 1. R is 1 and 5. So this call is made here for L equal to 0 and R is equal to 1 function call. And when you call this, a new function call begins from here. And R is not greater than L. So this call will simply not go inside this if condition. It will simply return the control back to the parent because this is over. So now the control comes here to the parent call with L equal to 0 and R equal to 1. So what does parent do? Parent was waiting for this. This was finished here. It was then waiting for this. This was finished here. So parent call now comes here. Merge LMR. So what it is going to do? It is going to call merge for this subarray and this subarray. LMR, which means 0, 0, 1. It's going to make a merge call with 0, 0, 1. Right? And what merge is going to do? It's going to merge this with this. So this is greater. So when merge happens, this will become 5. Right? It will become 5. And this will become 10. Right? So these two finished their call. They returned the control back to the parent, and parent call came into the merge function and merged these two subarrays. Right? So they merged. After doing the merge, this call L equal to 0 and R equal to 1 is done. It has finished its work. Now it finishes, so control comes back to the parent. Now parent call which was waiting here, right, to finish the left call to be over, now it makes a call to the right child, the other recursive call, right? So it makes a recursive call for M plus 1 to R. M is 1, M plus 1 is 2. So your L is 2 and R is 2, which is 30. So this call begins now, and when this call begins, what happens? It checks for this condition. R is not greater than L. So this call simply finishes, it's over, and it gives the control back to the parent. And for parent, L is 0 and R is 2 and M is 1. So for parent, this call is over, this call is over. Now what will parent call do? It will come inside this merge function. It will come inside this merge function, and inside this merge function, what it will do? It will merge the elements from L to M, which means 0 to 1, and then M plus 1 to R, which means 2 to 2. So it will merge these two subarrays. So when these are merged, what will you get? What will merge function do? It will simply bring them together in a sorted way. So you will get 5 and 10 and 30, right, when these two are merged. So this function call, which was called for L equal to 0 and R equal to 2, has done everything. It has made 2 recursive calls and it has called merge as well. And merge has done its work. It has merged these 2 arrays. Now this will give the control back to its parent. And what is the parent of it? Our original function, L equal to 0 and R equal to 4. So what will parent do? The parent was waiting for left call, which is over now. The left call has given control back to the parent. So parent will make this call. And what this call is? This call is for m plus 1 to r. So what is m? What is L? L is 3 and r is 4. Which means you have elements from 15 and 7. So this recursive call is made here by the original function call, right? Because this got control back, because this got finished. So our original function call got the control back. And once it got the control back, it started executing the next line, which is this line. Now what this recursive call do? It will make first recursive call for here, right? First it will find the midpoint and then make recursive call here. What is midpoint for this? 3 plus 4 by 2, which is 3. So it will make 2 recursive calls. L to M, which means 3 to 3, L is 3 and R is 3. And then it will make one more recursive call for M plus 1 to R. So what is M plus 1? 3 plus 1, 4. So L is 4 and R is also 4. 7. And then once these 2 calls are over, this will merge. So it will make it 7, 15. So this write call is also over. Now the control goes back to our original function call. Now what it is going to do? It is going to call merge. It is going to call merge from 0 to 2 and 3 to 4. Please note that the modifications that I have been making, they are done in the same array. So this array which is written here, it is actually modified. It is modified. It has become 5, 10, 30. So this was our input array. After these 2 calls, our input array has been changed to this, right? Now it is calling the merge function. And what merge function will do? It will merge this part and this part. So these 2 parts will be merged, and merging will simply combine them into one sorted array. So your input array is changed to 5, 7, 10, 15 and 30, right? So this is how your input array is sorted. We divided our input array into 2 parts, recursively called merge sort for the left half, then recursively called merge sort for the right half, which means we sorted left half and right half, and then our merge function combined these 2 sorted arrays. Let us now do analysis of merge sort algorithm. I have drawn here a sample recursion tree to get an idea how to compute the time complexity. The idea that we are going to use to compute the time complexity is this. We are going to compute the work done at every level of this recursion tree, and then we are going to do sum of all the work done, right? So we are going to sum all the work done at every level. Here I've taken a sample example. L is 0 and R is 7. You compute the mid is 3. Then you recursively call from 0 to 3, 0 to L to M. Then you call from M plus 1 to R, right? And this further makes calls for L to M, which is 0 to 1, and M plus 1 to R, which is 2 to 3, right? So all these calls happen this way. Now how much work we are doing at every level? In the main function call from 0 to 7, or we can say for n elements in general, what we do is we recursively call from 0 to n by 2, then n by 2 plus 1 to n, right? So this is how we make the recursive calls. And then we merge whatever we get from these 2 recursive calls. So how much merge process takes? It takes theta n time if there are n elements in total to be merged, right? So you're making 2 recursive calls. You will compute their execution time in the next level, But how much work you are doing in this level, apart from making the recursive calls? You do theta n work. So how much work you do in this level? You do theta n work in this recursive call to merge these sorted arrays. These two recursive calls gave you two sorted arrays, and then you merge them in theta n time. Now how much work you are doing in the next level? So this level is going to do theta n by 2 work, right? Because it is of size n by 2. It's going to merge two arrays of size n by 4, n by 4. This level is also going to do theta n by 2 work. So theta n by 2 plus theta n by 2 is theta n. So this level is going to do theta n work. How much work this level is going to do? It's going to merge arrays of n by 8, n by 8, and it's going to form an array of size n by 4. Right? This is also n by 4. This is also n by 4. So this merge will take theta n by 4 time, theta n by 4 time, theta n by 4 time, theta n by 4 time. So this is going to be theta n work. How much time this takes? If you see the last level is going to simply make one recursive call. These all recursive calls are simply going to check this condition and going to get out of this recursion, right? So all of these recursive calls are going to do theta 1, theta 1, theta 1 work. And how many recursive calls we have at the bottom? We have n recursive calls. So it's going to be theta 1 plus 1 plus 1, which is theta n. So we are doing this much work in the sort. We are doing theta n work at every level. Almost same work at every level. Now, can we figure out how many levels are there? So if I know that there are x levels, then my time complexity is going to be x into theta n, right? If the number of levels is x, and if every level I am doing theta n work, then how much total work I am doing? Theta n, theta n, theta n sum x times, right? So which is x into theta n. Now what is x? How many levels we have in this recursion? X is equal to theta log n. If you see this example, n is 8. And how many levels you have? You have log base 2 8 plus 1 levels. Right? These many levels you have. 3 plus 1 4. Right? If you take n equal to 16, then you will have one more level. Right? So if you're multiplying n by 2, your number of levels are being increased by 1. That's why we have log n factor. In case of 16, you will have all these, and then you will have one more subtree of same size, and then one more level. Right? So it's log n. It's growing logarithmically. For 16, you will have 5 levels. For 32, you will have 6 levels. What about if n is not a power of 2? I have taken here an example of 7 elements. How many levels you have? You still have 4 levels. This part is empty, right? You're still doing theta n work at every level. There are 7 elements being merged at every level. So you're still doing theta n work, and you still have 4 levels. So we can say it's ceiling of log 2 7, right? It's ceiling of log 2 7. That much work we are doing. Those many levels are there when n is not a power of 2. So in general, we can say ceiling of log 2n. But in general, it's theta log n, right? All these things can be written as theta log n. Theta ceiling of log 2n can also be written as theta log n. So the number of levels we have is theta log n. So what is the overall time complexity? Theta n log n. So time complexity of merge sort is theta n log n. Let us now analyze auxiliary space requirements. For that, we need to look at the merge function. Merge function that we discussed, it was needing theta and auxiliary space. What it was copying, what it was doing, it was copying the left half into a left array, right half into a right array, and then it was merging them. So merge function has theta n requirement. Now you might wonder, if I have theta n requirement, space requirement at every level, right? Theta n space will be required by here, theta n space by here, theta n by here, theta n by here. Why am I not saying that auxiliary space is theta n log n? Why am I saying that it's big O, theta of n? Please think about for a moment. Theta n space is required by this merge, theta n space by this merge, theta n space by this merge. Why the overall space is not theta n log n. Why is it theta n? The point is, at any movement in RAM, you will need theta n space only, because when you are calling this merge, this gets over and then this merge is called. So the space allocated for this is deallocated, right? When this gets over, space allocated for this is deallocated, and then this recursive call is made. And once these two recursive calls are over, space allocated for them is deallocated, right? That's how merge function works. In fact, you can just create one left and right arrays and can use them in all the recursive calls. You can optimize allocation and deallocation in the merge function when you are implementing merge sort. This is not the only optimization in merge function. There have been many optimizations. In fact, people have come up with a merge sort algorithm that works in big O of 1 auxiliary space. It still has theta n log n time complexity. But those are advanced versions of merge sort. Let's talk about this problem. We are given two sorted arrays. Our task is to print intersection or common elements of both the arrays. Both the arrays might contain duplicates, and if there is an element, for example 10 here, it appears 3 times here and 2 times here, but we should be printing it only once in the output. So for this example array, our output is going to be 3 and then 10, right? Even if it appears multiple times in both the arrays, we are going to print it only once. Then 15 is also common, so our output is going to be 15 also. Let's see this example. Here we have double 1, triple 3, then 4 ones, 3, 5, 7. Our output is going to be 1, 3, and 5, 7 are not common, so we are not going to print 5, 7. We are going to print only common elements. And if you are given two arrays which do not have any common elements, then your output is going to be empty. Now please pause this video and try to think of a solution that takes two arrays as input and prints common elements. Let us first talk about a naive solution to solve the problem. The idea of this naive solution is super simple. We traverse through every element of array A. We look for it in array B. If we find it in array B, then we print that common element and we continue for the next elements. The only things left here are how do we handle duplicates. Let's take a closer look at this implementation of the naive idea. I am taking two arrays as parameters. M is the size of array A, N is the size of array B. So we traverse through array A. For every element AI, right, we first check if it is same as previous element or not. So we are comparing with AI minus 1. This is done to avoid printing duplicates. So if you are traversing through this array, when you come to this 20, right, you have already processed this 20 and it was there in this second array, you must have printed it. So you don't want to print it again. That's why we have this condition. And since we are accessing negative index, we need to ensure, since we are accessing I minus 1, we need to ensure I is greater than 0, right? Otherwise, if you access this for I equal to 0, you will be having problems, right? Now, once after checking for this thing, we look for AI in array B. As soon as we find it in array B, we print it and we break the loop, right? Again to avoid duplicates, right? Because this for example is present at multiple places. We want to print only one occurrence. So this is the idea, and time complexity of the solution is clearly upper bounded by n into m, right? You are running a loop m times here, big O of m times here, and big O of n times this loop is running here. In fact, the outer loop is running theta m time and inner loop is running big O of n time, right? It's always run n times, and this might not run n times every time, right? So that's why we have used big O notation. Theta of m into big O of n is big O of n into m, or big O of m into n. Here is dry run of this naive approach. When you run for I equal to 0, which means you are looking for element 1, you search for it in array B, you don't find it, you go for 0, 1, 2, 3, this loop runs for 0, 1, 2, 3, don't find it. Then you run for 1, you search for it in array B, you find it at index 1, so you print it here and you break the loop. Then you run for 2, right? And when you run for 2, you go into this if condition and you skip this element. We're using continuous syntax. When you come to 40, you don't find it, you run for 0, 1, 2, 3. When you come to 60, you don't find it, you run for 0, 1, 2, 3. Now please pause this video and try to think of a solution that works in time complexity better than this. Let us now talk about idea for the efficient solution. We are going to use the idea of merge function of merge sort. We are going to initialize I and j as zeros, then we are going to compare ai with bj, right? And merge function is also theta m plus n, and we are going to solve it in the same time. And since we only need to print the output here, we don't need auxiliary space also. It's going to be simpler than merge function. So we traverse through array A, right? Simultaneously we traverse through array B and we compare AI with BJ. And there are three cases that would arise, right? AI is smaller than BJ, AI is greater than BJ, and AI and BJ are same. Let's understand three cases in this example. We compare 2 and 10 first. I is 0 and J is 0 initially. I is smaller. So what we do in merge sort, we go ahead because this element cannot match with any of the upcoming elements. It's smaller than the first element itself, and both the arrays are sorted. Please note that this implementation or this solution is actually using the fact that both the arrays are sorted. The previous solution that we wrote, it would work for any type of array, sorted or unsorted. Here we are actually using the fact. So if 2 is smaller, we move ahead in this array. We compare 20 and 10 now. Now 10 is smaller, so we'll move ahead in this array. Now 20, 20, they are same, so we'll print it. Now how do we handle the duplicates? We can use the same idea as we discussed in the naive solution. If AI is same as AI minus 1 and I is greater than 0, then we'll simply do I plus plus. That's the condition we'll put at the top, right? So this is the condition we'll put at the top before putting any condition. If I is greater than 0, right, and AI is equal to AI minus 1, then what are we going to do? We are going to do I plus plus, right, and we are going to continue the loop. We don't need to check for other things, because if this element was present in array B, this must have been processed already. Now after doing this check and then these three checks, we will be able to print all the intersection elements or common elements. Now please pause this video and try to fill the conditions here and try to write down the complete code yourself. So here are the things we will write in these conditions. If AI is smaller, we'll do I plus plus. If BJ is smaller, then we'll do J plus plus. If they are same, then we'll print AI or BJ. They are same, you can print any of them. And we'll do I plus plus and J plus plus. Now please pause this video and write the complete code yourself. Here is implementation of the efficient approach. We have I and J initialized as 0. We are running a merge type of loop, I is smaller than M and J is smaller than N. Inside this loop, we have the same condition as the naive solution. If I is greater than 0 and array I is I minus 1, if it is same as the previous element, we do I plus plus and continue. And these three conditions I just discussed. If AI is smaller, do I plus plus. If BJ is smaller, do J plus plus. If they are same, then print the current element. In Java, you can use system.out.print and increment both I and J. So let's take a look at this example and let's see the try run. Initially, I and J both are 0, right? Now we compare 10 and 2. 2 is smaller, so we do J plus plus. We get inside this loop, right? And we make J equal to 1. Now when J becomes 1, we compare 10 and 20. And this time 10 is smaller, so we do I plus plus and we make I equal to 1. Now I is 1 and J is 1. In the third iteration, we'll enter inside this if condition, right? Because both are same, AI and AJ are same, so we'll print 20 on the screen and we'll increment both. So I and J, they both now become 2, right? But this condition will save us from printing duplicates. In the iteration, when I and J both are 2, what will happen? We'll enter inside this if condition. And what this condition will do, it will make I equal to next element, which is next index, which is 3, right? Now I becomes 3, so we are going to compare 40 and 20, right, in the next iteration. And 20 is smaller, so we'll make J equal to 3. Now we'll compare again 20 and 40, this 20 this time, and 20 is smaller, so we'll make J equal to 4. And what happens now, J crosses the size, right? J crosses the maximum index. J now actually becomes the size. So we come out of the while loop. If any of them become equal to the size, we need to come out of the loop, and we have printed 20 on the screen. So this is how the solution, this efficient solution works. Let us talk about this problem. We are given two sorted arrays. We need to print union of these two sorted arrays. Our output should also be sorted. Every element should be printed in the sorted order. Now what do we mean by union? We need to print every element which is present in both the arrays, all the elements of array 1 and all the elements of array 2. And we need to print every element exactly once. For example, here 2 is the smallest element, then we print 2, 3, next is smallest 5, 8. 8 is there in both of the arrays, but we print it once. 9, 10, 15, we print these elements also. Let's see this example. 2, then 3 times, then 4 2 times, and then 4 2 times here. So 2, 3, 4, right? These are the 3 distinct elements present in both the arrays. So our output is 2, 3, 4. Now please pause this video, try to write down a function that takes 2 arrays as input, A and B, and prints union of both the arrays. Let's first talk about a naive solution to solve the problem. The time complexity of this naive solution is going to be m plus n into log of m plus n. M is the size of first array and n is the size of second array. And you might have guessed it, we are going to use sorting here. So what we do first, we create an array C. So this is C++ syntax. In Java you can create an array of size m plus n this way. Also, if you're programming in Java, you don't need to pass the lengths as separate parameters. You can get m as a.length and n as b.length. After creating the array, we copy the elements of array A into array C. After copying the elements of array A, we copy the elements of array B starting from index m, right? I goes from 0 to n minus 1, so we begin with index m. So we basically first copy the first 3 elements, m is 3 here for array A into C. Then we copy the 4 elements of array B into C. So our C has all the elements of array A, then all the elements of array B. After doing this copying, we sort the array C. After you sort the array C, what happens? Your C array becomes 5, 10, 20, all the same elements, they come together, right? See, we want to print the union and that too in the sorted form, right? So, and we don't want to print any duplicates. So we got the sorted form, we got all the elements, we now just need to remove the duplicates while printing. Now we simply traverse the array C, and while traversing, we see if the current element I is not same as previous element, then only we print the current element. See, for sorting, this is C++ syntax, this is how we sort in Java, and for printing, we'll use system.out.print in Java. So that's the simple idea. That's what we are going to get as an output. We have the time complexity this much because of the sort step. This is theta m, this is theta n, this is theta m plus n, but this is m plus n into log m plus n. Also, the solution requires theta of m plus n auxiliary space. Now, please pause this video and try to think of a solution that works in theta m plus n time. Let us now talk about the idea for efficient solution. What we are going to do is, we are going to follow the process similar to merge function of merge sort. We are going to traverse both the arrays simultaneously, array A using index I and array B index using index j. And what are we going to do? Like merge sort, we are going to compare A, I and Vj. For example, if I begin from index 0, 0 in both, and if this is smaller, see, we need to print the union in sorted order. Then what you will do? You will simply print AI and you will move ahead in array A. So if AI is smaller, then what are we going to do? We are going to print AI, right? And we are going to move ahead in this A array. We are going to do I++, right? And if so that's how we'll handle 2 and 3. We'll print 2 on the screen, then we'll move ahead. Now we'll compare 10 and 3. So now Bj is smaller, right? I is here and j is here. And when this is smaller, we are going to print Bj and we are going to move ahead in array B. So we are going to print Bj and move ahead in array B, right? J++. That's what we do when they are this way. So we'll print 2 first, then we'll print 3 first. Now we have I here and j here. Now I is smaller, so we'll print 10 and move ahead here. Now we have I here and j here, 20, 20, they are same. So what should we do in this case? See, when they are same, we are going to print one of those 2 elements, right? Any of those 2 elements and move ahead in both the arrays. So we are going to print AI or Bj, you can print anything, that's same. So print AI and move ahead in both I++, j++. So what will happen now? We'll print 20, right? Because we have printed AI, and we'll move ahead in both the arrays. So we will come to 20 and 40. See, now we need to ensure that 20 is not printed again, right? For that purpose, we need to add some extra conditions. The conditions that we are going to add is, if AI is equal to AI minus 1, then we need to simply move ahead and continue, right? Because we have processed the same element already, right? So we do I plus plus and we continue. And same thing we need to do for bj, right? If bj is equal to bj minus 1, then also we are going to do the same thing, right? J plus plus and continue. Also, we need to add a condition that we should check for this only when I is greater than 0. If I is 0, we should not be accessing minus 1. Here also we need to add a condition j is greater than 0. So this is how we are going to write the logic, right? So this 20 will not be processed. It will be falling into this condition and it will be ignored, right? So we reach the end of this array. Now what are we going to do? See, once we reach end of any of the arrays, we need to process the remaining elements of the other array. Same thing we do in the merge function of the merge sort, right? When we finish processing one array, we process the remaining elements of the other array. So now we are going to come to this array and we are going to process 40 and we are going to print 40 on the screen. So now you have complete idea about the solution. Please pause this video and try to write down the complete code yourself. Here is implementation of the idea that we have just discussed. If you take a closer look at this implementation, this is very similar to merge function of merge sort. We have initialized I as 0, j as 0, then we have loop I smaller than m, j smaller than n, and these three conditions are also very similar to merge function. If ai is smaller, then we process ai and we do move ahead in the a array. If bj is smaller, we process bj and move ahead in b array. If they are same, then we print ai here and we move ahead I plus plus and j plus plus. We are only printing ai because we don't want to print duplicates as per the question requirements. And these two conditions extra that we have added, they are also for handling duplicates. If there exists a previous element and if the current element is same as the previous element, then we simply ignore this element. Continue means simply ignore it and move ahead. And same is the case for array B, right? If the current element is same as the previous, ignore it. After we come out of the loop, we have two more while loops like we have in merge function of merge sort, right? If there are elements left in the first array, then process them. If there are elements left in the second array, process them. And again, before processing them, we need to ensure for every element that this is not same as the previous element, right? So let's do a try run of this for this example. We have array as this, b as this, I is 0 and j also is 0. In the first iteration, right, what will happen? These two elements will be compared, right? We'll not go inside here because I is 0 and j is also 0. So we'll print 2 on the screen and then we'll make I equal to 1. So now we are here and here. Now we'll compare these two and we'll print 3 on the screen and we are here and here. Now we'll print 10 on the screen, right? And we'll move ahead in this. Now we are here and here. Now 20, 20 same. So we'll come here and we'll print 20 on the screen and we'll move ahead in both the arrays, right? Now we'll compare now when we move ahead in both the arrays, we'll not be comparing because now we'll fall here. This 20 is same as the previous 20. So we are going to simply ignore it and move ahead in this array. That's why I've simply written I equal to 4 now. Now once your I becomes 4 and you check for these conditions, this condition becomes false because m here is 4 and I becomes equal to m. So we'll come out of this loop. After we'll come out of this loop, we'll check if I is smaller than m. Do we have elements left in first array? No. Now, do we have elements left in the second array? Yes, because last time j was 2 and we have size is 3, right? So we'll go inside this loop and we'll do an iteration and we'll print 40 in the screen. And before printing 40, we need to ensure that 40 is not same as the previous element. So we have added this condition both the while loops. And it's always true that both of the while loops will never execute. You will either have extra elements in first array or in the second array. Now, what is the time complexity of the solution? See, either we do increment of I or we do increment of j, and sometimes we do increment of both I and j. And I ranges from 0 to m minus 1, j ranges from 0 to n minus 1. So the time complexity is clearly upper bounded by m plus n. And extra elements also are to be processed that also come under m plus n because together the total number of elements are m plus n only. So the time taken is clearly big O of m plus n, and auxiliary space is, you can guess, it's big O of 1, right? Because we are simply printing the elements, we are not storing anything. So auxiliary space is big O of 1. So we have much better solution using merge function. In this video, we are going to talk about this problem, count inversions in an array. Let us first define what is an inversion. A pair array I and array j is called an inversion if I is smaller than j and array I is greater than j. It means a greater element appears before a smaller element. If that happens, then we call these two elements as inversion. Let's see this example. We have an array 2, 4, 1, 3, 5 and we need to count how many inversions this array has. So one inversion in this array is 4, 1, right? One pair is 4, 1. Other inversion is 4, 3. One more inversion in this array is 2, 1. So there are 3 inversions in this array. Let's see this array. When you have an array sorted in increasing order, the number of inversions are always 0. Let's see this array. When you have an array sorted in decreasing order, the numbers of inversions are always maximum possible. In this array, we have 6 inversions. You can notice that the first element forms 3 inversions. The second element forms 2 inversions. The first element forms 3 inversions with 30, 20, 10, all of them. 40, 30 is an inversion. 40, 20 is an inversion. 40, 10 is an inversion. Similarly, second element forms inversion with these two elements. 30, 20 is an inversion. 30, 10 is an inversion. And 20 forms an inversion with this element. 20, 10 is an inversion. So in general, if your array is sorted in decreasing order, then your first element is going to form n minus 1 inversions. The second element is going to form n minus 2 inversions. And the last element is going to form 1 inversion. And the total number of inversions is going to be n into n minus 1 by 2. In general, when your array is sorted in decreasing order. Now, please pause this video and try to write down a function that takes an array as an argument and returns count of inversions in the array. Let us now talk about the naive solution to solve this problem. The idea is to traverse through all the elements starting from first element to second last element. For every element, we count how many elements are there on right side of it which are smaller than this element, right? And that's how we count inversions, where this particular element is the greater part of the inversion. Let's consider this array for an example. We are going to begin from the first element and are going to go on till the second last element. We are going till the second last element because for last element, there won't be anything on the right side of it, right? And we need to count how many elements are there on the right side, which is smaller than this element. So we begin with 2. We count how many elements are smaller. We get the count as 1, right? And this is counted by this loop. Now we come to 4. We count how many elements are smaller. We get count as 2. So our result becomes 3. Now we come to 1. We count how many elements are smaller. There are 0 elements. So our result remains 3. We come to 3. We count how many elements are smaller. There is no element which is smaller. So our result remains 3. And at the end, we return the result. Now what is the time complexity of it? We have nested loops. The outer loop runs from 0 to n minus 2 and the inner loop runs from I plus 1 to n. So it's clearly big O of n square. Let us now talk about an efficient solution to count inversions in an array. The idea is based on merge sort. We divide the array into 2 halves. We sort these 2 halves recursively and then we merge these 2 halves. We do exactly what merge sort does. But with this merge sort operation, we also count inversions while we are sorting the array. We count inversions in the left half, we count inversions in the right half, and then when we are merging, we count inversions where one element is from the left half and the other element is from the right half. Let's understand this approach. Say you have an array from elements L to R. L is the starting index and R is the ending index. You compute the midpoint like you do in merge sort, L plus R by 2. After you compute the midpoint, every inversion which is there in this whole array can have 3 possibilities. So here we are considering inversion x, y such that x is greater than y. The first possibility is both x and y lie in the first half. So this is the first half and this is the second half. So both x and y lie in the first half. That's one possibility. The second possibility is both x and y lie in the second half. And third possibility is x lie in the first half and y lie in the second half. Please note that it will be an inversion only when x lies in the first half, because x is a greater element, right? So that's why we have only 3 possibilities. Now please pause this video and try to write down a merge sort based function that counts inversions in the array. Here is basic idea for the recursive function. We compute the midpoint. We recursively call count inversion for left half from L to M. Then we recursively call count inversion from M plus 1 to R. These two functions not only count inversions, they also sort left and right halves. And we'll soon discuss what is the advantage of sorting while you are counting inversions. We'll discuss this when we will discuss this count and merge function in detail. That's a key function here. It merges two sorted arrays and it also counts inversion such that one element is in the left half and the other element is in the right half. This is also done by count and merge. So what are we doing here in this basic function skeleton? We are simply counting inversion in the left half, counting inversion in the right half, and we are counting inversions while we merge these two parts, right? And at the end, we simply returning the result. Now please pause this video and try to write down count and merge function. Also think of a reason how sorting left half and right half and then sorting the whole array helps us in efficiently counting inversions when we are merging the two sorted halves. Let us now talk about count and merge function. This function is very similar to merge function of merge sort. In fact, almost all the code is same except these few differences. Result is a variable which is used here, which is initialized as 0. This is where we update the result and this is where we return the result. Since we are returning an integer value, our return type is also different. It's instead of void, it's now int. These are the only changes. Otherwise, it's similar to merge function. We create two temporary arrays left and right. We copy the elements from L to M into left array. We copy the elements from M plus 1 to R into the right array. And then we begin this loop where we compare which element is smaller, left I or right j. If left I is smaller, we put left I in array k. Right? If right j is smaller, then we put right j into array k and we do j plus plus here, we do I plus plus here. In this case, when right element is smaller, we also update the result, right? That's what we are doing extra here. After that, this is again same as merge. If there are extra elements in the first array, you simply put those elements into array k and increment the corresponding indexes. If there are extra elements in the second array, you put those elements in the array k and increment the corresponding indexes. At the end, you simply return the result. Let's now see what happens with these lines. What is the significance of this particular line with this example? So let's do this one by one. We begin with I equal to 0 and j equal to 0 and k equal to L at this point. We compare array I and array j. Here array I is smaller, right? So we put array I here in array k, right? And move I to the next point. And when array I is smaller or same, when we are in this case, we do not update the result, right? We do update the result when we are in the other case. Let's now see what happens in this line. What is the significance of this particular expression? Let's understand this with an example. So we have, say, left array as this array and right array is this array. Left half is also sorted and right half is also sorted. N1 is 4, N2 is also 4. Number of elements in the left array and right array. And this is our original array ARR, right? And we are going to merge these one by one and going to write the elements in this array. So our I begins with 0 for the left array. Our j also begins with 0 for the right array. Our k begins with the first index of this array, right? Which is initialized as L here. Now we compare left I with array right j. So we compare 2 and 3 and we fall into this case, left I is more than equal to right of j. So what are we going to do? We are going to copy this element 2 here in our original array and we are going to move I hat here at this point. So I moves here at this point and now we also going to move k here at the next point. After that we run this iteration again and compare left I with right j, right? We compare 5 and 3 and this time right j is smaller, right? So you fall into this else case and this time you are going to update the result. So what do? You simply copy write j into the array. So you copy 3 here, right? And you move ahead next in this particular array, right? So your j now is here. And what else you do is you update result equal to result plus n1 minus I. So what is your new result? Result equal to 0 plus, what is n1? n1 is 4 minus I. What is I? I is 1 here. So your result becomes 3. Now what is the significance of this particular line? See, you found an element in the right array which was 3, and this element was smaller than this element 5. So this element is going to be smaller than all the elements after this index I. It's going to be smaller than this, it's going to be smaller than this. So it's going to be smaller than 3 elements in the left array. What it means is it's going to form an inversion with all the 3 elements. 5, 3 is an inversion, 8, 3 is an inversion, 11, 3 is an inversion. So we have 3 inversions because of this element being smaller. And that's the significance of this line. That's why we add n1 minus I. If we find an element in the right array which is smaller, then it's going to be smaller than all the elements from I to n1 minus I. So we add this expression to count the inversions found by right j and all the elements from left I to left n minus 1. Okay, so we again compare 5 and 6. And this time we find left is smaller, so we are not going to update the result, we are simply going to copy 5 here. Our I moves here. This time we again compare left I and right j, and we found that left I is greater than right j. Right? So what are we going to do? We are again going to update the result. So we are going to update the result as 3 plus n1 minus I. What is n1? n1 is 4, and what is I? I is right now 2. 4 minus 2, which is 3 plus 2, which is 5. And you can notice that this element forms inversion with 2 elements, and that's how we have added 2 here. And here you can notice also an advantage of sorting. What is the advantage we are getting with the sorted arrays? Whenever we see an element from the left array which is greater than an element on the right array, we are counting many inversions together in one go. Imagine arrays of size thousands each. So your total arrays of size 2000 and left and right are 1000 each. And in one go, you might count hundreds of inversions, because if this element is smaller, this is going to form an inversion with all the other elements in the left array. That's the advantage we are getting with the sorted arrays. Please note that with inversion count increment, we must also move this j here, right? J must move here, and we must copy 6 here at this particular position in the array. Now we are again going to compare left I and right j, and we find that left I is smaller. So we do not update the result, we simply copy it here and move ahead in the left array. Now we again compare left and right, and this time left is greater. So this 9 is going to form inversion with 1 element only. We can find it out also. Result equal to 5 plus, what is n1? n1 is 4, and what is I right now? I is 3. So we have only 1. So we have 6 as result now. And what are we going to do? We are going to put 9 here in the result array, and we are going to increment this here. And now again we are going to compare left I and right j. And this time left I is smaller, so we are simply going to put left I. And at this point, you come out of this loop because you have traversed all the elements in the left I. And what are you going to do now? You are going to come into this particular loop, going to copy 13 here, right? And at the end, you are going to return the result 6. So you have total 6 inversions such that one element is in the left array and the other element is in the right array. And the other inversions which were there within the left array and within the right array, we must have counted them when we recursively called for the left half and right half. So this is how this inversion count logic works using merge function. Let us now talk about time complexity of the solution. I think you must have guessed. It's simply doing merge sort work. So the time complexity is same as merge sort. It's big O of n log n. And it's just doing constant amount of extra work other than merge sort. So it's going to remain as big O of n log n. And since we are going to use the merge function which requires auxiliary space, we need big O of n auxiliary space to solve this problem. In this video, we are going to talk about partition function of quicksort. We'll first talk about partition function. We will understand it well so that we can quickly understand quicksort. So we are given an array, an unsorted array obviously, and we are given index of an element inside this array. So I'm given this index P as 5, which is index of the last element 7. So the requirement of the partition function is it should partition the array around 7. All the elements before 7 should come before it. All the elements greater than 7 should come after 7. If there are elements which are equal to 7, they should also come before 7. That's the requirement. There can be multiple possible outputs of the partition function. You can have 3, 6, 7, 8, 12, 10. Here all the elements here are smaller than 7. All the elements are greater than 7. But there can be multiple permutations of these elements and these elements. For example, this is a permutation. This is another permutation. So you can have multiple possible outputs and any of those outputs is valid. So your partition algorithm can either change this array to this or any other array where 7 is at its correct place and all the elements before 7 are smaller and all the elements after it are greater than 7. Please pause this video and try to think of a solution that partitions the array around a given element. You may think of different solutions. We'll talk about 3 solutions of this problem. One is naive solution. Then there is an algorithm called Lomuto Partition. Then there is another algorithm called Hoare's Partition. We'll talk about these 3 algorithms one by one. Let us now talk about naive solution to partition the array around a given pivot. Let's take a look at this example. We are given this array where low points to this element, low is 0 and high points to the last element. And we are also given the partition point as last element. So indexes are from 0 to 6, 0, 1, 2, 3, 4, 5, 6. So P and H both are 6, both are last elements. So L and H represent the whole array and this element represents the element around which you want to partition. So what do you want as an output? You want to put all the elements which are smaller than or equal to 8 on the left side and all the greater elements on the right side. So your output should be 5, 6, 8 and then 9, 12, 11 and 13. These elements can come in any order. These elements can come in any order, but they should come before 8 and they should go after 8. Let's see how does this work. How does this partition function, naive function work that we have written here. So what does this function do? It creates an array of size temp which can hold all the input elements. How many input elements are there? L is 0, H is 6. So you will have 6 minus 0 plus 1, 7 elements. So you create an array of size 7. First, you copy all the smaller or equal to elements into this temp array. So after this step, what will happen? Your temp array will contain 5, 6 and 8. We traverse through the input array. For every element, we compare it with the pivot element or the element around which we want to partition. If it is small or equal to, we put it in the temporary array and we increment the index, right? So we have 5, 6, 8 after this step. Now in this step, we put all the greater elements. So we have 13, 9, 12, 11, 9, 12, 11. And you can see that our temporary array has the partitioned array. It has all the elements which are smaller than or equal to 8 on the left, all the greater elements on the right. So what all we need to do now is copy this temporary array back to our original array. So we copy these elements back to our original array and our original array becomes a copy of temp, which is 5, 6, 8, 13, 9, 12, 11. So this is a naive way of partitioning. It requires 3 traversals and also requires big O of n extra space. So auxiliary space requirement by this is big O of n and time is big O of n. but it is like doing 3 traversals of our input array. So can you solve this problem with big O of 1 extra space? In this video, we are going to talk about Lomuto partition that works by traversing input array exactly once and requires constant extra space. Let us understand Lomuto partition. How does this work? Let's take a look at this array. We have been given low index and high index. Also, in the previous video, I considered that pivot is given as an input, right? We were taking P as an input. Here, we are going to assume pivot always as last element, right? In this partition. We'll talk about a solution, a modification to this code when pivot is not the last element. But for simplicity, we are going to assume that pivot is always last element. Always last. We are not taking it as an input, right? To simply understand the algorithm. Then we'll later talk about how to handle if P is an input to us, the pivot is an input to us, or index of the pivot is an input to us, and you want to partition around a random element in the array. The idea of this algorithm is to traverse the input array from low to high, L to H minus 1, right? Your array H is always pivot. That's what we have assumed in the beginning, right? Array H is always pivot. So we traverse from left to right till H minus 1 because last element is pivot. We do not have to worry about that for now. We handle that at the end. We put it at the end at its correct position. While we are traversing, we ensure few things. We ensure this, that the element from 0 to I are smaller than pivot. Elements from I plus 1 to j minus 1 are greater than or equal to pivot. So when we are at jth index, we are sure about these things. We maintain this loop invariability that elements from 0 to I are smaller and these elements are greater than or equal to. How do we ensure that? The idea is simple. You traverse the input array from left to right. If you see a smaller element here, right? A smaller element here. What do? You know that I plus 1th element must be greater. We'll talk about corner cases later though, if there are no greater elements. You know that I plus 1th element is greater. What do you do? Simply, you swap this element with this element and you increment the window of smaller elements. Let me repeat what I just said. If you see a smaller element, you swap the I plus 1th element from this and you increment the window, right? You increment the window size. Your I, now number of smaller elements become more than 1. So let me write down that case. So if array j is smaller than pivot, we are going to increment this window. What are we going to do? We are going to make it like this. 0 and one more element is included here, right? So this element is included here, right? And now this is our new I and j is moved here to the next element, right? This is our new, so this is our new I and this is I plus 1 and this is j minus 1. That's how we proceed if it is smaller. If it is greater, we do not need to do anything because we anyways want to put greater or equal elements in the window from I plus 1 to j minus 1. So if it is greater, this window does not change, only this window extends by 1, right? So that's the simple idea of Lomuto partition. If you see smaller elements, simply increment the window of smaller elements by 1 by doing this swapping and proceed. Greater elements, you're anyways maintaining the end of greater elements till the previous element. So you just increment the greater element. Basically, you don't do anything because your j changes, right? So you increment the window of greater elements. Let's demonstrate this with this array example. So we initialize I as L minus 1. Our window of smaller elements has nothing as of now, right? This is where our window of smaller elements is right now. Now what do? We traverse from low to high minus 1 and we check if array j is smaller than pivot or not. So what happens here? J is right now here. This array J is smaller than pivot, right? This is our pivot also. So pivot is 70, we've written it here, right? So it's smaller than pivot. So what do? We go inside this if condition, we increment I. We increment the window of smaller elements. I becomes 1, right? And we swap array I with array J. Where is J right now? J is here. Let us do a dry run of this algorithm for this example. We initialize I as -1, L -1, right? So L is 0, so our I is -1. So our initial I is here because we do not know how many smaller elements are here in this array. So we just keep it before the first element. Now we run this loop. And what do? We begin from J equal to L. So our J is 0. J is here right now. And we compare it with pivot. Pivot is 70. So it's smaller than 70. So they go inside this if condition. And what happens when they go inside this condition? They increment I. We increment I and we swap the elements. We increment the window of smaller elements. So I now becomes 0, right? And J is anyway 0. So 10 is actually swapped with itself, right? So when you were here, your initially I was -1 and here J is 0. So I is incremented, I becomes 0 and J remains 0. So the element is swapped with itself. Although you're doing swapping with itself, but your window of smaller or equal elements is increased. So this is now your window of smaller or equal elements. It has one element only because I has now become 0. And J is moved to next position after swapping. So when now J comes here, right? When J comes here, you again compare 80 with the pivot element. Pivot is 70. So when array J is greater, you do not do anything, right? You do something only when this is smaller, right? In greater or equal cases, you do not do anything. So you keep 80 as it is and you move to the next element. So you come to J equal to 2 here, which means 30. So you are currently at 30. You compare 30 with 70. So what happens when you compare 30 and 70? 30 is actually smaller. And what do we do in smaller case? We increment the window of smaller elements. So I now becomes 1 and we swap these two. So 30 and 80 are swapped. So you have 10, 30, 80. So these two elements are swapped by this statement. You increment the window of smaller elements and then you do swapping. And your I becomes 1 now. So your window of smaller elements is this. And your J becomes 3. So your J reaches here. This is window of greater or equal elements. This is window of smaller elements, right? So what will happen when your J is 3? You will see that 40 is smaller than pivot, right? So what you'll do? You will again do swapping. So you will increment the window of smaller elements and you will swap 80 with 40, right? You will do I++ and you will swap 80 and 40. You increment the window of smaller elements and then you do swapping. So your I becomes 1 now. So I is now 1 and J is moved to the next element 3. So we were here at J equal to 2. Now we moved J equal to 3. So our window of smaller elements is 0 and 1, right? This 10 and 30. Window of smaller elements is 10 and 30 here. Here also we have 10 and 30. So J is 3 now and J3 means you are here at 90, right? And what happens when we see a greater element, greater or equal to element, we simply ignore it, right? We do not do anything, simply increment the J. So this is now your new window of greater elements, right? New window of greater elements, simply ignored it. And this is a window of smaller elements. Then you move to next element, J becomes 4 now. So what do you do when J is 4? It's smaller than pivot, right? So 40 is smaller than 70. So what do? You increment the window of smaller elements and then you do swapping. So the window of smaller elements now become 10, 30 and 40 because you have swapped 40 and 80. You increment I, right? And then you do swapping, right? So your I becomes 2 now and your J becomes 5 now, right? You have 3 elements in the smaller window, right? And now you move to the next element, which is 50. I is 50. So what happens? This is again smaller. This is again smaller, and what do? You do increment the window of smaller elements, and then you do swapping. So the window of smaller elements is increased. It becomes 3 now, and you have swapped 50 and 90, right? These two are swapped, right? So 50 comes here and 90 goes there, and this is your new window of smaller elements, and this is your new window of greater elements. After this step, j becomes 6, and your high is also 6. We run a loop from L to high minus 1. So we stop here because it has gone beyond high minus 1. So we stop the loop here, and you can see that all these elements are smaller and all these elements are greater, and your pivot is here. So what do you do at the end? You swap your pivot with the first greater element, right? So you swap 70 and 80. How do you find the first greater element? Using I plus 1. Your I is 3. So when you do I plus 1, you will come here, right? So you swap these two elements at the end. I plus 1 and H. H is your pivot, right? So after swapping, what will you get? You will get 10, 30, 40, 50. You have swapped I plus 1th element with the last element with your pivot. So you will get 70 here and 90 here and then 80 here. So you have pivot at its correct position. You have all the smaller elements on left side, all the greater elements on the right side. So if you want to return the index of pivot, if you want to return where your pivot is after modification, you can return it again as I plus 1. Because this is where pivot is, right? You swapped pivot with the I plus 1th element, and you're sure that I plus 1th element is going to be greater because your window of smaller elements is from 0 to I, and window of greater elements is from I plus 1 to last element. To get a better understanding of Lomuto partition, I strongly recommend that you try these corner cases yourself. I'll give you an idea what happens in the corner cases. So this is a corner case because the pivot element, the last element that we always consider as a pivot here in the algorithm, the pivot element is smaller than all the other elements, right? So do a dry run and see how will your algorithm work, because there is not going to be any window of smaller elements. So what will happen in this case? Your I is initialized as -1 here, if you are considering L as 0, right? And then you will continue doing j plus plus, j plus plus, j plus plus, j plus plus, and you will stop here. I will never change from -1. So the window of greater element is all the elements, right? And window of smaller elements is empty. What do you do at the end? You swap array I plus 1 with the pivot. So what will you do? You will swap 70 and 30. You got the answer right. 30, 60, 80, 40, and then you will get 70. So you have your pivot at correct position, and you have all the greater elements on right of it. And you can find the position of pivot also, right? Using I plus 1 again, right? Using I plus 1, we can get where pivot is. So it works for cases when your pivot element is smallest of all. Let's now talk about what happens when your pivot is greatest of all. Please do a dry run for this particular case also. Let us see what happens. We initialize I as -1. So when we are here, our j is here. We see that array j is smaller than pivot. So we'll do I plus plus, right? And we'll swap array I and j. So we are going to make the window of smaller elements of size 1. I becomes 0, and we are going to swap array I with array j. So j, this element is going to be swapped to itself, right? That's what will happen. Then you will come here, you will increment the window of smaller elements, and you will swap array I with array j. So which means the 40 is going to be swapped with itself again. So the window of smaller elements is going to become this. And you will swap 40 with 40. Now what will happen? You will come here, and it's again smaller. So you will increment the window of smaller elements further. And you will swap 20 with 20. Your I will become 2. What will happen when you come here? You will increment the window of smaller elements, and you will swap array I with array j. So 50 will come here and your array I will become 3, right? So your I at the end is 3, right? This is your window of smaller elements. And at the end, what do? You swap array I plus 1 with pivot. What is array I plus 1? This 80. So you will swap the element, the pivot element with itself. So you have your original array as it is. You just did swap of every element with itself in every iteration. And at the end also, you did the same thing. And you can see that your position of pivot is I plus 1. It's 4. So this way, you could partition even the array, which is all the elements smaller than the given element. So far, in Lomuto partition, we have been assuming that pivot is always the last element. What if I give you an element which is not the last element and I ask you to partition the array around this element? What if your P is an input parameter, index of the pivot element is an input, right? I tell you that partition the array around this element. I tell you the index of P pivot element is 2. What changes you will make to Lomuto partition to handle this? This can be done simply. See, the standard Lomuto partition assumes that pivot is always the last element. You can simply do a swap between this and the pivot, right? So you just need to add this line, swap array P with array H. What will happen after this? Your array will change to 50, 30, 11, 10, 5 and 20. So your 20 moves to the end. Now you can run the standard Lomuto algorithm on this array, right? Your pivot is at the end. You wanted to partition around 20, you will get the partition around 20. In this video, we talked about Lomuto partition. Lomuto partition partitions an array around a pivot in big O of n time. It requires big O of 1 extra space. Also, it does only one traversal of the input array, right? Unlike naive partition, which was doing 3 traversals. So obviously, it is better than the naive partition. There is one more partition algorithm called Hoare's partition algorithm. On average, Hoare's partition algorithm works much better than Lomuto partition. In this video, we are going to talk about Hoare's partition method. Hoare's partition method works much better than Lomuto partition method. And like Lomuto partition, this is also big O of 1 extra space and big O of n time. Also, only one traversal of input array. Let us now understand Hoare's partition. In Lomuto partition, by default, we were considering last element as a pivot. In Lomuto partition, in its typical implementation, we consider first element as a pivot element. So our pivot is first element. So low is here, it's 0, and high is here, it's 1, 2, 3, 4, 5, 6, 7. It's 7. And our pivot is array of low, which is 5. So we need to partition this array around this value of 5. All the elements smaller than 5 should move to the left, and all the elements greater than 5 should move to the right. Greater than or equal to 5 should be on the right side. Let's see how does this work. We begin 2 indexes I and j. I begins with L minus 1. J begins with H plus 1. So I is initially minus 1. L minus 1 means 0 minus 1. J is initially H plus 1. So J is initially 8. We mainly have I here on left of this element and J here on the right of this element, right? J is here. We move I from L minus 1 to this side. We move J from H plus 1 to this side. We stop when they cross each other or they meet each other. After every iteration of this outer loop, we ensure this. The elements from L to I are smaller than pivot, and elements from J to H are greater than pivot. That's the idea of this algorithm. So what do? You begin from this side, you keep on incrementing while elements are greater than pivot, right? So when you begin with j equal to h plus 1, you will come here and you will see that this element is greater than pivot. So you will move ahead. Now you see this element, you will see this is actually smaller than pivot. So you will stop your j here. And you will begin with L minus 1. And you will stop here because this is not smaller than pivot. It's actually pivot itself and not smaller than pivot. So you will stop here. And after stopping, what you will do, you will swap this 1 with this 5, right? So 5 goes there, 1 comes here, right? And you continue this way. You come here, then you again increment I, right? 3 is actually smaller, so you will go to the next element. 8 is actually greater, so you will stop here, your I. Your j will start from here, it is actually greater, so you will continue. You will come here, you will see this is smaller, so you will stop here. Now what you will do? You will swap these two, 8 and 2, right? And now you will increment I. If this is smaller, so you will continue. Now you will come here and stop. Now what you will do? You will decrement j. You will come here and you will stop because this is smaller. Now you will come to this part because I has crossed j. I and j have crossed each other. So you will simply return j. That's the idea of Hoare's partition algorithm. Let us again take a look at this code and let's run this code step by step with this example. So we initialize I as L minus 1 and j as h plus 1. And before that, we have initialized pivot as array low, right? We'll talk about how to handle the situations where we want any other element as a pivot. We'll also talk about corner cases. So we do this. After that, we have an infinitely running loop. And what do we do inside this loop? We first do I++. We have a do while loop. First we do I++, then we compare it with the pivot. So I begins with L minus 1, so it's going to increment for sure in the first go, because after incrementing we do comparison. So this do while is actually useful in the coming steps also. We'll see in this example. Same thing we do for j. We have a do while loop. We first do j minus minus, then we check, right? So I stops at an element where your array I is greater than or equal to pivot, right? So in the first go, it stops at 5 itself. And j stops at an element when your array j is smaller than or equal to pivot. So in the first go, j does not stop here, it stops here, right? After doing these two loops, we check have they crossed each other while moving forward. If they have crossed each other, we simply return j. If they have not crossed each other, then we swap I and j, array I and array j, right? So we have initialized here I as minus 1, L minus 1 and j as 8 because your h is 7. Now what we do? We increment I first, right? And then we check for this condition. So I stops here itself. And same thing we do j for j here. J stops here because this element is smaller. Now what do? We swap these two elements, array I and array j, right? When you swap, your 1 comes here and 5 goes here. So we have swapped these two elements, right? I and j have stopped here. And after swapping, they change their positions and we again begin this loop. After swapping, we again begin from here. And this is where do while is useful. You increment I before checking the condition because currently I is, at an element which is greater than or equal to pivot, right? So you increment I and then you check, right? So you come here, you check, right? It's a smaller, so you continue. Then you come here and then you check. It's greater, so you stop, right? So you stop here at this time. Now you begin with j, right? So what do? You come here, you see it is greater, so you do not stop. You come here, you see this is smaller, so you stop. right? So you stopped at this point. This has stopped, this has stopped. Now you come here and you check whether they have crossed each other or not. They have not crossed each other. So you come here and you swap these two. So your 2 comes here and 8 comes here. Now you move forward I again. You begin the loop again and you move forward in I. So you come here, you see it's actually smaller. So you come here and you stop here, right? You stop at this element. And you move forward in J. So your J is currently here and it will stop here because this is smaller. So J stops here and I stops here. This is where they cross each other. So after these 2 loops are finished, in this iteration they've crossed each other. So you come inside this if condition and you return J. So you return this index J, 3. So what you have after returning, you have all these smaller elements, then 5 on the left side and all the greater elements than 5 on the right side, right? Greater or equal to elements on the right side. So that's what is ensured by Hoare's partition algorithm. So what you have before returning, you have all the elements on the left smaller than all the elements on right. In Hoare's partition, you may have smaller than or equal to elements on the left side, smaller than or equal to pivot, and greater than or equal to elements on the right side, greater than or equal to pivot. After this is ensured, you return this index J, right? And you simply have to recursively call from here to here and then here to here. One thing different from Lomuto partition. In Lomuto partition, we were picking a pivot and we were fixing that pivot at its correct position, right? And then left and right were greater and smaller respectively. In Hoare's partition, you picked the pivot as 5, but 5 is not at its correct position here, right? 5 is not at its correct position here. 5 has gone the right side, right? Ideally 5 should have been just after 4. So this is where Lomuto partition is slightly better. It ensures that your pivot is at its correct place once your partition is done. In Hoare's partition, only this thing is ensured that all the elements till J are smaller than or equal to pivot and all the elements on right of J are greater than or equal to pivot. So this is an interesting point about Hoare's and Lomuto partition. When we implement quicksort, we'll see that in quicksort, when we use Hoare's partition, we pass different parameters in the recursive calls, and when we use Lomuto partition, we pass different parameters in recursive calls of quicksort. Why different parameters? Because Lomuto partition, it fixes, it sorts one element, right? You don't have to sort that particular element. But Hoare's partition, it does not guarantee that. Whatever pivot you have picked, it might not be at its correct position. So you mainly do not fix any particular element in Hoare's partition. But in general, Hoare's partition takes less number of comparisons compared to Lomuto partition and practically works much better than Lomuto partition on average. Let us now talk about some corner cases. How are these cases handled by Hoare's partition? Let's consider this case when your pivot is smallest. In Hoare's partition, you always consider array low as pivot, right? So this is a pivot and this is the smallest of all the 4 elements. So what will happen? You will begin I with -1, you will bring I equal to 0, and then you will check whether array I is more than pivot or not. It's actually equal to pivot. So you will stop here. Your first while loop will break. Your first do while loop will break. You will begin with j equals to 4 here, right? So j will begin from at this position. You will do j minus minus. When will you stop? When array j becomes smaller than or equal to pivot. So you will come here, you will come here, you will come here, you will not stop because all these are greater. Then you will come here and you will stop. So I and j are in the first iteration, I will become 0 and j will also become 0, right? In the first iteration itself. And when I is greater than or equal to 0, you stop, right? And you return j. So you will return 0. So your this list has all the elements which are smaller than this list, right? So your list is partitioned, your array is partitioned into two halves, and you have one list which is smaller, right? And that Hoare's partition works. Let us now talk about this another corner case when your pivot is largest. 12 is pivot here. It's the largest element among all the elements. What you will do? You will initialize I with -1, j is 4, right? Now you will continue incrementing I while array I is smaller than pivot. So you will stop here, right? You will stop at I equal to 0 itself because this is greater than or equal to pivot. This side you will stop here itself because this is smaller than pivot, right? So you stop at these 2 points, you swap these 2 elements, 9 comes here, 12 comes here, and after that you will again iterate in this loop, and in this iteration you will increment I, right? You will come here because it's smaller than pivot, you will come here, it's smaller than pivot, and then you will reach here because it's smaller than pivot, right? So your I stops here, I becomes 3, and j stops here itself because it's smaller than pivot, but they cross each other. So you will return j, which means you will return index of this element. And you can see that elements from L to J are smaller than elements from J plus 1 to H. So you have partitioned the array. Let us now talk about third corner case when all the elements are same. With this corner case, we'll also understand that Hoare's partition is not stable. And that's one of the reasons your quicksort is not stable algorithm by default. So what happens in case of equal elements? Your I is initially -1 and j is 4. So you have do while loops. Both will increment only once. Your I will stop at 0 and j will stop at 3 because we have smaller and equal conditions, smaller and greater conditions in these two loops respectively. So after they are stopped at these 2 points, we swap these 2 elements and we again begin with the next iteration. In the next iteration, your two do while loops will again stop after just incrementing I and j, incrementing I by 1 and decrementing j by 1, right? So it'll stop here and you will again do a swap, right? So after swapping, these 2 elements will be swapped and your I will become 2 and j will become 1. They'll cross each other and you will return j. One important observation, it's not stable because you are swapping equal elements, you're changing their positions. And something similar happens in Lomuto partition also. Lomuto partition is also not stable. But the naive partition that we talked about in the first video, that is stable because you create an auxiliary array and you first copy all the smaller elements. So while copying the smaller elements, you can just copy the smaller equal to elements on the left side, right? So that is stable because they are traversed in the same order and copied in the same order. So your naive partition, although it requires big O of an extra space, it does 3 traversals, but it is stable. That's the advantage this naive partition has over Lomuto partition and Hoare's partitions. Let us introduce quicksort algorithm. Quicksort is a divide and conquer algorithm, which means it first divides your input array or list in 2 parts, then it sorts those 2 parts independently. It's similar to merge sort in that way because merge sort is also divide and conquer. The difference here is in merge sort, the merge process is complex, the division is simply half of division, but in quicksort, the partition process or the division process is complex. We call a function called partition that divides your list into 2 parts, and these 2 parts need not to be of half of size. In merge sort, they are of half of size. The partition function ensures that you have some elements in one half and some other elements in the other half, and then this sorts these 2 parts independently. That's how quicksort works. So in merge sort, merge function is complex. In quicksort, the partition function is complex. That's the key function. Partition function is the key function in quicksort, like merge function is the key function in merge sort. But they both are divide and conquer. The next point is worst case time complexity of quicksort is big O of n square. If you compare it with merge sort has big O of n log n time, even in the worst case, but it is big O of n square. But despite having big O of n square worst case time, this is considered faster than merge sort. The reasons are, it is an in-place algorithm. See, this is arguable. Saying in place is arguable because it requires auxiliary space for the recursion call stack. But when we say in place, we mean here is it does not create auxiliary arrays to partition the array. It does not copy or input data to some auxiliary array. It only uses auxiliary space for recursion call stack. So the partition function of quicksort, if it uses Lomuto or Hoare's partitions, these partition algorithms partition the array in place. They do not need an extra array. So partition is in place. The only extra space you require is only for recursive calls. Since it is an in-place algorithm, it's working on the same array or list, it is cache friendly as well, because you are more likely to have all the items in cache, and that's the reason it is considered faster than merge sort, because merge sort, it creates auxiliary arrays to sort. Average case of quicksort is big O of n log n. Although the worst case is big O of n square, on average it works in big O of n log n time. It's a tail recursive algorithm. See, what is a tail recursive algorithm? If a recursive function does recursive call as the last thing, then this recursive function is called tail recursive. And such functions can be rewritten in such a way that you can remove the recursive call and you can write it as a loop. So in merge sort, if you remember the merge sort, the last thing that was happening was merge function, not the recursive call. In quicksort, when we study quicksort, we see that the last thing that happens in quicksort is a recursive call. So one recursive call can simply be replaced by a loop in Python or go-to statement with Java and C++. So we can replace that one recursive call in quicksort, and many compilers do this optimization automatically. But Python does not do tail call optimization or tail call elimination. We have to do it as a programmer if we are writing the Python tail recursive code. As we've discussed earlier, partition is the key function in quicksort, and we are going to discuss three different approaches for partition. We are first going to talk about naive partition, which is going to be inefficient, but the good thing about naive partition is it is stable. So quicksort is not stable if you use these efficient partition algorithms, but if you want a stable version of quicksort, you can use naive partitioning. These two algorithms are in place, they are faster, they just do one traversal of the array or list and do the partitioning, but naive requires 3 traversals, but it is stable. But in general, if we are using that much work, then quicksort is definitely not as efficient as it is generally talked about, right? So naive partition is generally not used, and that's why the Lomuto and Hoare's partitions are preferred, and among these two, Hoare's is the most efficient, right? Hoare's is the most efficient partition scheme. That's what is used in practice, and with Hoare's partition, you get a fast sorting algorithm, but which is not stable. So many library implementations, they use quicksort when stability is not required. For example, in C++, there are two functions, sort and stable sort. The sort function uses quicksort variation internally. It uses an algorithm called intro sort, which is a hybrid of quicksort, heap sort, and insertion sort, but mainly quicksort based. C library has a function called qsort, right? And qsort, as the name suggests, is a quicksort implementation. Java uses quicksort for primitive data type sorting, right? For primitive types, it uses quicksort, dual pivot quicksort algorithm, a variation of quicksort for sorting purpose. For non-primitive data types, Java uses timsort algorithm, which is also used in Python. And timsort is a variation of merge sort. So Python and Java's non-primitive type sorting, they are based on merge sort. They are stable. But other algorithms like C++ sort, C qsort function, Java primitive type, they use quicksort algorithm variation for sorting purpose. If we compare quicksort with merge sort, see, when you don't need stability, then quicksort is definitely the fastest algorithm. Quicksort or its variations, the intro sort version, they are the fastest variations which are actually used in libraries also. But if you need stability also, then merge sort is preferred. Let us now understand algorithm. We are going to consider Lomuto partition to understand this algorithm. The algorithm changes when we use Hoare's partition. So in this video, I am going to first consider Lomuto partition, and at the end, I'll talk about the changes that we need to make in this algorithm if we use Hoare's partition. It is strongly recommended that you see that Lomuto partition video first. Let's do a recap of Lomuto partition. What Lomuto partition does, you give it an array, it takes the last element, puts this last element at its correct position. Then it returns that position. So when I say it puts that element at its correct position, what it means is all the elements on left of it are smaller than equal to this element, and all the elements on right of it are greater than equal to this element. And this element is at its correct position where it should be in the sorted array. So if you take a look at this example, what Lomuto partition will do with this array? It will put 5 at the third position because there are two elements which are smaller than 5. So it will put 4, 3 at first two positions in any order, and it will put all the greater elements on right of 5 in any order. But it will ensure that 5 is at correct position, and it will also ensure that all the elements on left of 5 are smaller or equal, and all the elements on right of 5 are greater or equal. Lomuto partition, after putting the element at its correct position, returns you index of this position. So what Lomuto partition will do is, it will put 5 at its correct position in sorted array. Where should 5 be in the sorted array? At index 2, because there are two elements before it, which should go at 0 and 1. So it will put 5 at index 2 and 3 and 4 at index 0 and 1, right? They can appear in any order. All the elements which are greater than 5, 8, 7, 9, 10, they'll go at these 4 indexes. They can go in any order. So you have all the elements smaller here, all the elements greater here, and 5 is fixed. Now if you individually sort these two elements and individually sort these 4 elements, you do not need to do anything more. Once you have sorted these two, you will get 3, 4 here. Your 5 is anyways here. And once you sort these 4, you will have 7, 8, 9, 10 here. Your whole array is sorted, right? That's what quicksort does. It calls Lomuto partition here, right? What Lomuto partition does, it does this. Puts 5 at its correct position, puts a smaller element on left, puts greater elements on right. And we already talked about code of Lomuto partition, working of Lomuto partition. Now what all quicksort does after it? It calls itself from L to P minus 1. So P is the index returned by Lomuto partition. What Lomuto partition will return here? It will return 2 here, right? So P will become 2 here, right? So you get this index. Now what do? You call quicksort again from 0 to 1, which means you sort 3 and 4, right? Then you call quicksort again for 3 to, what is H here? H is 6, from 3 to 6, which means you have sorted 7, 8, 9, 10, right? So once this part is sorted of the array, this part is sorted, your whole array is sorted because this part is anyways at its correct position. So that's the idea of quicksort with Lomuto partition. Let us now do a step-by-step run of quicksort algorithm. Say we have this array. Indexes are 0, 1, 2, 3, 4, 5, 6. Your L value initially passed as 0. So L is 0. And H value is last index 6. We want to sort the whole array. This condition in quicksort says that if there is one element, do not sort it, right? Or if H crosses L, then also do not do any recursive calls, do not do anything, right? Because there is no point in sorting one element, it's already sorted. So what do? We first check for this condition. This condition is satisfied because L is 0, H is 6, we come here. And we call the Lomuto partition function here, right? So I've shown the step here. QS, I've written the short for quicksort. L is 0 and H is 6 initially. So this is our L and this is our H in the initial call. And this is our original array, right? Copy the same array here, right? So first thing happens is partitioning. And what partition does, it changes this array to 4, 3, because it has to put 5 at its correct position. So it puts 5 at its correct position and then it has 9, 8, 10, 7. How do we get these values? 9, 8, 10, 7. For this, please refer the Lomuto partition video. We have explained this part in detail there, right? So Lomuto partition puts 5 at its correct position, puts 4 and 3 here, 9, 8, 10, 7 here. These 4 and 3 or 3, 4, this particular order can be anything, but if you run the Lomuto partition algorithm that we discussed in the video of Lomuto partition, you will get 4, 3 and 9, 8, 10, 7. And what this partition will return? It will return index 2. So P is 2 here. Now what do we do after it? Once our partition function is over, which has done this work, we call quicksort from L to P minus 1. So we call qsort L to P minus 1, means 0 to 1, which means we call for this subarray. So when you call for this subarray, what are L and H? L is 0 and H is 1, right? So your execution begins from here again. L is smaller than H, so you come inside. And when you come inside, what do you call? You call partition. So you are going to call partition for this subarray, Lomuto partition for this subarray, with L equal to 0 and H equal to 1. What Lomuto partition will do? It will consider last element as a pivot, right? And it will put this element at its correct position and will return the index of it. So what it changes it will make to the array? It will make this subarray as 3, 4. Because the last element was 3, it has to put it at its correct position, which is 0. And next element at next position, there is only one element after it, so that element goes to the next position. And what will partition return? It will return 0, because this is where it has put the element 3. So when it returns 0, your quicksort comes here after calling the partition function, and it will call itself from L to P minus 1. What is P? P is 0. What is L? L is also 0. So it will call for 0 to minus 1, P minus 1. This will again cause a call to quicksort, and this time L is not smaller than H. L is actually greater than H. So your quicksort function call will get over immediately, right? And the control will come back to this call, because this call had called the partition function, then called this, and it was waiting for this to finish. Now this is finished, this call will come here and it will call P plus 1, right? 0 plus 1. So you call for 1, 1. When you call for 1, 1, you have only one element, right? So L is not smaller than H. It would not make any change. So your array remains 3, 4. Your left part remains 3, 4. And it gives the control back to its caller, right? And its caller has finished, so it will give the control back to the main caller. And main caller has finished the left part, right? So main caller has had called the partition, right? Got the partition index 2. It has already called for the left, and left part is done. Now the main function call, which was there for 0 to 6, it will make call for P plus 1 to R, this particular P plus 1 to H, this particular call, right? What is P plus 1? P plus 1 is 3. So it will call from 3 to 6, right? Which means it will call for 9, 8, 10, 7. So when you call for this, you again make a call for quick sort. L is smaller than H. What is L here? L is 3 and H is 6, right? So you come inside and you call partition for this subarray. Now if you call Lomuto partition for this subarray, Lomuto partition will consider the last element as pivot, right? 7 is considered as pivot in the default implementation, and it will move all the greater elements on right side. So your Lomuto partition changes this array to 7, 8, 10, 9. And how do we get this array? You can refer the Lomuto partition video for this. How does it work? But the main idea is it's going to put the pivot element at its correct position for sure, right? So you will have 7 its position. Now you are there in this function call, you are done with the partition, and what did partition return? Partition returned 3 to you, right? The index 3, which is this index of 7. Now what will you do? You will call for L to P minus 1. So you will call from 3 to 2. P minus 1 is 2, right? So you will call from 3 to 2, because after partitioning you call for the left, and left is empty, nothing is there on the left. So you call from 3 to 2. So when you call for 3 to 2, again the execution begins from here, and this time L is greater than H. So this call immediately finishes, right? And next call in the parent function call, which was from 3 to 6, is for this subarray 8, 10, 9, right? That's what we call here. When you call for this subarray, your 9 is the pivot, right? That's what we do by default in Lomuto partition. So 9 is pivot. What you will do? You will partition the array around this value 9. So 9 will go to the middle, right? And you will get the index of middle. So your partition function will change it to 8, 9, 10. And you will call for 4 to 4 and 6 to 6, right? And 4 to 4 will immediately return because there is only single element. 6 to 6 will also immediately return because there is only single element. So this is how you get your array sorted. You got 3, 4 here, you got 8, 9, 10 here, and 7 got its correct place, right? And 5 also before that got its correct place. So you have array 3, 4, and then you have 5, then you have 7, then you have 8, 9, 10. So your whole array is sorted. The thing about quick sort is you do the extra work in partitioning, and then you divide it into 2 halves and then simply call quick sort for them. You don't have to do anything. You can relate it to binary search tree. What happens in binary search tree? You have a root. So the element that you get after partitioning becomes the root, right? And this is your left subtree. All the smaller elements go to the left subtree. And this is the right subtree. All the greater elements, they go to the right subtree. You make a call for the right subtree. That's how you can relate quick sort to binary search tree. In this video, we are going to talk about quick sort algorithm using Hoare's partition. We have already talked about quick sort algorithm using Lomuto partition. We are talking them separately because our main quick sort algorithm changes according to partition. Also, different academic environments, they teach different partitions. So let's understand quick sort considering Hoare's partition. The idea of quick sort is this. You have a partition algorithm which takes a pivot, divides your array elements around that pivot. So your Hoare's partition, it considers first element as a pivot. It puts all the smaller than or equal to elements on left side and all the greater than or equal to elements on right side. So your different partitions can be sorted independently and your whole array becomes sorted. Let's take this example. Using Hoare's partition, we consider 8 as a pivot. And when you call Hoare's partition, what happens? All the elements which are smaller than 8, they go to the left side, and all the elements which are greater than or equal to 8, they go to the right side. This is how your Hoare's partition your algorithm. 5, 4, 7, 3, they go on the left side. 9, 10, 8, they go on the right side. Now, if you sort these arrays independently, if you sort them independently, right? If I sort this, I'll get 3, 4, 5, 7. If I sort this, I'll get 8, 9, 10. I don't have to do anything extra after that. I just have to do the partition, and after partitioning, if I sort this independently and sort this independently, my whole array is sorted. If I sort this sub-array of my array independently and this sub-array independently, because all these small elements are smaller than or equal to all these elements. So if they are sorted and they are sorted, there is no element which is going to be moved on this side, and there is no element which is going to be moved on this side. So if they are sorted independently, you are done. So in quicksort, your main function is partition function that partitions the array around the pivot, and once the partitioning is done, you just have to recursively call left part, which is smaller or equal to, right part, which is greater than equal to. That's all your quicksort logic is. So there is a base condition which says that there should be at least 2 elements to sort. If you have only 1 element to sort, then nothing to be done, right? So L smaller than H means there should be at least 2 elements to sort. So when that is the case, you find the partition point by calling the partition algorithm. Then you call quicksort from L to P, and then you call quicksort from P plus 1 to H. So if you take a look at this array example, your L is 0, your H is 6, and this is considered as pivot by Hoare's algorithm. And after partitioning, what happens? Your left array becomes this and right array becomes this. And your Hoare's partition returns an index 3, right? Which means elements from 0 to 3 are smaller than or equal to elements from 4 to 6. That's what Hoare's partition guarantees. So what do? You get 3 as an output in the partition here. So you initially passed 0 and 6 to the partition function. And we have already talked about this partition function. If you have not seen the Hoare's partition video, it's strongly recommended that you see that video first. So what that video does, that returns 3. So P becomes 3. Now what do? We call from 0 to 3, and then we call from 4 to 6. And if we sort them independently and sort them independently, our whole array is sorted. We don't need to do anything more. So there is nothing after this line. You just have to sort these 2 sub-arrays independently. So let's do a dry run of this algorithm with this example. Let's see what all happens when you run this algorithm. So you initially pass 0 and 6 to this quicksort function. I have written QS here, which means this QSort only, right? We have to type it again and again, so I've used the short form here. So L is 0 initially and H is 6. Now we call the Hoare's partition function, and what this function does, it modifies this array to 5, 4, 7, 3, and then 9, 10, 8. That's what this function does. And it returns you this index, P. Right? So you get P as 3. Now what do? After you get this P as 3, you go to this recursive call. Right? And when you come to this recursive call, you call from L to P, which means you call from 0 to 3. So you call from 0 to 3, the partition function is called again in this recursive call. So let's see how does this 0, 3 call work. So when you call from 0 to 3, you again begin from here. 0 is smaller than 3. So you will come here and you will again call the partition function for 0 to 3. So you will call partition for this array. And what partition function will do? It will rearrange this array as 3, 4, 7, 5. So I'm directly writing the output of partition function everywhere because we have already talked about Hoare's partition. And your partition function will return you this index, which is 1. P is 1, right? So what will you do? After partition is over, you will call from 0 to 1, L to P, right? That's what we do here, right? So when you call from 0 to 1, you again begin execution from here with these indexes. Since L is smaller than H, you will come inside. When you come inside, you will again call partition and Hoare's partition. So Hoare's partition is called for 3 to 4, and what this partition does, it makes this array 3 to 4 only. It keeps the array as it is if you run the Hoare's partition algorithm, and it returns you pivot index as 0. This is what your new P is, right? So you call from L to P, which means 0 to 0, and then you call from P plus 1 to R, which means 1 to 1, right? So you have two calls after it, 0 to 0 and 1 to 1. So 0 to 0 call will begin from here, and it will see L is equal to H now. So it will immediately return, right? So your this call returns immediately. And this call, this will also see that L is equal to H. So it will also return. So your caller gets the control back. It has done the partitioning, called quicksort for left half, called quicksort for the right half, right? And it is done. So it will also finish immediately. This call will also finish immediately. It will give the control back to the caller. So caller, which had done the partition, had called for the left half, and left half is now sorted. Now will call for the right half, right? Right half is 7, 5, right? So Hoare's partition is called for this subarray. So when you call for this subarray, what happens? Your array changes from 7, 5 to 5, 7. So when you change it to 5, 7, you again call from 2 to 2, because this is a pivot, new pivot return, and 3 to 3. These two calls, they come here and they immediately finish because they have only one element, right? So they don't go inside. So once this is done, it sorts the array to 5, 7, gives the control back to the caller, and caller has now complete array sorted 3, 4, 5, 7. After doing this, your caller gives control back to the main function, this function, and this now calls this part. And this part is also going to call recursively this way, and ultimately going to sort the array as 8, 9, 10. Right. Now caller has both the parts sorted 3, 4, 5, 7 in 8, 9, 10. It does not have to do anything more, and caller also finishes, and your whole array is sorted. When we implemented quicksort using Lomuto partition, we called quicksort from L to P minus 1. This is where Hoare's partition differs from Lomuto partition. Lomuto partition ensures that the pivot is fixed at its correct position. Then it calls for the left half and right half, and it calls for left half from L to P minus 1, right? Because P is fixed, it goes to its sorted position where it should be in the sorted array. But Hoare's partition, on the other hand, does not guarantee that thing. What it does, it ensures that the element on the left side are smaller than or equal to elements on the right side, right? And it returns you index of the last element of left side. So that's what is done by Hoare's partition. It does not fix any element at its correct position. It only partitions. That is why we call the recursive quicksort from L to P, right? Not to P minus 1 when we are using Hoare's partition. And other recursive call is same. Other recursive call is same in both Hoare's partition and Lomuto partition. Hoare's partition is much faster than Lomuto partition in general. There have been studies which say that Hoare's partition is 3 times faster than Lomuto partition on average. However, like Lomuto partition, Hoare's partition is also not stable. We did an example of an array where all the elements are same in the Hoare's partition video, and we saw that the elements were changing their positions even if they were same. That makes it unstable. There is one naive partitioning algorithm that we discussed. That's the partitioning algorithm which is stable. These two, Lomuto and Hoare, are not stable. In this video, we are going to talk about analysis of quicksort. For analysis purpose, I have considered Hoare's partition here. However, the time complexities in both Hoare's partition and Lomuto partition are going to be same. In fact, the extra space requirements, they are also going to be same in both the partition algorithms. Naive partitioning algorithm, however, requires some more extra space. Let us take a look at this algorithm and let us analyze it for different cases. Let us first talk about the best case of quicksort. In general, we never analyze algorithms for best case. It's not recommended to analyze for best case. But for quick sort, it's a good idea to analyze for best case so that we get some idea about average case. I have drawn here an example recursion tree for the best case. What happens in best case is your input array is divided into two halves in every recursive call, right? So your pivot is always picked in such a way that it is middle element value wise, and it puts half elements on left and half elements on right. And we are considering here Hoare's partition. So pivot itself is not fixed. Pivot can go anywhere, but it is ensured that elements on left are smaller than equal to pivot, elements on right, they are greater than equal to pivot. So you call recursively for left half and right half, right? In Lomuto partition, you fix an element, right? And in best case, you will be calling for n minus 1 by 2 left half elements and n minus 1 by 2 right half elements, right? In Hoare's, you will be calling for n by 2 and n by 2. So I've considered the best case where we have 8 elements and we divide them in such a way that we have 0 to 3 elements, 4 elements on left side and 4 elements on right side. So these are the indexes we have written. L is 0, H is 7, L is 0, H is 3, L is 4, H is 7. So this is the best case scenario. Your partition point, it always divides your array into two halves. What is the time complexity in this particular scenario? Let's analyze it. How much work we do at this level? We call the partition function for n elements from 0 to n minus 1, and that takes Cn time. Right? So we do Cn work at this level. How much work we do at this level? We call partition function for n by 2 elements here. So it takes Cn by 2 work, this particular partition function, and then partition function takes Cn by 2. So Cn by 2 plus Cn by 2 is Cn. So we do Cn work at this level. How much work we do at this level? We again do Cn by 4, Cn by 4, Cn by 4 and Cn by 4 work, and 4 into Cn by 4 is Cn. And then we are going to make recursive calls for single elements 0, 1, 2, and then it will make a recursive call for 3, and it will make a recursive call for 4, 5, 6 and 7. Once single call are made, you stop here, right? That's your termination point, because you go inside this if condition only when there are more than one elements. So how much work you are doing here? These are all constant operations, right? Theta 1, theta 1, theta 1 operation. So you do theta n work here, right? Theta 1 plus theta 1 plus theta 1 n times. So this is theta n work. So how much work you are doing overall? Right? What is the sum of all this work that you've done in all the levels? So all the work done in all the recursive calls can be written this way: Cn plus Cn, Cn, and then theta n for the last level for single element recursive calls. Now how many Cn are going to be there? Let's take a look at this example. We have 8 elements and we have Cn 3 times. 1, 2, 3, right? So how many Cn we have for 8? 3. How many Cns we are going to have for 16? Just pause this video and try to guess yourself. In every recursive call, you are reducing the n by 2, right? You're dividing n by 2. So if n is 16, then it will become 8 in the next recursive call, then 4, then 2, then 1, right? So how many recursive calls it will take? For 16, it's going to be 4 Cns, right? And for 32, it's going to be 5 Cn. So we can say these are log n terms, right? These are log n terms because we are dividing n by 2 in every recursive call in the best case. So we have Cn into log n plus theta n, right? And how much is this? We can ignore the lower order term, so we get the time complexity as Cn log n. or we can say theta n log n in the best case, right? So that's the time complexity of quicksort in the best case. I have redrawn the recursion tree for general best case, when you have n elements and you have n by 2 elements on the left side in the partition, n by 2 elements on the right side. So if you see, for n elements, you do Cn work at the top level, then Cn by 2 plus Cn by 2, Cn work at the next level, Cn by 4, 4 times, Cn work at the next to next level, and at the last level, you do theta n work because you call for single elements. And when you call for single element, you do not go inside if condition and you come out in constant time. So the overall work done is Cn plus Cn dot dot Cn means Tcn for log n times, right? So this is Cn into log n, Cn into log 2n plus theta n, which is theta n log n, right? So in best case, we have the time complexity as theta n log n. Here is a recursion tree diagram for worst case. What happens in worst case? Your partition function divides your array in such a way that you have one element on one side and n minus 1 elements on the other side. Your worst case diagram can be like this, or it can be something like this also, that you have Cn minus 1 on one side and one element on the other side, which is theta 1 work. Then you have, theta 1 on here and Cn minus 2 here. Then theta 1 here and Cn minus 2 here, Cn minus 3 here. So this is also worst case. If your partition function is again and again dividing your array in such a way that you have n minus 1 elements on one side and n elements on the other side, then that's the worst case. That's the worst case of quicksort. If you remember the best case, in best case our recursion became something like this. We had n as an input and we were dividing it into two parts, two equal parts, 2tn by 2 plus Cn work for the partitioning. This was the recursion for best case. Now if you try to write the recurrence for worst case, what will be your recurrence for the worst case? It will be Tn equal to, where Tn is the time taken by quicksort for input size n. It will be Tn minus 1 because you have n minus 1 elements on the one side plus theta n work to partition, right? And we have solved this in the recurrence track, right? This is n square. But let's see again, with this example also, how are we getting n square? So we are doing Cn, Cn minus 1, Cn minus 2 work here. And how many levels we have in this tree? So you say have an input array of size 5, something like 0 to 4. And you recursively call your quicksort for 0 to 0. Then you recursively call quicksort for 1 to 4. Then again worst case considering 1 to 1. Then 2 to 4. Then 2 to 2. And worst case considering 3 to 4. So if you keep on doing this way, you will have how many levels? So let me draw the last level as well. 4, 4 and 3, 3. That's your last level. So how many levels you have for 5 nodes? You have 5 levels. 1, 2, 3, 4, 5. Right? For n nodes, how many levels you will have? N levels. And if you do the sum of the series, Cn, Cn minus 1, Cn minus 2 up to 1, what you will get? You will get Cn square, theta n square, n into n plus 1 by 2. This is sum of natural numbers, right? So you will get theta n square. And plus you have theta 1, theta 1, theta 1. This is also n times. Plus you will have theta n, right? Which is theta n square. So this is one way to analyze the worst case. Other way could be Tn equal to Tn minus 1 plus theta n, right? Which is big O of n square. That's the worst case, right? And if you want to write the best case recursion, that will be Tn equal to 2Tn by 2 plus theta n. In both the recursions, theta n is for partitioning work, and In worst case, you will have n minus 1 elements on the one side, so you will recursively call for n minus 1. In best case, you will have n by 2 elements on both sides, and you will make two recursive calls for n by 2 n by 2. So that's the best case recursion, and recurrence, that's the worst case recurrence. Let us now get an idea of average case analysis. Please note that we are not going to do average case analysis exactly, because that is too much mathematical. Here we are only going to consider a case to get an idea of average case analysis. Please remember, for average case analysis, you need to consider every permutation of input array, assuming the fact that every permutation is equally likely in input, right? And with this assumption, for every permutation, you need to count how many partitions, how many elements will be there in one partition, another partition. You need to do sum of all the times taken and then divided by the total number of permutations. So we are not going to do that. We are going to consider a situation where we have n by 10 elements on one side and 9n by 10 elements on the other side. So we are considering a fairly unequal division where you have out of 100 elements, say 10 elements on one side and 90 elements on the other side. So that's a fair assumption for considering the average case. So I've taken an example of 1000 here, and I've assumed that we have 9n by 10 elements on one side and n by 10 elements on the other side. So what will happen in this case? You will have 100 elements here and then 900 elements here. And in this 100 case, you will have 10 here and 90 here. In this 10 case, you will have 1 here and 9 here. In this 9 case, although it's not exactly n by 10 and 9n by 10, because it will be 8.1 if I do 9n by 10. So I've considered 1 and 8 elements, right? Because that's not a possible partition. Your overall sum should be equal to 9 and equal integer element should be there on every side. So again, you will have 1 by 8, 1 and 8 elements here, and 8 and 73 elements here, and so on. If you see this recursion tree, what is happening here? This level has all the elements filled, right? And this is last to such level. Below this level, you do not have these two, right? And below this level, you do not have these two, right? So this filling in this recursion tree, it's going to be partial, right? And this tree is going to exhaust first, then this tree, and this tree is going to go down, 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 right? So it's going to be the deepest tree, the rightmost tree, right? And this is going to be the shallowest tree, the leftmost tree. That's how the recursion tree is going to be. So what we do to analyze in such a case, we consider the recursion tree to be completely full, right? We assume that, okay, let there be extra work done here, and we compute an upper bound on the time complexity, right? So we do Cn work here for sure, Cn work here for sure, C1 work here for sure. Then we do less than equal to Cn work at this level when this becomes, completely full. The last level which is completely full, because you have theta 1 work here, and then you have Cn minus 1 sort of work here. Then you again have less than equal to Cn work here, right? And then you again have Cn less than equal to Cn work here. So for simplicity, we assume that this is equal to Cn, right? Let's assume this is Cn and your tree is completely full. So we'll have Cn work to get an upper bound, right? We are not going to get an exact bound. We are going to consider upper bound. So we consider Cn at every level. Now how many levels we have, right? So can you guess the number of levels till the deepest node, right? The last rightmost node is going to be the deepest node. Till the deepest node, how many levels you are going to have in the tree, in the recursion tree? So if you see this side, the rightmost side, which is going to be the deepest side, you are dividing your n by 10 by 9, right? So when you divide your n by 2, you have log 2n levels. Now when you're dividing your n by 10 by 9 in every level, how many levels you will have? You will have log 10 by 9 base n. These many levels you will have. The deepest level is going to be this much below, right? And if I assume that total work done is Cn, although we have less than Cn at the lower levels and much less at the lower and lower levels, right? So if I assume that I have Cn work done at every level, I'll have Cn into this much work, and I put a big O here, right? So what is this value? This value is actually big O of n log n only, because base in log does not matter. It's an asymptotic notation, and we can change the base by multiplying and divide by some constants. So in the case where you have slightly unfair division, or maybe too much unfair division, where you have n by 10 elements on one side and 9n by 10 elements on the other side, still you are getting the time complexity as n log n. So this is not average case analysis. This is a case where division is slightly unfair, and we get an idea that even with this unfair division, we are getting the time complexity as n log n. That's an upper bound, right? That's an upper bound on the time complexity. So we have analyzed quicksort in best case, in worst case, and to get an idea of average case, we have considered an unfair division. If you even consider random pivot selection, if you randomly pick a pivot, right? Even in that case, it can be proved that the expected time taken by quicksort is theta n log n only. So the random pivot selection also gives you theta n log n time, and that's how quicksort is n log n on average, and that's the reason it works better than other competitors like merge sort and quicksort. Although worst case is n square, but on average it takes n log n time only. Hi, in this video we are going to talk about auxiliary space analysis of quicksort. Most of the textbooks and Wikipedia page, they say that quicksort is in place. However, this is arguable. It depends how do you define in place. If you define in place as an algorithm that takes constant extra space, then quicksort is definitely not in place. The partition function of quicksort, it's in place if you are using Hoare's partition or Lomuto partition. Whichever of these two you use, they both are in place. They use constant excess space. But if you consider quicksort algorithm, it requires extra space for the recursion call stack. There are other ways people define in place algorithms. The other definition is, if your algorithm is not copying input elements to an auxiliary space, then this algorithm is in place. If you go by that definition, then you can call quicksort as in place, because it does not copy the input array elements to another array. It only needs extra space for the recursion call stack. Let us see now how much space quicksort requires for recursion call stack. I have drawn a recursion tree for the worst case. In worst case, like time complexity analysis, what happens? You have one element on one side and n minus 1 elements on the other side, and that keeps happening in every recursive call. So let's understand how much extra space is required on the recursion call stack. So when you make the first call for qsort for 0, 4, right? You begin from here, this goes into the recursion call stack, and you call for qs04, right? Then you call the partition function, right? After that partition is called, partition goes into the recursion call stack. It partitions the array, it goes out of the recursion call stack, right? It finishes and goes out of the recursion call stack. Now you call quicksort for 0, 0. So quicksort 0, 0 comes into the recursion call stack. Now quicksort 0, 0, it fails with this condition, so it immediately returns, right? So you're done with the quicksort 0, 0 as well. Now you call quicksort 1, 4 here, right? Because the left call is done and before that partition is also done. So you have come here and now you call for quicksort 1, 4. So your next recursive call is quicksort 1, 4. When you make a recursive call for quicksort 1, 4, your 0, 4 is still not done. It's there waiting in the recursion call stack for this to finish and quicksort 1 to 4 has also come in the recursion call stack. What this will do, it will call partition. Partition will partition your array from 1 to 4 as 1 1 and 2 4, and quicksort 1 1 will be called after that. What will happen with quicksort 1 1? It will not satisfy this condition and it will immediately return, right? Then quicksort 2 4 is called. What will happen in quicksort 2 4? It will also call the partition function. So I'm skipping some steps here, right? It will call the partition function, that will go into the recursion call stack, and that will finish. Then it will call quicksort 2 2, considering the worst case. It will start and it will finish. And then it will call quicksort 3 4. So I've jumped a few steps here and directly written quicksort 3 4. Now quicksort 3 4 will call quicksort 3 3. Quicksort 3 3 will return, and then it will call quicksort 4 4. If you look at this recursion call stack at this point, how many stack call frames, how many function call frames are there in this stack? We have 5. That's the maximum function calls you have at any moment of time in the worst case. And how is this 5 related to the number of elements in the array? It's equal to the number of elements. We had 5 elements 0 to 4, and we have 5 function calls at most at any point, right? Because when you call 4 4, it will finish because there is one element only, and it will return control back to 3 4, and which means it will go out of the stack, then this will go out of the stack, then this will go out of the stack, they'll start returning. But in worst case, you have 5 function calls in the recursion call stack, which is equal to the number of elements in your input array. So what do you say about the extra space required by the quicksort? It's theta n, right? There are n function call records, which is theta n. So if you have n elements in your input array, you have theta n worst case. Let us now talk about best case space requirements of quicksort. Best case happens when your array is divided into 2 halves in every recursion. See, your extra space requirement of quicksort can be seen as number of levels in your recursion tree, right? Because if you're calling this, then you're calling this, then you're calling this, then you're calling this gets over, then you're coming here. So how many recursion function calls you will have in recursion call stack at most? Height of this recursion tree. And height of this recursion tree becomes theta n when you are dividing your array such that you have one element on one side and then -1 elements on the other side. When will the height minimum? When you have equal elements divided in every recursion, half elements, right? And that's an example of this case. So you have half elements on left side here, half on right side. Here also you have half on left, half on right, half on left and half on right. So what is the height in this particular case? Log n, right? Height of this recursion tree is log n. At any moment in your function call stack, you will have at most 4 functions, right? At most 4 functions, which is log of 8, because we have 8 elements plus 1, right? If you have 16, then you will have at most 5 functions at any moment, which is log of 16 plus 1. So when you have this much function calls at most, this is your auxiliary space requirement, because quicksort requires auxiliary space only for the recursion call stack, recursion calls, right? It does not require extra space for anything else. Partition is big O of 1 extra space if we are considering Lomuto or Hoare's partition. But please remember, Lomuto and Hoare partitions, they do not provide stability. However, they both are in place. Naive partitioning scheme, it is not in place, but it is stable, right? So if you are talking about Hoare and Lomuto, then theta of log n is the maximum space you need in the best case. With some optimizations like tail call elimination, we can optimize the extra space requirements of quicksort to this in worst case. In the previous videos, we talked about time complexity analysis of quicksort and space analysis of quicksort, how much auxiliary space it requires. In both the videos, we saw that quicksort requires maximum space and maximum time when your partitioning happens this way, that you have one element on one side and n minus 1 elements on the other side. Now, if you take a look at these Hoare's partitions and Lomuto partitions that we discussed in separate videos, Lomuto partition, it picks the last element as a pivot. And Hoare's partition, it picks the first element as a pivot. What happens when your array is sorted? Sorted in the increasing order or sorted in the decreasing order? Both the partitioning schemes, Lomuto and Hoare, they will lead into the worst case. They will turn into the worst case. If you have a sorted array, for example, 10, 50, 100, 200, and if you are using Lomuto partitioning, you will pick this as a pivot, and what will happen? You will have n minus 1 elements on one side and 0 elements on the other side. And if you use Hoare's partitioning, you will consider this as a pivot and you will have n minus 1 elements on one side and 1 element on the other side, right? That's how these partitioning algorithms work, Hoare and Lomuto. So if your input array is sorted, they both are going to turn into the worst case. Now imagine a situation that you are designer of library of sort function of a programming language like Java or C++, and you wrote the quicksort function by choosing first element as a pivot or last element as a pivot. Now there are many users of your library, and some of those users, they always use your function for a sorted array. What will happen for those users? They will always get the worst case, and they will say that the sort function of this programming language is not well written. It takes a lot more time compared to other sort functions, other functions in other languages. You don't want that. Basically, you don't want a pattern of input for which your algorithms generally fail. And this is what is called adversary analysis, right? You don't want an adversary who knows your algorithm and can always give inputs which lead to the worst case. So what do you do for such cases? You use a random function to generate a random pivot, right? And that's what is generally done in practical implementations of quicksort. Most of the practical implementations, they are randomized versions of the quicksort algorithm. And the idea is simple. You can generate a random pivot, right? A random number from L to H, right? And I've written R here, so let's consider L to R. So you generate a random pivot from left to right, and after generating the random pivot, you simply swap array array L with array P. And then you can apply Hoare's partition, standard code of Hoare's partition, right? And if you are using Lomuto partitioning algorithm, then you can do swap array R with array P and then call Lomuto partition. How does this work? We generated a random number between L to R. We went to that index and put the element at that index in the beginning, right? And now your Hoare's partition will partition your array around this beginning element. And what did we do here? We again generated a random number, right? We again generated a random number from L to R. We went to that index and swapped it with array R, right? So our random number goes to the last element and our partitioning happens around that random number in both the partitions now. So we can quickly modify both Hoare's and Lomuto partitions to partition around a random element. And this way, we do not have any pattern for which our quicksort algorithm always leads into the worst case. Also, it can be proved mathematically if your random function generates random number uniformly, then your expected time complexity of your quicksort is big O of n log n. In this video, we are going to talk about tail call elimination in quicksort. The idea is to optimize it, and compilers, modern compilers, most of the time do tail call optimization themselves. Let's take a look at this quicksort code. What happens here? We do partition, we call the quicksort for the left part and right part. If you take a look at this code, we do not do anything after making a recursive call. That's the last thing we do. So what happens in such functions? Such functions are called tail recursive functions, and we can always optimize them by doing tail call elimination. The idea is this: you can change the parameters, you can add a go to statement here, and you can send them back to this level. You can make a label here, begin, and you can send them back to this particular begin point. And this way, you eliminate the last recursive call. The basic idea of tail call elimination is, if recursive call is the last call, then there is no point of keeping the track of parent function call, because it doesn't do anything when the child call returns. That's the main idea, that's the basic idea for tail call elimination. I have rewritten the quicksort function after doing tail call elimination. What I've done here, I've removed the last recursive call, right, which was from p plus 1 to r. What I've done, I've changed this L to p plus 1, right, and now send the control back to this point. What will happen at this point? It will again compare L and R. Since L is smaller than R, it will come here and continue, right, and it will effectively do the same thing as the recursive call. We can use tail call elimination to optimize the extra space required for quicksort. What we can do, we can see how many elements are there in the left part after calling the partition, and how many elements are there in the right part after calling the partition function, right? And whichever has smaller element, you recur only for that part. You do tail call elimination for the larger part. This way, you can optimize extra space required for the quicksort. Let us talk about this problem now. We are given an unsorted array and a number k, where k is smaller than or equal to size of the array. Our task is to find out kth smallest element. For example, if this is our input array and if k is 2, then we need to find out second smallest element. The smallest element is 5 and the second smallest element is 10. So our output is going to be 10. Let's now see this array. We are given this array and k is 4. We need to find out the fourth smallest element. The smallest element is 5, then 8, then 10, and then 20. So fourth smallest is 20 and our output is 20. Now please pause this video and try to write down a function that takes an array as input and a number k as another input and returns kth smallest element in the array. Let us first talk about a naive solution to solve the problem. The idea is very simple. We simply sort the array, and after sorting the array, we return the element at index k minus 1. So if this is your array, you will first sort it. You will get 3, 5, 10, 20. For k equal to 2, you will return array k minus 1, which is array 1, which is 5 in the sorted array. So this is C++ code and this is Java code. It's a simple implementation, and the time complexity is clearly big O of n log n because sorting is involved. And auxiliary space required for this solution depends upon the requirements. If you are allowed to modify the array, then it's clearly big O of 1, right, because you're sorting the array. But if you're not allowed to modify the array, then you will have to copy the original array into a temporary array, right? Then you will have to sort the temporary array. So auxiliary space is big O of 1 if you are allowed to modify the array, otherwise it's big O of n. Now please pause this video and try to think of a solution that works better than this on average. Here is the idea for the efficient solution. What we do here is we use the partition function of the quicksort. And we use particularly this form, which is close to Lomuto partition. We pass the array, we pass low index and high index. And what this partition does, it simply picks an element and partitions the around this element. And it could pick a random element, first element or last element, any element. Say it picked an element x. And after partition, what this function is going to do, it's going to put all the smaller elements on the left side and all the greater elements on the right side. And for simplicity, as I said earlier, we are assuming that all elements are distinct here. So we get all smaller elements here and all greater elements here. And x is fixed at its correct position. And the index of this x element is returned by the partition function, right? So we get this index p. Now, if you understand this, I think you can guess rest of the code. What happens now, if p is k minus 1, suppose you are looking for second smallest element and p is 1, then you have reached the second smallest element. The element that you picked as a pivot and the element around which you did the partition is actually your answer. So in this case, what are you going to do? You are simply going to return ARRP. That's your output, right? That's your kth smallest element, as simple as that. Now, if p is greater than k minus 1, what will you do? Please pause this video for a moment and try to write down the expressions that you will write here in these two conditions. If p is greater than k minus 1 and if p is smaller than k minus 1. See, if p is greater than k minus 1, that means your element lies on the left side of p, right? And if p is smaller than k minus 1, that means k is actually higher than the this value. And what it means, k lies, your required element lies on this side, or the greater element side. So when p is greater than k minus 1, you know that element lies here, right? So what do? You actually reduce the upper limit from high to p minus 1. So what are you going to do in this case? You are going to do high equal to p minus 1. High equal to p minus 1. That's what you will do, right? You reduce this input to this left side of the element. Now if p is smaller than k minus 1, that means your element lies on this side. And now I guess you can guess it. What are you going to do? You are going to change your low equal to p plus 1. That's all you need to do, right? So now you have the complete idea. Please pause this video and try to write down the complete function that takes array as input, k as input, and returns the kth smallest element. And please remember, the time complexity of this implementation is going to be same as quicksort. In the worst case, it's going to be big O of n square, right? It might happen that you keep on having one element on one side of the partition and all the remaining elements on the other side, and at the end you figure out the kth element, right? So worst case can be n square, but in general it is going to work much better than the naive solution we wrote, because it might happen the first iteration itself that you find out the kth smallest element, right? Or maybe in the second or third iterations. So on average, it's going to take much less time. It's going to be like quicksort. Quicksort on average takes big O of n log n, right? And in the best case also takes n log n, but in the worst case takes n square. So it's going to be like quicksort, and quicksort in general works good. So time complexity wise, it's going to be same as quicksort implementation. Now you have the enough idea. Please pause this video and write the complete function. Here is the implementation of the partition based approach. We have this array and we have this value k as input. First thing, we initialize low as 0 and high as n minus 1, the number of elements in array. If you're programming in Java, you don't have to pass the size of the array as argument. After this, we run this loop while low is more than equal to high, and we implement that logic, right? We first find out the partition point by using the Lomuto partition. So if this is your input array, then your partition point is going to be, we are always going to pick last element as a pivot, right? So we pick 26 as a pivot, and p is going to be 6, the last index in the array, right? And this Lomuto partition might rearrange these elements as well, right? But in this case, it would not, because they are all smaller. So we are going to get p is 6, and when p is 6, your k is 5, so p is actually greater than k minus 1. In this case, what we do? We know that the fifth smallest element is going to be on the left half, and right half is not present at all. So that's why we change high equal to p minus 1, so that we move to the left half subarray. So high now becomes 5. And when high becomes 5, you again pick the last element of the current subarray's pivot, which is 6. right? So when you pitch 6 as a pivot, you again do the partition function in this iteration, right? So you get 4, 5 on left side and all the greater elements on the right side, and these elements get rearranged, right? 8, 11 and 10 instead of 10, 11, 10 and 11, they might get rearranged, and I've written the rearranged order 8, 11, 10. So what happens now, you have a pivot at index 2, so return value by this function is going to be 2, and this 2 is smaller than k minus 1. K minus 1 is 4, and this time what are we going to do? We are going to call for this side, right? We are going to call for this side. That's why we change low to p plus 1, right? We change low to p plus 1, and when we call for p plus 1, we actually call for low equal to 3 this side. And when you do this, you are going to consider 10 as pivot, right? This side means from current low to current high, right? So you are going to call for pivot as 10, and when you call for pivot as 10, you get the array rearranged like this. You get 8, 10, 11, and the return p value is 4. And this time, p is actually equal to k minus 1. So you return 10. You return the output 10, and you find the kth smallest element. Right, that's the simple idea of this implementation. In the worst case, it's clearly big O of n square. In the best case and average cases, it's big O of n log n. And see, it is an iterative implementation. First, when we look at the idea, we write down the recursive solution, right? We'll call the partition and we'll pass low and high accordingly. But iterative is much easier to write and much simpler to write. That's why I've written the iterative implementation here. And iterative is going to be faster also because there are no recursive calls involved. And this standard algorithm, this is actually a standard algorithm and called quick select algorithm to find the kth smallest element or kth largest element.
Let us talk about this problem. We are given an array of integers. Our task is to find the minimum difference in this array. For example, if we are given this array, our minimum difference is 3, and we get this minimum difference by subtracting 5 from 8. Let's see this example where we have only 2 elements. So when we have only 2 elements, the minimum difference is only the difference between these two, right? So our answer is 15 minus 8, 7. Here's one more example. The minimum difference that we get is by subtracting minus 1 from 0, right? 0 minus minus 1 is plus 1, and we get the minimum difference as 1. If we have only single element, then we are going to return infinite. In C++, you can return int underscore max. In Java, you can return integer.max value. So please pause this video and try to write down a function that takes an array as input and returns the minimum difference. Let's first talk about a naive solution to solve the problem. The idea of this naive solution is consider all pairs. For every pair, find the absolute value of difference, and if this absolute value of difference is less than the result so far, then update the result. We initialize the result as infinite, int underscore max in C++ and integer.max value in Java. So if you have an array like this, a0 to an minus 1, and if you are at element ai, what you are going to do is you are going to consider every element aj from a0 to ai minus 1 to consider every pair, and you are going to find the difference between ai and aj, right? You are going to find the absolute value of this difference, and then you are going to compare it with the result so far. So this way you will be able to consider every pair. See, ai, for ai we have considered, we have paired it with all the elements before it when we are at ai, right? And all the elements after it are anyways going to pair with it, right? So that way we have paired ai with every element, right? So every element is paired with every other element, and this way we have considered every pair and find the difference. So this is the implementation. I have written pseudocode here, right? I have initialized the result as infinite. Infinite means integer underscore max in C++, integer.max value in Java. So what I've done here is I've run a loop for I equal to 1 to n minus 1 because we are going to begin with second element. For first element there is nothing before it, right? So for every element ai we are going to run a loop from 0 to I minus 1, and we are going to compare the absolute difference between ai and aj with result, right? And if the absolute difference is less, we are going to update the result, and at the end we are going to return the result. So if I is 0, I is 1, we are going to run for j equal to 0. Initially result is infinite, it's updated to 2. Then for I equal to 2, we run 2 iterations of the inner loop for 0 and 1, and we get the differences as 3 and 5, so they are greater than 2. We don't update result. At the end we have result 2 only and we return the result. Now what is the time complexity of the solution? It's clearly big O of n square, or you can say theta n square also, because we do not have any break statement inside it. So the time complexity is clearly theta n square. Basically we are considering every pair, n into n plus 1 by 2 sort of expression we get, which is theta n square. Now please pause this video and think of a solution which takes less than theta n square time. Let's first talk about the idea of the efficient solution. The idea is, if you can somehow rearrange the array in such a way that every element is close to its value wise closest element, then you just need to find the difference between current element and its value wise closest element. If you are able to do so, then you don't need to compare the current element with any other element, because the minimum difference will be with the value wise closest element for every element. Now please pause this video and try to think of a solution that rearranges array in such a way that for every element we have the value wise closest element. The idea is simple. We are going to sort the array. Once you sort the array, then every element is going to be surrounded by its value wise closest elements. For example, if I have 10, 3, 20, 12, it's going to become 3, 10, 12, 20, right? And every element now has its value wise closest smaller and greater elements, right? Except the first and last. First has value wise closest greater next, and last has value wise smaller previous element. So once you have arranged in such a way, you can just traverse this array and you can find the difference between adjacent elements like 10 and 3, 7, 10 and 12, 2, 20 and 12, 8. And just return the minimum of these differences, which is 2, right? So you have the enough idea now. Please pause this video and write down the code. Here is implementation of the efficient approach. We are going to first sort this array. So for this sort, we need to include algorithm in C++, and we can do arrays.sort in Java. For that, we need to import java.util.arrays. So if you are given this array, your array will become after sorting, right? You will have 1, 4, 8, 10. After that, we are going to initialize our result as infinite in .max in C++, in underscore max in C++, and teacher.max value in Java. Now we are going to run a loop from the second element. We just need to subtract the previous element from every element to find the difference, right? And for first element, there is no previous. So we are going to begin from after sorting from 4. We are going to subtract previous element. We are going to get the difference as 3, right? So 3 we compare with infinite, we get the less value as 3. Then we come to 8 and we subtract 4 from it, so we get the difference as 4. Now we come to 10 and we subtract 8 from it, so we get the difference as 2. So our final result is 2 because 2 is the smallest difference, and we are finding the minimum value here. In Java, we can simply need to use math.minimum.
What is the time complexity of this? As a first step, we are sorting the array. Sorting takes big O of n log n time. So it takes big O of n log n time here. And then this loop takes, this whole thing takes big O of n time. Or you can say theta n, because we are running a loop from 1 to n minus 1. So that takes theta n. So overall time complexity is going to be this plus this, which is going to be big O of n log n. Let's talk about this chocolate distribution problem. We are given an array of packets. The first packet has 7 chocolates, the second packet has 3 chocolates, the third packet has 2 chocolates, and so on. And there are 3 children. There are m children basically. We need to pick 3 packets from this array, right? We need to basically pick m packets from these n elements, right? Such a way that the distribution of chocolates is fair. What do we mean by fair distribution? The minimum chocolates that a child gets and the maximum chocolates that another child gets, the difference between these two should be minimum, right? So let's understand this example. So I need to pick 3 items from this array such that the difference between minimum item picked and maximum item picked is minimum. So the answer for this is 2. The 3 items that we are going to pick are 2, 3 and 4, and the difference between 2 and 4 is 2. If you try picking any other 3 items, you will get difference more than 2. For example, if I pick 7, 3, 2, the first 3 items, the difference between minimum and maximum is 5, which is not fair. A child got 7 chocolates, another child got 2 chocolates. Now if I pick say 7, 3, 4, the difference is 7 minus 3, 4, right? Which is again not as fair as this one. right? And if I pick 249, then the difference is 7, which is again not fair, right? 7 difference. A child is getting 9 chocolates, another one is getting 2 chocolates. So we want fair distribution. In this example, we have this array of packets and we have 5 children, and you want to minimize the difference between minimum and maximum. So we pick these 5 items, 3, 4, 7, 9, 9. If you pick these 5 items, your difference between maximum and minimum is 9 minus 3, 6. Right? If you pick any other 5 items, you will get more than 6 difference. Right? 6 or more than 6, 6 is the minimum. Now, please pause this video and try to think of a solution that takes an array as input, another value m as another input, and returns the minimum difference between maximum and minimum of m picked item from the array. Let's now talk about the idea for this solution. If you take a closer look at this problem, this is similar to minimum difference problem. There we had to find out the difference between the adjacent items. Here we are going to find out the difference between m distance items in the sorted array. Let's first talk about the idea. So we need to pick m items, right? And out of these m items, one will be minimum and one will be maximum. So what we do is, we traverse through the array, we consider every item as minimum. You could do the other way also. You could consider every item as maximum as well. So what I'm going to do is, I'm going to consider every item one by one as minimum, right? And then I'm going to find out the closest m minus 1 items. And then I'm going to take the difference between maximum and minimum, right? That's going to be the set of m items where the current item is minimum. And out of all these differences, I'll take the minimum difference. So if 7 is the minimum element of m picked elements, then what should be the element so that we get the minimum difference in the m items? We'll pick the just greater elements, right? We'll not pick 56 because we have 9 and 12 greater, right? So we'll pick the adjacent greater element, just greater than this, then just greater than this. So we'll pick 7, 9, 12, and that's how we get the output as 12 minus 7, 5, where 7 is the minimum element, right? So now we consider 3 as the minimum element. So 3's adjacent just greater element is 4, then just greater than 4 is 7. So we take the difference between 7 and 3, we get the output as 4. Now we pick next item and we consider as minimum. So 2, 3, 4, difference is 2. This way we consider all the items one by one. The maximum item 56 would not be the minimum of the output because we need 3 elements where 56 is minimum and there can't be 3 elements. Same is the case with 12. 12 can't be the minimum element where you have 3 items. So we'll ignore 12 and 56. Right? And 12 and 56 could be anywhere, it's an unsorted array. So this is how find out the differences, potential differences, and out of these potential differences, we pick the minimum of all these, and which is 2. So our output becomes 2. So this is the idea. And one naive way of implementing this would be, you traverse through the array, for every item you find the just greater element than this, then the just greater element than the greater, right? Which is going to be a high time complexity solution. And we've already discussed this idea in minimum difference array problem. We are going to use the same idea. Basically, we are going to sort the array, and after sorting, we can find out m minus 1th greater element, like this is the current element, right? So we want to pick the 3 elements. So the second greater element after 7 is going to be 12. The second element, greater element after 3 is going to be 7. That we can quickly find out. We take the current index, we add m to it, and then subtract 1 from it. We get the I plus m minus 1 item as the largest element of the m items. So this is the idea. Now you have the complete idea. Please pause this video and write down the complete solution yourself. Let's now talk about implementation of the idea. So we first sort the array, and the advantage that we get sorting is m minus 1th greater element you can find in big O of 1 time, right? So this is your array. You will sort it first. You will get 1, 3, 7, 8, 9, 12, 56. Your m is 3. So what you will do, you will initialize the result as difference between 1 and 7. 7 minus 1. So what are we doing? We are considering every element as minimum. Then the corresponding maximum element we find out by simply considering I plus m minus 1 in the sorted array, right? If array I is the minimum element of the current set, then in the sorted array, this will be the maximum element, right? So 7 minus 1, 6 is our initial result. Then we initialize the result as ARR m minus 1 minus ARR 0. See guys, here I have handled the basic condition here. If m is greater than n, then we return minus 1. If there are more children than the packets, we'll return minus 1. Then we sort the array, and this sort is in C++ style syntax. If you are using Java, then use arr.sort, right, and pass the array. And again, if you are using Java, then this parameter is not required because length of the array you can determine using arr.length, right? So you don't need to pass array here. You can use arr.length here, right? So those are the basic differences between C++ and Java syntax. What are we doing? After checking for the base condition, we sort the array. And after sorting, we initialize the result as this 7 minus 1, 6. Then we run a loop from second element. And we run the loop while I plus m minus 1 is smaller than n, right? So we run this loop till this point 9, right? While we can consider the current element as the smallest element. You can't consider this element as the smallest because there are no two greater elements than this. You can't even consider this element as smallest, right? So we begin with the second element. And for every element, we find the element at I plus m minus 1 index, right? We subtract the current element from there. We check whether the difference is smaller than the result, then we update the result. So you begin with I equal to 1. Your I equal to 1 means you are going to consider this set. 8 minus 3 is 5. So your result is updated from 7 to 5, is from 6 to 5. Then you come to I equal to 2. And you consider 7 as the minimum element and you consider this set. 9 minus 7 is 2. So 2 is smaller, so you update the result. Now you come here and you consider 8, 9, 12. This 12 minus 8 is 4, this is greater, so result does not change, right? Result remains 2, that's why I've written dot 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 here. Now you guys come here. 56 minus 9, 47, result is not updated, result remains same. So we have dot 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 here, result remains 2. So this is our final result. Right? Basically, after sorting, we are getting an array like this and we are considering this element as minimum and this element as maximum when we are traversing array higher. So that's the simple idea. Now, what is the time complexity of the solution? You can clearly guess it's big O of n log n in sorting, right? And then we are traversing the array in linear time, so which is theta n. So time complexity is going to be big O of n log n.
Let us talk about these type of problems where we are given an array of two types of elements and we need to sort this array. This question is asked in different forms and I have written here three popular forms. The first form is given an array of positives and negatives, you need to put negative first in the sorted array and then all the positives. The order among negatives may change, it does not matter, and the order among positives also may change. For example, if you're given this array 15, minus 3, minus 2, 18, you need to produce an array which has all the negatives first, like minus 3, minus 2, and then all the positives, 15, 18. So this is not the only valid output. The other possible valid output can be where you have different order of negatives and different orders of positives. This is second form of this problem, where we are given an array of even and odd elements, basically integers. We need to segregate even and odd, right? So all the even come first, like 14 and 12, right? And their order does not matter. You can put 12 first and then 14, but even should be together and then all the odd elements. First all even, then all the odd elements. The third form of this problem is you need to sort a binary array. You are given a binary array like 0, 1, 0, 1 and you need to sort it. You need to put all the zeros first and then all the ones. For this particular problem, many of us, when we start solving this problem, we think, okay, it's a very simple problem. What all we need to do is count how many zeros are there, right? And then you can get the count of ones by subtracting the count of zeros from total size. Now what you do is you put, say you have the count of ones as count of zeros at count 0. So you run a loop from 0 to count 0 and you put all the zeros first. Then you run a loop for count ones. Count 1 you can get by subtracting array size minus count 0, right? Then you run a loop from 0 to count 1 minus 1 and then you put all the ones after zeros. See, this solution is fine, but there are certain disadvantages with this solution. The first disadvantage is you are traversing the array multiple times. First you are traversing the array to count how many zeros are there. Then you are traversing the array to put the zeros and then you are traversing the array to put the ones. Basically, if you see, you are traversing the array exactly 2 times. First to count zeros, then you will put those many zeros, you will traverse some part of the array and then you will traverse the remaining part of the array to put the ones. This is one disadvantage, that your array is being traversed twice. Other disadvantages which we many times forget, that these elements may not be only 0 ones, they can represent an object. For example, 0 represents here an object. Suppose this is an array where you have keys as whether a student has passed the exam or failed the exam. 0 means failed and 1 means passed. Now these keys, they represent actual student objects, and when you sort this array, and if you simply put 0 0 0, you are losing the relation with the actual objects. So we need to ensure we use an algorithm which simply does not count and put all the zeros, because these can be actual objects also. So please pause this video now and try to think of a solution that takes an array as input and then sorts the array. You can try solving this problem. We are going to discuss different solutions for this problem, and the same solutions can be used for other two problems also. Let us first talk about a naive solution to solve the problem. The idea is to create a temporary array temp of size n, initialize an index variable I as 0. What are we going to do is, we are going to traverse through our input array, and we are going to first put all the negative elements from our input array to temp array. Then we are going to traverse our input array again, and we are going to put all the positive elements after the negative elements in the temp array. That's why we are using a variable I which is being shared by both the loops. So we are first putting all the negative elements in the temp array in this loop. In this loop, we are putting all the positive elements after the negative elements, because we are using the same index variable I for temporary array, right? We have used I here, we have used I here again. So after these two loops, our temporary array has the required order of elements. All the negatives are first and then all the positives. In the third loop, we are simply copying the temporary array elements back into the original array so that our original array is modified. After the third loop, our original array becomes -12, -10, 13 and 18. Now this solution requires theta n time, requires theta n auxiliary space, and it does 3 traversals of our input array. You can see that first traversal we are doing here, second traversal we are doing here, and third traversal we are doing here to copy the elements. Now please pause this video and try to think of a solution that works in theta n time, takes theta 1 or big O of 1 auxiliary space, and does only 1 traversal of our input array. You might have guessed the efficient solution now. This problem is mainly a variation of partition function of quicksort, and the solution, the naive solution that we just discussed, it was actually naive partitioning algorithm, right? In the quicksort, we discussed 3 different partitioning algorithms, right? So if you've not seen the quicksort videos, please refer the quicksort videos first. In the naive partitioning algorithm, we were doing 3 traversals, theta and auxiliary space, the same thing we did here. So we can solve this problem efficiently by using either Hoare's partition or Lomuto partition. Both of these partition algorithms, they work in theta n time. They do 1 traversal of the array and they take theta 1 auxiliary space. So now I am going to write Hoare's partition to solve the problem. Please pause this video and try to write down either Hoare's partition or Lomuto partition yourself. Here is the implementation based on Hoare's partitioning scheme. I've done some minor changes in the actual Hoare partitioning scheme. For example, we are not returning any integer value here because we just want to rearrange the array. We don't want to return any index from this function. So most of the code is similar. We are beginning I from here and j from here, right? And when we begin from here, we consider 0 as a pivot. So we find first element which is greater than 0, right? So we stop our I at this point. And this is what this do while loop does. It first makes I equal to 0. Since it is a do while loop, it will first make I equal to 0. That's why we have initialized it with -1. And it will compare, is it smaller than 0? Yes. It will further increment it and it will stop at 18 because now it's greater than 0, right? Same thing will happen with j. It's a do while loop. It will begin from here. It will continue here because it's greater than 0. It will stop here. So they both stop at the point which the elements which should be swapped with each other, right? And since I is not greater than equal to j, they have not crossed each other. This condition is for checking whether they've crossed each other or not. The elements array I and array j are swapped. So after the first iteration, our array becomes this -12, -10. These two elements are basically swapped, right? So we get this and this. Now if you see, I has come to 1 and j has come to 2. And now we are going to begin our second iteration. So what will happen in the second iteration? I is currently here. This do while loop will run. It will make I here, right? And after I becomes here, it will stop, right? Because this condition will be checked. Array I is actually greater than 0. So it will come out of the do while loop. So I will stop here, and j, which was earlier here, right? It will enter into this do while loop, and j will stop here because this is smaller than 0, right? And now I and j have crossed each other. I has become greater than j. So we'll fall into this if condition and we'll return. And you can notice that our array has become sorted. It's simple Hoare's partition that we've earlier discussed in detail. And time complexity of Hoare's partition is theta n. This has also been discussed. Auxiliary space is clearly theta 1 and does only one traversal of the array. Let us talk about this problem. We are given an array of 3 types of elements. We need to sort this array. This problem is asked in many different ways, and here I have written 3 common ways. The first is, you are given an array of 0s, 1s and 2s. You need to sort this array, which means all the 0s should come first, then all the 1s, then all the 2s. The next form is 3-way partitioning. You are given an array. You need to partition the array around a pivot, and there can be multiple occurrences of this pivot, and all occurrences of this pivot should come together. For example, if you see this array and pivot is 2, what happens here is all occurrences of 2 come together, then all the smaller elements than 2 on the left side, all the greater elements than 2 on the right side. See, the order of these elements which are smaller can be anything, and the order of elements which are greater can be any order. But all 2's should come together, and all the smaller than 2 should come on the left side, all the greater than 2 should come on the right side. And this is the third form. Here we are given an array and we are given a range. Instead of single pivot, we are given a range. What we want is all the elements which are smaller than the smaller value of this range, smaller than 5, they should go to the left. Then all the elements which are in this range 5 to 10 should come. Then all the elements which are greater than 10 should come. So if you see this array, the elements smaller than 5, only one element 3, so first 3 comes. Then all the elements which are in range like 5, 6, 9, 10, and these elements may appear in any order, right? Order is not important here. And then all the greater elements in range 20 and 40. So these are 3 common ways this problem is asked. Now please pause this video and try to think of a solution to solve the problem. Let us first talk about a naive solution to solve the problem. The idea is to use an auxiliary array. We create a temporary array of size n. Now what we do is, we first traverse through our input array, consider all zeros and put all zeros in the temporary array at the first positions, right? So after the first loop, our temporary array is going to have 2 zeros because there are 2 zeros in the input array, and remaining elements we don't care, right? So this is what happens after the first loop, and in the first loop we are running a loop from 0 to n-1. We check if it is 0. If it is 0, we put it in the temporary array and we increment the index of temporary array. Please note that this variable I is being shared by all the loops 1, 2, 3, right? In the 4th loop, we are simply copying the temporary array back to the original array. So in the 2nd loop, we are copying all the 1's, right? If it is 1, we put it in the temporary array and we increment the index in temporary array. In the 3rd loop, we are putting 2's. So we put into the temporary array and we increment index. And at the end, our temporary array has all the required order elements, right? All the zeros first, then all 1's and then 2's. So what we do at the end is we simply copy the temporary array back to our original array. So our original array becomes 0, 0, 1, 1, 1 and 2. Now time complexity of the solution is theta n, auxiliary space is theta n, but this solution requires 4 traversals. So please pause this video now and try to think of a solution that works in theta n time, requires theta 1 auxiliary space and does only one traversal of our input array. Let us now talk about the efficient solution. The algorithm that we are going to discuss is a standard algorithm called Dutch National Flag algorithm. And this algorithm is simply a variation of Hoare's partition. See, in the normal Hoare's partition, what we were doing, we were partitioning the array around a pivot. And what we were having is all the smaller or equal to elements on the left side, all the greater equal to elements on the right side. Here what we want is, we want an extension. What we want, all the pivots should come together, right? For example, in this problem, if we want to sort this array, we can consider 1 as a pivot, right? And we want all the occurrences of 1 to come together and all the smaller elements to go on the left side. So what all smaller elements we have? We have only zeros, right? So all the zeros will go to the left side and all the greater elements to on the right side. So what greater elements we have? We have only 2's. Right, so if I modify the Hoare's partition algorithm in such a way that all the pivot elements are coming together, then I am able to sort this array of 0's, 1's and 2's. Now please pause this video, take a look at the Hoare's algorithm and try to extend the algorithm to solve this particular problem. Here is the idea of this Dutch national flag algorithm. We are going to maintain 4 sections in our array. The section from 0 to low -1 is going to contain all zeros. The section from low to mid -1 is going to contain all ones. The section from mid to high is unknown. These are the elements we are currently processing. So what are we going to run? We are going to run a loop for mid, right? And we are going to bring mid and high toward each other, right? And when they cross each other, then we say we are done. We have traversed every element, right? And high is going to be set up in such a way that elements after our high are all 2's. Right? Now, how do we initialize these variables? See, here we are guaranteeing about before low, so we will have low as 0. So there is nothing before low, so there is no guarantee required. And we are going to initialize high as n-1. So there is nothing after high, so our guarantee is still valid. And we are going to initialize mid also as 0. We are guaranteeing about elements before mid, right? So that guarantee is also valid, right? We are guaranteeing from low to mid -1, so that guarantee is also valid because mid -1 does not exist. So this is our initial setup. After we have initialized this way, we are going to run a loop for mid variable. Here is implementation of the Dutch national flag algorithm. We have a function sort that takes an array, and array should contain only 0, 1's and 2's, and n is the size of this array. We have initialized low as 0, high as n-1 and mid as 0, as we have discussed, right? Now we are running a loop while mid is smaller than or equal to high. So we are going to move mid and high. If you see these conditions, in every condition, we are either moving mid ahead or we are moving high toward left side, right? So mid and high, they are moving toward each other, and when they cross each other, we are going to come out of the loop. And we are maintaining this thing that elements from 0 to low -1 are 0, low to mid -1 are 1, and mid to high are unknown. Mid to high are the elements that we are currently traversing, and high +1 to n-1 are 2's. So what we do here is we check for array mid, right? Array mid is the element that we check all the time. If it is 0, then what we need to do is we need to increment the boundary of low, right? Low should move 1 position ahead, and this element should go there. And whatever is at low, low must be, if this range is valid, then array low must be having a 1. So we move that one here and we move the 0 there. That way our boundary shifts, slides 1 position ahead, right? That's the idea we are following. And if there is no 1, then low and mid must be pointing to the same location, right? Then the same element will be swapped with itself, the 0 will be swapped itself, and your low will move 1 position ahead. Basically, you need to ensure that if you see a 0, your low window, this window, increases in size, right? Now, if you see this example, initially our low and mid are 0. When you see a 0 here, you are going to swap array low with array mid, and the same 0 is going to be swapped here itself, and your low and mid both are going to increment and both are going to become 1 now. So now you have a valid window of zeros, right? This window has now size 1. And now what you do is you again check what is array mid. Array mid is 1 this time. Now when you see an array mid 1, you need to increment this window. And how do you increment this window? You simply need to do mid plus plus. That will increment the size of this window. So in this case, we have nothing much to do. We are simply doing mid plus plus. So our mid now comes at 2. Right, and low stays here. You can notice that elements from 0 to low -1 are zeros, and elements from low to mid -1 are ones, and mid is currently here, right? So this is unknown range. And now what we do is we check for this element. This is now 2. So in case of 2, we need to increase size of this window, right? And how do we increase the size of this window? We move high toward the left side, right? So we do high minus minus in this case, right? And and you need to ensure that whatever high currently holds, this value should be updated with 2. So what you do is you swap array high with array mid, right? And then once you swap, you do not change mid, because mid, this element is unknown where high is currently pointing to, right? And this is swapped with a 2. This window is increased. We change high, but we do not change mid. So whatever was here is now going to be processed in the next iteration. So what we do here, we see a 2 here, right? Currently mid was here, we see a 2 here. So we are going to swap these two, right? This 2 is going to come here and this 2 is going to go there. We increase the size of this window by doing high minus minus. Now high is here and mid is here. We did not change mid because we do not know what is this current element, right? See, this window from high plus 1 to n minus 1 is guaranteed, not the high itself, right? So now we have 2 here and we have this window is guaranteed now. And now what we have here is we have 2 at mid. So again we fall into the same case, right? And we swap mid and high, right? So 1 comes here, 2 goes there. We do high minus minus. So high now comes here. Now mid is here. We check what is the current value of mid. Mid is 1. So we are going to increment it here. Now mid and high, they both are at this 1. Now we again check what is mid. Mid is 1. So we again increment mid and mid now becomes 4. And now mid becomes 4, so mid and high, they cross each other. So we come out of the loop and our algorithm terminates. Let's now talk about time complexity and auxiliary space for this algorithm. See, auxiliary space is clearly theta 1 because we are not using an auxiliary array or list. Talking about the time complexity is theta n, and this algorithm requires only one traversal. See, in every iteration of this loop, you either increment mid or you decrement high, and you stop when they cross each other. So you are going to traverse through array exactly once, right? That's why the time complexity is clearly theta n, but theta n was earlier solution also. The great thing here is it's only one traversal.
In this video, we are going to talk about this problem, merge overlapping intervals. So we are given a set of intervals. An interval mean we have start time and end time. So one interval is 1 to 3, starting at 1 and ending at 3. Other interval is 2 to 4, 5 to 7, 6 to 8. If you take a look at these intervals, you can notice that this interval and this interval, they have something in common. This is from 1 to 3. So if you draw the line 1, 2, 3, 4. This interval is from 1 to 3. First interval. Second interval is from 2 to 4. Right. So second interval is from 2 to 4. So there is an overlapping part between them. When there is an overlapping part, we need to merge these two intervals. And how do we merge? We take the minimum of start times and maximum of end times. So mainly this interval becomes one interval. So it becomes 1 to 4. Right. So we have printed 1 to 4 in the output. If this can be merged with any other interval also, we will merge it with any other interval also. Let's see this interval. Can we merge 5, 7 with 1 to 4? So 1 to 4 is now a one interval. It has been merged. And 5, 7 begins from 5. So it's from 5 to 6 to 7. So there is nothing common in these two intervals. So we do not merge them. We keep 5, 7 separate. Now 6 to 8. 6 to 8 is interval which begins from 6 and goes till 8. So this is a different interval 6 to 8 that has something common with 5 to 7. So we need to merge these two intervals. And what will be the minimum value of merged interval? Smallest of the two. This is 6 and this is 5. Smallest of the two is 5. What will be the maximum value? Greatest of the two. 7 and 8. Greatest is 8. So these two intervals are merged as 5 and 8. Let's take a look at the next example. Here we again have more intervals. And we can notice that the interval from 1 to 3 and 2 to 4 can be merged. they can become 1 to 4, and this can also be merged. You know, there is an interval from 1 to 4, and there is another interval from 4 to 5. So we consider them also as overlapping because they have this point common. So we need to merge these two also. So all of these three are merged in one interval 1 to 5. 6 to 10 and 7 to 9. You can notice that they also have something in common. 7 to 9 is completely inside this interval, right? This contains 7 to 9. So they have overlapping portion and they are merged as 6 to 10. Please pause this video now and try to write a program that takes an array of intervals as an argument and produces non-overlapping intervals. This is an output, right? So you will be given an array of intervals. You can make an array of pairs, right? This is how you can make an array of pairs to store the intervals of given size. Or you can create a structure or class. If you're in Java, then you can probably create a class also. You can call it interval. Java also has pairs. You can use pairs, but you can use class also. So you will have int start and int end. Then you will make an array of these intervals, right? So you'll make an array of these intervals. And so in Java, probably you will make this way. So please try to write down a program that reads intervals in arrays, something like this in C++, probably something like this in Java, and then produces this as an output. You need to print non-overlapping intervals after merging them. Please pause this video and try to implement it yourself. You may consider input as array of a structure or class where your interval is represented as a structure. If you talk about C++, if you talk about Java, then it is considered, you can consider it as a class, and it has start and end. Start time and end time, and you have an array of intervals. So you can consider this simple implementation. This is your input and you need to print this as an output. You may also consider an array of pairs. You know, instead of creating structure, you can also use array of pairs. Instead of creating a class in Java, pair is also there in Java, pair is also there in integer. So you can use pairs also to represent an interval. Let us first talk about this problem. We are given two intervals. We need to check whether these two intervals overlap or not. Please pause this video and try to write down a solution, a code that takes two intervals as arguments and returns true if these two intervals overlap, otherwise returns false. So there are two ways to do it. One is you find the larger of the start values. You have two intervals. The larger of the start values is 5. This is one start value, this is one start value. In this example, larger of the start values is 10. Now you look at, now you take this larger value and you see, does it lie in the second interval? If it lies in the second interval, then you say there is an overlap. So take the larger of the start values of the two intervals and then check if this large value lies between start and end of the other interval. What is the larger value here? 10. Does it lie between these two? Yes. So they overlap. Now if I take an example where two intervals do not overlap, what is the larger value of two start values? 100. Does this 100 lie between 10 and 20? No. So they do not overlap. Other way of finding whether two intervals overlap or not. Take the smaller value of end values of intervals. So what is the smaller values of ends? 7. Now check if it lies between the range of other interval. So 7 lies between 5 and 10. So they are overlapping. What is the smaller of these two? 15. Does it lie between the 10 and 20? Yes. So they overlap. What is the smaller value of these two? 20. Does it lie between 100 and 200? No. Do not overlap. Let us first talk about a naive solution to solve this problem. What do? We traverse through all the intervals one by one. So I begin with this interval 5, 10. I check this interval with every other interval. So I'll be running two loops. For int I equal to 0, I is smaller than size of the array, and then j equal to 0, j is smaller than size of the array. To check with every other interval. I will check if it overlaps with any of the other intervals. If it overlaps with any of the other intervals, I will merge these two intervals and will delete the other interval, right? So if I begin with 5, 10, I'll go through the whole list and I'll compare it with every other interval. And now we know how do we check if two intervals overlap or not. We just need to find the larger of two start values and then check if it lies between start and end of the other interval, or the other way around, finding the smaller of two end values and checking whether it lies between start and end of the other interval. So let's begin with this approach. 5, 10 we take, we search it everywhere, we compare it with 2, 3. It does not overlap with 2, 3. Does it overlap with 6, 8? Yes, it does. So we remove 6, 8 from the list. We keep 5, 10, we keep 2, 3. We remove 6, 8 from the list. And when we remove 6, 8 from the list, we merge these two intervals. What do we do in the merging two intervals? We take the start of new interval. Say I have two intervals I1 and I2. And what will be my new start? It will be min of I1 dot start and I2 dot start. What will be new end? It will be maximum of I1 dot end and I2 dot end. Let me see. Let me just demonstrate what I just said. So I have say two intervals 5, 10 and other interval is say 2, 7. I want to merge these two. I know they overlap. I know a way to find out whether they overlap or not. What will be the new start? It will be minimum of 5 and 2. What will be the new end? Maximum of 10 and 7. So merged interval will be 2 to 10. So 5 and 10 and 6 and 8, when they are merged, we get the merged interval as 5 and 10 only, and then 6 and 8 is removed from the list. We remove it from the list because it overlaps with this. Now we go to the next interval, 1, 7, and 1, 7 also overlaps. So what do? We update this interval. We take the minimum of 5 and 1, we make it 1, and maximum of 10 and 7, we take it 10. So this becomes merged interval, and we remove this also from the set. Right, so this is our new interval. Now we take 2, 3 and we traverse through all the remaining intervals. So there is one interval 1, 10. Now they overlap. 1, 10 and 2, 3 they overlap. So we'll merge these two also and we'll remove this from the list. So we'll have only one interval in our resultant list, which will be 1 to 10. You take the minimum of these two values, 1, maximum of these two values. So you need n square time to traverse every other interval for an interval, and then you need to delete the other interval. Deleting other interval from a list is again big O of n time. So that is why it's big O of n cube solution. Please pause this video and try to think of a solution that is big O of n log n. Let us now talk about an efficient solution. The idea of the efficient solution is to sort the intervals. We can either sort them in increasing order of start time, or we can sort them in decreasing order of end time. I am going to consider this approach where we are going to sort them in increasing order of start time. right? And we'll discuss solution according to this approach, and then you will get an idea how you can solve it by sorting in decreasing order of n time. So what we do is we sort all the intervals in increasing order of start time. We traverse all the intervals from left to right and we keep merging overlapping intervals. When you are at ith interval, these intervals must have been merged into some intervals m1, m2, mj minus 1 and mj. So these are also intervals, these are also intervals. And these many intervals say got merged into these many intervals. And these must be non-overlapping intervals because we have merged overlapping intervals so far, right? And this input is now sorted in increasing order of start time. So this is sorted in increasing order of start time, right? These intervals, and these intervals are merged, right? Merged from x1 to xi minus 1. So you've sorted the intervals. Now you are sorted the intervals according to start time. Now you process, say, these many intervals and you merge them into m1 to mj. Now when you are at ith interval, when you are at xi, the claim is this interval will only merge with mj. You do not have to go beyond the last interval. You only need, if it has to be merged with any of the previous intervals, then it will merge only with the last interval. That's what the idea of this algorithm is. So if you have sorted the intervals, then for every interval, you just need to check previous merged interval. That's the idea. That's the idea of this n log n solution. Let's see how does this work. So I've taken some example here. I've taken this example 510, which is say last to last merged interval. And then this is last merged interval. So we had some intervals, say 1 to xi minus 1. We merged them into these two intervals, right? Now we are processing this interval. This is our xith interval. What we'll do, we'll compare it with the mjth interval only. We never have to compare it with mj minus 1. That's what we are saying. And why are we saying this? We are saying this because this will be overlapping with this interval only if its start time is greater than equal to start time of this and smaller than equal to end time of this. Then only it will merge. That's the idea we discussed in the checking of whether two intervals overlap or not. We take the greater start time. Here xi has come later, so its start time has to be greater. And if it has to be merged, then its start time has to be greater than equal to start time of this, smaller than equal to start time of this. So this is how we decide whether it can be merged with this or not. Now how can we ensure that this will never merge with any of the previous intervals? Please pause this video and try to think of it. We can ensure this because if this interval could be merged with any of these previous intervals, then its start time must have been between previous intervals, and that merging must have been done by now, right? So all the mergings are done, and these mj minus 1 and mj are non-overlapping intervals, which means its start time is definitely greater than the end time of mj minus 1 because they are non-overlapping. Since its start time is greater than its end time, its start time has to be definitely greater than end time of this, right? Because this is greater than the start time of this start time. So what I'm saying here is xi dot start is greater than mj dot start greater than equal to, that is because we have sorted them in increasing order of start time. We know this for sure, and we also know mj minus 1 end time is smaller than mj dot start. Because if this was not the case, then these two would have been merged. Mj minus 1 and mj would have been merged for sure, right? So this has to be there because they are non-overlapping. So from these two, I can conclude that xi.start is greater than mj minus 1.end, which means xi cannot merge with mj minus 1 because its start is greater than end of mj minus 1. So it cannot merge with any of the previous intervals. So if you have sorted all the intervals in increasing order of start time, after sorting you just have to do a linear traversal, right? You keep merging the intervals, and for every interval just check with the previous merged interval. That's all you need to do. If it overlaps with the previous merged interval, then merge it with it and go ahead, right? In this case, it overlaps with the previous merged interval. So what we'll do, we'll change mj. We'll change mj from 1120 to merge of these two, which means 1130. And we'll go to the next of it, right? So that's the idea. After sorting, you can just traverse the intervals in one go, in one linear traversal, and you can merge them in linear time. So that's the advantage of sorting we get here. After sorting the intervals, we can merge them in linear time. Let us now talk about big O of n log n implementation. In this implementation, I am going to consider intervals as this structure in C++. If you are talking about Java, then this will just be a class, right? So this is the structure we are assuming. We also assume that we have a comparator function, myComp, that allows us to sort the intervals in increasing order of start time. So you need to write your comparator function, whether you are programming in C++ or you are programming in Java. We have talked about how to write a comparator function in these sort examples. So what are we doing here? We sort all the intervals according to their start time in this step. So if I take this array example, after this step, I will modify the array to following. I'll first have the smallest start value interval 27, then 315, then 510, then 1830. So these are the sorted intervals after the sorted step. They are sorted according to start time, right? After sorting, we start merging them. And the idea is this: we are going to use the same array. Instead of creating an auxiliary array to store the non-overlapping intervals, we are going to put them in the same array, modify the same array. So what do? We maintain a result index. So when I say result index, elements from 0 to result are the elements which have been merged, which are non-overlapping and merged intervals. So right now I assume that my first interval is part of the output and it has been merged. So this is finalized. And we begin from the second interval. So this is our xi, the interval that we are doing, array I. And this is mj that we discussed in the previous example. Previous interval of the merged intervals. So I begin from the second interval, and what I do is I compare it with the last interval of the non-overlapping interval. So this is my first non-overlapping interval, and this is the interval that I am currently processing because I begin from I equal to 1. Now what I do is I check whether they overlap or not. For this, I simply check if array I of start is smaller than last non-overlapping intervals end, right? Then only they will merge, right? If that is the case, then we will merge them and we change the interval at result index, and you know what do we do in merging? We change the end as max of 2 end values and min as minimum of 2 end values. That's what I've written here. So here I am merging array result and array I into array result. That's what we are doing in this step, right? So these two overlap. We change our array to, we merge this into this. So we have now 215, right? And our this element is going to be 315 or 315 only, and this is 5, 10, and this is 18, 30. And our result index is still pointing to 0. We have only one interval so far in the result, right? So it's pointing to 0. We now move to the next index. I becomes 2, so we come here. So this is where I is right now. Now we check if this I is overlapping with the last non-overlapping interval. So in non-overlapping, we have one interval so far. So they are overlapping. So we'll merge this also with this. So let me modify the array at same place. So what will I have now? I'll merge this with this, and this interval will be remaining same because this is 5, 10, and if I take the minimum of these two, I'll get 2, maximum of these two, I'll get 15. So there is no change in the array. Your result is 0, they are merged, but this is merged into it. It did not make any change into this interval because the max of end is this, min of start is this. Now we change I, we come here and we compare it with the last non-overlapping interval that we have found. So they are not overlapping. We will not go inside this if condition, right? Because they are not overlapping. And how do we check? We check the start of this. Is it lying between end of this? Between the start and end of this? It's not lying. So we'll move the result ahead, right? And what we'll do, we'll change our array. We'll write this interval at this index. So our new array is going to be 215, 18, 30. We override this interval because this is of no use, right? This has been processed. We'll have 5, 10, and we'll have 18, 30 here again. And our result is now here. Result is now here at this index. Right? This is where result is. This is our result index. So we have two intervals in result. Right? The intervals, number of intervals in the result are from 0 to result index. So we print these two intervals at the end. We print 215, then we print 18, 13. So that's how we merged all the overlapping intervals in big O of n log n time. Big O of n log n time to sort the array, and then we can process it in linear time. That's the advantage of sorting here. We could sort the intervals in n log n time, and then we could process them in n log n time. We could sort the intervals in n log n time, and then we could process them in linear time. This is where we sort, this is where we process and get the non-overlapping, and this is where we print the non-overlapping.
Let us talk about this problem. Consider a situation where you have a full day party. Party starts at 00 and goes till 23:59. You are also invited in the party, and there are many other guests invited. You have list of all guests, and you also know when are they going to come to the party and when are they going to leave from the party. For example, here there are two guests apart from you. The first guest is going to come at 9 o'clock and leave at 10 o'clock. The second guest is going to come at 9:40 and leave at 10:30. Please note that I have not used colon in the time to keep the question implementation simple so that we can use integers. Ideally, it should have been 10 colon 30, right? 10 colon 30, but I have written only integer values. So 1030 means 1030 means 1030 time. So you have list of guests apart from you who are going to come to the party, and their arrival and departure times are going to be from 0 to 23:59, right? Because party goes from morning 00 to night 23:59. Your target is to meet the maximum guests. You want to go to the party so that you can meet the maximum guests. And your target is to find out how many maximum guests you can meet. Let's understand with this example. Here we have two guests apart from you coming. One guest comes at 9 o'clock and leaves at 10 o'clock. The other guest comes at 9:40 and leaves at 10:30. So if you go at the time from 9:40 to 10 o'clock, you will be able to meet both of them, right? From 9:40 to 10 o'clock. Let's now see this question, this example. Here you have four guests coming from you, coming in the party, and these are their arrival and departure time. Guest 1 comes at 8 o'clock, leaves at 8:40, 7 o'clock, leaves at 8:20, comes 6 o'clock, leaves at 8:30, comes at 5 o'clock and leaves at 5:30. In this party, you can meet maximum 3 people. And what time you will go to the party so that you can meet 3 people? You will be going from 8 to 820, right? If you go from 8 to 820, the first 3 people will be there. This guy is there from 8 to 840, he's there from 7 to 820, and he's there from 6 to 830. So if you go from 8 to 820, you will be able to meet 3 people. And in this question, if you go from 940 to 10 o'clock, you will be able to meet both the people. In this question, you get the answer 3. Can you guess the time frame around which you should go to the party? You should go to the party from 11 to 11:20. If you go from 11 to 11:20, you will be able to meet this guy. He's there from 11 to 11:30. You will be able to meet this guy, and you will be able to meet this guy. You will be able to meet 3 people if you go from 11 to 11:20. So you have 2 integer arrays given to you, and you need to write a function that returns an integer value, and this integer value tells you how many guests you can meet at most. Now please pause this video and try to write down a function that takes 2 integer arrays and returns an integer value. Let us now talk about an efficient solution. We are going to use sorting here. Let's see how sorting can be useful to solve this problem in big O of n log n time. The basic idea behind the solution is we consider all the timelines starting from the first arrival to last departure, and at every time we see how many guests are there, right? And whatever is the maximum is our result, right? We'll go at that time and meet the maximum guests. Now if you see this example, there are 3 guests. One arrives at 6 o'clock, leaves at 8 o'clock. The second guest arrives 7 o'clock, leaves at 7:30, and the third guest arrives at 9 o'clock and leaves at 10 o'clock. So if I draw a timeline of all these guests, I'll get this timeline. At 6 o'clock, first guest arrives. We have count of guests as 1. 7 o'clock, second guest arrives. We have count of guests as 2. At 7:30, one guest leaves. So we have count of guests as 1. At 8 o'clock, one more guest leaves. So we have count of guests as 0. So A means arrival, D means departure here. 9 o'clock, one more guest arrives. So we have count of guests as 1. So between 8 and 9, there was no guest. At 10 o'clock, one guest leaves. So we have count as 0. Now if I go through all this timeline, I can notice that I have maximum guests here, right? So this is my maximum. So this is the basic idea to solve the problem, and we are going to use sorting to implement this idea. You would love to pause this video now and implement this idea yourself. Let us now take a look at the implementation of the approach. So we have a function max guest count that takes arrival, departure, and size of the arrays as arguments. What this function does, it first sorts both arrival and departure arrays. If you are programming in Java, then you will use arrays.sort to sort the arrays. This is the syntax in C++. So we first sort both the arrays in increasing order. See, the point is we want all these events according to the timeline. Now we have 2 different events in 2 separate arrays. So we first sort both the arrays individually. So we get all the arrival events according to the timeline. We have all the arrival events and all the departure events according to the timeline. Now our task is to merge both the events and then keep on counting the guests at the current moment. Now this problem becomes very similar to the merge function of the merge sort. And if you take a look at this code, this is close to the merge function of the merge sort. This is what we do in the merge function. We compare array I with array 1i with the array 2j, and we do I++, otherwise we do j++. Something similar we are doing here. So what are we doing here? We have considered the first arrival here. We know that array 0 is ARR 0 is going to be smaller than departure 0 for sure, right? So we have considered beginning I from 1. We are going to begin from the second arrival. We have initialized j as 0, first departure. And since we have already gone to this event, right, we have already considered one arrival and our count of guests is 1. Our current guest is 1. Our result is also initialized as 1. It's going to be at least 1. So we have already considered the timeline when one guest has arrived. Now we are going to consider all the remaining events by merging both the arrays. So what we do, we say if current arrival is smaller than current departure, then this arrival event, the current arrival event is first. So take this event, increment the count of current guess because arrival has come before next departure, and do I plus plus, go to the next arrival in the arrival array. And if current departure is smaller than current arrival, if the next event is a departure, then decrement the count, current count, and go to the next event in the departure. And whatever you do out of these two, you compare the current with the result. If result is less than the current, then you update the result. You basically are checking when you get the maximum result. So at this moment, you will have the maximum result as 2, right? And result will be updated here. It won't be updated after this. Let's now do a run of this code with this example. We have 3, 900, 600, 700, 1000, 800, and 730. We'll sort both the arrays. 6 o'clock, 7 o'clock, 9 o'clock, 7:30, 8 and 10. After sorting, we'll initialize these values and now we'll run this loop. Now we'll compare, our I is currently here, right? And J is here. We have initialized I as 1 and J as 0. Now I'll compare these two. 7 is smaller, so array I is smaller. We have now 2 guesses. At this point, we have 2 guesses. And we update the result also as 2. And we increment the I because array I is smaller than departure J, so our I must have been incremented. So I becomes 2 now. Now we do the next iteration of the loop and we compare array I with array I, which is 2 now, with departure J, which is this now. So this time our array I is greater, right? So we fall into this if condition. So we do not change I, we change J. J moves to this point, right? J comes here. And we decrement the current count and we do not update the result because current is less than result. So our J has come to 1 and our I is here. Now we are going to compare these two, right? 800 and 900. 800 is again smaller. So we are going to make the count of guests as 0 and result is going to same as 2, right? We have current as 0, right? Less than result. Now we are going to go to the next iteration. In the next iteration, our array I is smaller than departure J. So we are going to increment the current, but current is not more than result, so we are not going to update the result. So you can notice that we have actually considered all the events in sorted order because we are doing something like merge of merge sort, and at every moment we have just counted the current guess and we have compared it with the maximum guess so far and we have updated the maximum. Let us now talk about time complexity of the solution. Time complexity of the solution is clearly n log n because we have 2 arrays of sort of sizes n, and what we are going to do, we are going to sort the first array which takes n log n time, then we are going to sort the second array which also takes n log n time. And this loop is clearly big O of n plus n, right? That's similar to merge function, and merge function takes m plus n time if you merge 2 arrays of size m and n. So it's big O of n plus n, which is big O of n. So overall time complexity is big O of n log n plus big O of n log n plus big O of n, which is big O of n log n.
In this video, we are going to talk about cycle sort. Cycle sort is a big O of n square worst case algorithm, or you can say theta n square time it requires in the worst case. The specialty of this algorithm is it does minimum memory writes. There is no other sorting algorithm which can sort an array by doing number of writes less than cycle sort, right? Cycle sort is optimal in terms of memory writes. So if you have memory like EEPROM where write is costly, doing more writes reduces the age of this memory, right? In those cases, you can use cycle sort. Wherever your write is costly, right, you can use cycle sort. It's in place, does not require extra space, and not stable, right? It's not a stable algorithm. I mean, if there are 2 equal elements, then they may be changed in their position by this algorithm. The last point is the reason we are discussing this here. This is asked in many places in this form. You are given an unsorted array, how many minimum swaps you will need to sort this array. So questions like this and other variations of this are interview questions or problems based on cycle sort. So in this algorithm, we need to sort an array. Say we are given this array, we want to sort it to 10, 20, 30, 40, 50, right? That's what we want to do. And the main purpose of this algorithm is to minimize the memory writes. Considering this main purpose, we count how many elements are smaller than the current element for every element. So we begin our traversal from here and we count how many elements are smaller than this. We know one element is smaller. So we know for sure that this element will go at second position or index 1. So we minimize the memory writes. We find the exact position where this element has to go. If you see other sorting algorithms, they do multiple swaps to fix the position of an element. Here in one memory write, we are fixing this element. How? By counting the smaller elements. So we count how many elements are smaller than 20. We got the count 1 and we know that 20 has to come to this position, right? We know that 20 has to come to this position. So this 40 becomes our new item now because 20 is going to replace 40. Now we count for 40. How many elements are smaller than 40? 1, 2, 3. There are 3 elements smaller than 40. So we know that 40 has to go to the position 4th or index 3. So we know 40 has to come here. Now 40 is going to replace 10. So 10 becomes our new item. So our item is 10 now. Now we again count how many elements are smaller than 10. There are 0 elements smaller than 10. And we know 40 has to go to index 0 or position 1. So our item becomes 10 again or 20 again. Now this item has repeated, right? This item is some item that we have already seen. So now we know 10 has to come here, 20 has to come here, 40 has to come here. So we sort these 3 elements first, right? We put 10 here, 20 here, 50, 40 and 30. That's what we do in the cycle sort. So these 3 elements are at their correct positions now. Now we traverse again to the next element and we see it's already there at its original position because there is only one element smaller than this and it's already been placed by this first iteration. Now we come to the next element 50 and 50 is not at its correct position because the number of smaller elements than 50 are 4. So our new item becomes 50. And we know where 50 should go. 50 should go at 5th position. How do we know? By counting smaller elements, right? There are 4 smaller elements, so it should go at position number 5 or index 4. Now our item becomes 30. We count how many elements are smaller than 30. We have 2 elements smaller than 30. So we know 30 has to go here at this index. And this is our starting item again. Item is again 40, 50. So we finalize these 2, right? We fix these 2 at their locations and we get 10, 20, 30, 40, 50. So our whole array is sorted by the cycle sort. The task that we just did, the example that we just did, it was fixing elements in the form of cycles. That is why it is called cycle sort. And I've drawn the cycles here. See, I counted how many elements are smaller than 20. I got the count as 1. I got this position, right? So there is an arrow from here to here because 20 has to go at this position in the sorted array. Then I come to 40 and I counted how many elements are smaller than 40. I got 3 and I got to know that 40 has to go to this position by counting the smaller elements, right? Then I came to 10 and I counted how many elements are smaller. I got the value 0. So I got to know that 10 has to come here, right? So these arrows indicate that this element should go there, this element should go there, this element should go there. And there's a cycle here between these 3 elements. So you fix these 3 elements first at their original positions and then there is another cycle between these 2 elements. So you fix these 2 elements by fixing the cycle, right? That's all we do in cycle sort. We process the elements in the form of cycles. Let us take a look at another example to better understand cycle sort. I have written an example here with values 40, 30, 20, 10. We want to sort it this array as 10, 20, 30, 40. So what do we do in cycle sort? We take a look at first item, we count how many elements are smaller than this. We got to know that there are 3 elements, so we know the position that this element has to go to 10, right? So we have to move it to this position. Now our new item becomes 10 and we count how many elements are smaller than this. There are 0 elements smaller than this. So this element has to come here. So we fix these 2 elements first, right? There's a cycle between these 2, right? Now we come to the next element and we find how many elements are smaller than this. We found that there are 2 elements which are smaller than this. So we know its position is going to be 3. So this has to go there. Now we come to this element. We find how many elements are smaller than this. We get the count as 1. So this has to go to the position number 2. So there is another cycle, right? So we fix these 2 elements by interchanging them. Suppose they were 20, 30, then there will be cycles of length 1, right? 20 has to go its original position, 30 has to go its original position. There will be cycles of length 1. Any sorted array, if you have a completely sorted array already, there will be cycles of length 1. 10 has to go here, 20 has to go here, 30 has to go there, 40 has to go here, right? So that's the idea of cycle sort algorithm. Here is an implementation of cycle sort. In this implementation, I have assumed that there are no duplicates in our input array. The purpose of writing this restricted implementation is to first explain the algorithm with simple restricted input. Once you understand the algorithm, you can yourself extend it for duplicates, right? So this code that I've written here, it's different from the article on Geeks4Geeks. It's only for distinct elements. I have mentioned the function name also as cycle sort distinct. In this whole code, we are using our main variable, which is CS. CS stands for cycle start. So in theory part, we saw that we process elements in the form of cycles. We consider all the elements as cycle starting point, starting from the index 0 to second last element. So once you consider an element as a cycle starting point, you find the whole cycle, you fix all the elements in this cycle at their correct positions. So one thing is ensured that elements before CS, say CS is right now 5, then element from 0 to 4, they are sorted, right? And since you are processing them in cycle, it would happen that many of the elements which are after the index 5 are also at their correct positions. But one thing is ensured that element from 0 to CS minus 1 are already sorted. And elements from CS to n minus 1 may be sorted, may not be sorted, depending upon the cycle lengths and how these cycles are processed. Let's see this algorithm step by step for this input array. Our item is initially array CS and CS is initially 0, so our item is 20, right? So we have item equal to 20. And our position right now is 0. So position tells us how many elements are smaller. You begin with array 0, you count how many elements are smaller, and there is only one element smaller than 20, so your position becomes 1. And what do you do after it? You swap item with array position. So what is the item at position 1? 40. So your item becomes 40. And you update array position also to item, right? You swap these two things. So this position 1 now has 20, 50, 10 and 30. Right? So these two things are swapped. And you got this, right? Now 20 is at 2 place, but no problem because you have 40 in item now, right? So 20 is fixed at its correct position. Now you need to fix the next element of the cycle beginning with 20, and next element is 40. Your item is currently 40. And after 40 is fixed, you need to fix the element where 40 goes, the element which is replaced by 40, right? So you run a loop to fix all the elements of this cycle. So you fixed the first element of this cycle separately. Now you are fixing remaining elements of this cycle, right? To fix 40, what do? You count how many elements are smaller than 40 in this subarray, right? From here, CS plus 1 to end. How many elements are smaller than 40? 1, 2, 3. So our position becomes 3. Please note that we begin position from CS, right? So position is again initialized to 0 to count the remaining elements, and then we count how many elements are smaller and shift the position by those many times. So position is now 3 after you counted the smaller elements. After finding the position as 3, you know that element at position is 10, you again do the swapping. You swap item with array position. So your modified array becomes 40 comes here in place of this position and items become 20. So we have swapped item and position again. So our new item is 10. Now what do? We initialize the position as 0, which is cycle starting point, and we count how many elements on the right of this cycle starting point are smaller than our current item. And we find no element. So position remains 0, right? Because nothing is smaller than 10. And what do you do now? You do swap of item with array position. So what is your modified array? It's now 10, 20, 50, 40 and 30. And what is your new item? Your new item now is 20, right? You get the value of this item as 20. And now your position is 0, right? After doing this iteration, when you go back again, you see that position is equal to the starting point, cycle starting point. So you are done with the cycle. You have finished the cycle. You have sorted all the elements at their correct positions. 10 has come to its original position, 20 has come to its original position, 40 has come to its original position. So all the elements of this cycle are fixed. So our one iteration of this outer loop is over. We have fixed one cycle, right? 10, 40 and 20, they are fixed at their correct positions. Let's see how does this code work. How does this code treat the fixed elements and other elements? So what this code is going to do now, it's going to make CS equal to 1, right? Your 0th item is sorted and its correct position. Now CS is 1, right? So when CS is 1, it's going to take the position also as 1, and it's going to assign item equal to array position, which is 20, right? And you can see that 20 as its correct place, right? 20 is at its correct place. So this particular loop is not going to run, right? This is not going to run. Basically, it's going to swap 20 with itself and then it's going to stop at this loop, right? So it's going to consider this as a cycle of length 1, right? So this whole loop gets over by just doing the swapping, because you find the position as 1 only and you just do the swapping, and after swapping you see that position is equal to cycle start, so you stop. Now your cycle start becomes 2. You begin a new iteration of this outer loop and your new element is 50. Your position is also initially cycle start, right? And your item is 50. Now you count how many elements are smaller than 50 on right of it, right? Because the elements on left of it are already sorted. So you have 2 elements. So your position increments from 2 to 4. Your new position becomes 4. Now you know that this has to go at position 4. So what do? You swap item with array position. So you put 50 here and now your item becomes 30, right? Now you count how many elements are smaller than 30 in this subarray, right? And what do you get? You get nothing, right? So your position remains 2, right? Equal to CS. You initialize the position equal to CS, so it remains 2. So what happens now? You swap array position with item, which means your item now becomes 50 and array position now becomes 30. Your item is now 50, right? After the swapping, right? Your item is now 50 after you swap. Once you have done that, you will see that position and CS, they are same, right? So you will come out of this loop, and you fix this cycle, right? Now you begin with the next cycle. In the next cycle, you see the next item as 40, right? And 40 is at correct position. So you will simply do the swapping and then you will come out. So your CS will become now 4. And once your CS becomes 4, it crosses the limit of n minus 1, right? So you stop. Why do we have the limit till n minus 1, right? I mean, the last index till which we traverse is n minus 2, right? Because CS should be smaller than n minus 1. So why are we not traversing the last element? The reason is simple. Once you have fixed all the cycles, your last element must be fixed at its correct position. If it is part of a cycle, then it must have been fixed by that cycle. If it is not part of cycle, then it's a greatest element and it's already a single element with cycle to itself and it must have been fixed.
Let us talk about heap sort. The basic idea of heap sort is based on selection sort algorithm. In selection sort algorithm, we find out the maximum element and we swap it with the last element. In selection sort, we do linear search to find out the maximum element, and that's how the selection sort time complexity becomes big O of n square. Heap sort does an optimization over selection sort, uses the same idea, but for finding the maximum element, instead of doing linear search, heap sort uses max heap data structure. So what we do in heap sort is, we are given an array, we restructure the array or rearrange the elements of this array so that they form a max heap. And building a max heap or min heap from a random array is big O of n time. So we get our max heap as a first step. After building the max heap, we swap the last element with the root of the max heap. So your maximum element goes to the end like you do in selection sort. And after that, you simply do heapify. Because heapify is an operation that works well when the subtrees are heapified, only root is disturbed. So we fix the root using heapify operation and we keep on repeating this process. So let's consider this example. We have an unsorted array and we want to sort it, right? We want to get this array as an output. So every array can be seen as a complete binary tree. This array can be seen as this complete binary tree, right? And the first step of heap sort is convert this complete binary tree into a max heap. See, if we want to sort an array in increasing order, we use a max heap. And if we want to sort an array in decreasing order, we use a min heap. Let us now talk about first step of heap sort algorithm, which is building a max heap. So we are given an array. So this is our given array. And we can see this array as this complete binary tree. Our target is to convert this complete binary tree into a max heap. To convert it into a max heap, we call a process called build heap. And this is our build heap process. And what this build heap process does, it begins from the last internal node, goes till root of the tree, which is 0 index, and keeps calling heapify for every node it visits. So what is our last internal node? This is our last internal node. So we call heapify for this node, and this time we are calling max heapify because it's a max heap. So when you call max heapify, how does max heapify function work? It finds the largest of three things, node and its two children, and swaps the largest with the node if one of the children is largest. So we swap 20 and 15, right? So 20 becomes the root of this subtree, and after swapping these two, we recursively call max heapify for the node with which we have swapped. So we have swapped with this node, so we recursively call max heapify for this node. That's how this max heapify function works. The first three lines in this code are mainly to find largest of three things, node and its children. So we have the index of node as largest initially, then we find the left child, right child. We compare the largest with the left child, and if left child is greater, we update the largest. If right child is greater than largest, then we update the largest again. And before going to the left and right child, we make sure that we are not going out of bound indexes. Once we find out largest of three things, node and its two children, we check if node itself was already largest. If it was already largest, then there is no point recursively calling the heapify, because heapify assumes that left and right are already heap, and if the node itself is also a heap, we don't need to make any change in the heap. And if node itself is not a heap, then we swap it with a particular child which has the largest value, right? We swap it with the child which is the largest value and recursively call max heapify for the child. So we swapped these two and we recursively called max heapify for this particular node. Now when you call max heapify for this node, your left and right, these two conditions will become false and your largest will remain I, because this left of this is going to be 4 into 2 plus 1 are 9 and right is going to be 4 into 2 plus 2, 10. And 9 and 10 are beyond n. What is your n? N is your 5, right? There are 5 elements in the array. So we are not going to fall into these if conditions. We are going to have the largest as itself, and the recursive call of this node 15 is not going to do anything in this subtree, right? So after we have called max heapify for this, we get this subtree. Now we are going to call max heapify for the next internal node. So we called for 1, now we are going to call for 0. So we call max heapify for our root. When you call max heapify for the root, it's again going to follow this process. It's going to find out the maximum of 3 values, 10, 20 and 50. Maximum of 3 values is 50. It's going to swap itself with this node 50, right? So 50 is going to become the root, and then 10 is going to come here, and then it's going to recursively call max heapify for 10. When it calls recursively max heapify for 10, 10 is a leaf node. So again, these two conditions will not be true. So we are going to come out of the loop. So this is how our given array, which is pictorially this complete binary, becomes a max heap. Now we have already talked about how did we get this index. This is parent of the last node. So last node index is n minus 1, and parent of this is going to be, so parent of I is I minus 1 by 2, right? Parent of I. If we apply this formula for this index, we are going to get the parent of last node as n minus 1, 1 by 2. So we have n minus 2 by 2. That's how we find out the last index. For example, if we apply this formula here, we have n equal to 5 and 5 minus 3 by 2. We get 2 by 2, which is 1. That's why we started from this node, right? We started from this particular node, and then we decrease the value of I. So we call max heapify for this node, then we call max heapify for this node, right? That's how this build heap function works. And we have already discussed build heap in detail. We have talked about time complexity of it. Time complexity of build heap is big O of n. We have talked about step 1, and step 1, we build a max heap. This was the max heap we got after step 1, and this actually is an array. This is just a pictorial representation, and we have this array. Now we want to sort this array. Now we are going to follow the process like selection sort. We are going to swap the maximum element with the last element, then second maximum element with the second last element, and so on. Now the good thing is, since it is a max heap, we have the maximum element at index 0 itself, right? So we swap array 0 with array 4. So these two elements are swapped. And after you swap these two elements, 50 goes to its final position, because 50 was the maximum element and it has gone to the last index. So we remove 50 from our max heap. Now our max heap has 4 elements. And this is not a max heap now because we have done some swapping and 15 has gone on the top and 15 is not the maximum element, right? So what we need to do now is we need to fix this max heap. To fix this max heap, we use our standard process which is called heapify. Heapify can always be used when your subtrees are heaps, only the root is disturbed. And here we actually disturbed the root, right? We swapped these two. So they were heaps. We just disturbed the root and now we want to fix it. So we call heapify. So to call heapify, we compare this with its two children and we take the maximum of these three. Maximum of these three is 20. So we swap these two. Now we have 20 at the root and 15 comes here. Now we recursively call max heapify for this. And this is already a max heap. So max heapify would not do any change. So this is what we have as our heap after first iteration of this loop. We swapped array 0 with array 4 and then we called heapify for 0, right? So this is what we get after first iteration of the loop. And please note that we are passing I as a size to the heapify. So it means we are reducing the size of heap in every iteration. So after this, we again do an iteration of this loop, and in the next iteration, we again swap first element, which is root of the max heap, and which is the second maximum element, because it's a binary heap of remaining n-1 elements. So your second maximum element will be at the top. You swap it with the second last element in your array or last element in your binary heap. So basically you swap 20 and 4, and after that you get this array. Right, so your now 20 is fixed at its final position. Right, your two elements are fixed at their sorted positions, and your heap size reduces by 1. Now your heap has 3 elements. So what you do now again is you fix this heap. You want to keep it as a max heap, so you need to heapify the 4. After heapify 4, you get this heap. You get 15, 4, and 10. 4 and 15 are swapped, and recursively call for this. Recursive call for this would not do anything because it's a leaf node. So we get this heap as final. Now we again do the next iteration of this loop, and in this iteration we swap array 0 and array 2, 15 and 10. And this is what we get as our final modified heap. And now these 3 elements are fixed at their sorted positions. We do not want to touch them now. So our heap has only these 2 elements. Now we heapify the root, and it's already heapified. So heapify would not make any change. And here comes the final iteration of this loop. In this iteration, we swap array 0 and array 1. Once you swap these two, your array becomes this. And now your heap size reduces by 1, so your heap has 1 element. And now if you call heapify for one sized heap, you are not going to make any change into the array. So your 4 remains as it is. And after this iteration, we stop because now I becomes 0 and we come out of the loop, and our array has become sorted. Heap sort can be mainly seen as an improvement of selection sort. It uses heap data structure and the concept of selection sort. Selection sort worst case time complexity is big O of n square, but heap sort's time complexity is big O of n log n, which is the best possible time we can get in any comparison based sorting algorithm. There are other sorting algorithms like merge sort and quick sort, which also take big O of n log n time. Merge sort takes big O of n log n time in worst case. Quick sort takes big O of n log n time on average case. Heap sort takes big O of n log n time in all cases. When we compare heap sort with merge sort and quick sort, the constants hidden in heap sort algorithm are higher than merge sort and quick sort. In practice, merge sort and quick sort takes less time compared to heap sort. And that is why merge sort and quick sort are used more in practice. However, there are hybrid algorithms like intro sort, which are based on quick sort. This intro sort algorithm uses heap sort. What happens in quick sort is it may go beyond n log n in certain cases. Its recursion depth can become big O of log n. And this intro sort algorithm switches to heap sort when the recursion depth goes beyond log n. And this intro sort algorithm is a standard algorithm used in C++ standard library. So heap sort is not used as a standalone sorting algorithm or main sorting algorithm in libraries, but it is used as a helper sorting algorithm in hybrid algorithms. Let us talk about counting sort algorithm. Counting sort is a linear time algorithm for the cases when our input elements are in a small range. For example, if we have n elements and elements are in range from 0 to k minus 1, then counting sort is going to take big O of n plus k time. It is not a comparison based algorithm. It never compares items with each other. Rather, it counts their occurrences. Counting sort is useful only when k is linear in terms of n. K is n, n by 2, or 2n or 3n. When k becomes n log n or quadratic, it is of no use because we have algorithms, comparison based algorithms that work for any range and take big O of n log n time. Let us understand counting sort with this example. We have an array ARR with the range of elements from 0 to 4. So we have k equal to 5 and we want to sort this array. So our output array is going to be sorted. Now this example, k is 10, so elements are in range from 0 to 9 and we want to sort this array. So we want this as output. Now please pause this video and try to write down a program that takes an array as an argument, takes k as an argument and sorts the array in big O of n plus k time. Let us first talk about a naive implementation to solve this problem. The first thing that we do in this naive implementation is we create a count array of size k. We know that array elements are in range from 0 to k minus 1. So we can have an array of size k to count occurrences of all array elements. We initialize this count array as 0. Now we traverse through the input array and increment the count of every element that we see. So we are using array elements as indexes in this count array and incrementing their counts. So after this first phase of this algorithm, our count array will look like this. 1 appears 3 times, so you have 3 at index 1 in this count array. 0 appears 1 times, so you have 1 at index 0. 2 and 3 are not there in our input array, so we have 0, 0 as the counts of 2 and 3. And 4 appears 2 times, so we have 2 as index 4. Size of this count array is 5 because k is 5, so we have the size of count array is 5. Size of our input array is n, which is 6 here, right? So we create a count array of size 5 and simply increment count of every element that we traverse in the input array. Now once we have built the count array, how do we use this count array to sort the input array? In this simple implementation, we are using this simple idea. We know that 0 appears 1 times, so we run a loop for count 0, how many times 0 appears, and put 0 those many times. Since it appears 1 times, we are going to put it only once. Now we go to the next element and we get count of it. 1 appears 3 times, so we run a loop 3 times and put 1 3 times in our original array, right? So we have 1 3 times. We do not care what elements are there, right? We actually have the same elements at this position, but we are going to override the whole array by considering the count array. Now we go to 2. For I equal to 2, our count is 0, so we do not do anything. For I equal to 3, our count is again 0, we do not do anything. But when we come to I equal to 4, our count is 2. So what we do is, we put 4 at the last 2 positions, and that's what we have implemented here. We are running a loop that traverses through every element of count array. This loop runs from 0 to k minus 1. And what it does, so this loop is basically going to run through this count array, right, that we have built. And what it does inside the loop, it runs another loop that runs count I time for an index I in the count array. And that tells you how many times this I appears your input array, right? That's what count array meaning is. So what we are going to do, we are going to put I those many times at the next index in our original array. So our next index is another variable that we have initialized as 0. So first element, the 0 count, if 0 is there, it's going to be put at index 0. Then 1s are going to be put and then 2s are going to put, right? So for I equal to 0, we have 0 count as 1. So in inner loop is going to run once and it's going to put a 0 here, right? And then this inner loop will stop because count 0 is 1. Then outer loop will run for 1. And for 1 at this loop is going to run 3 times, right? And when it runs 3 times, it's going to put 1 3 times in your array at the next index and it's going to increment the index. So that's how this logic works. Now what is the time complexity of this solution? The first part of this loop, if you see, it runs theta k times. This runs theta n times. Let's now analyze this loop. This loop runs count I times for every I varying from 0 to k minus 1. And what is the sum of all the counts? It's actually n. So the innermost statements are going to run theta n times. But we have an outer loop also. If k is high compared to n, then also this outer loop is going to run theta k times at least. So we can say the overall time complexity of this part is theta n plus k. So overall time complexity of this algorithm is theta k plus theta n plus k, which is theta of n plus k. So that's the overall time complexity of this algorithm. The naive implementation that we have written here, it works in theta n plus k time. It's fast, but it cannot be used as a general purpose sorting algorithm. It can only be used when you have an integer array or an array of items which are integral, like short integer or characters. It cannot be used for sorting objects. For example, sorting an array of students by their marks. Because what happens in this solution is, you are going to use array I as an index. So say you use marks as an index. You have an array of students and you do array I dot marks as an index, right? And you do plus plus. You know that marks are going to be from 0 to 100. You create an array of size 101 and you do array I marks plus plus. Now once you've done this step is going to fail, because what are we going to do in this step? We are going to assign indexes in the array of objects. And we cannot do that, right? It's a student object which we are sorting, right? Array of student objects. And what are we putting here? We are putting index. So we cannot assign simply marks to the student objects. So we need to come up with an approach that can work for general purpose objects, the objects which have multiple fields. Here is a general purpose counting sort implementation. It works really well when you have objects to be sorted also. And these objects are to be sorted according to a certain key. This implementation works for integers as well. For simplicity of implementation, we are showing this implementation only for integers. So the first step of this algorithm is same as the naive implementation. We have a count array. We initialize this count array as 0 and then we increment count of every array element one by one. So after this step, for this input array, our count array is going to be 1, 3, 0, 0, 2. Count of 0 is 1 in our input array. Count of 1 is 3 in our input array. 1 appears 3 times. And 2 and 3 do not appear, so their counts are 0. 4 appears 2 times, so count of 4 is 2 here, right? So this step is same as the naive implementation. After this step, we modify our count array such that count I stores how many elements in our input array are smaller than or equal to I. And this is what we do in this loop here. We run this loop from second element, starting from index 1. So count 0 is going to be remaining as it is because there is nothing before 0, and number of elements which are smaller than or equal to 0 are going to be the same. When we are at index 1, right, we begin this loop on index 1. What are we going to do? We are going to add count 0 with count 1. So count 0 with count 1. 1 and 3, 4. So we get the value 4. And now when we go to the next index, index 1, what are we going to do? We are going to add count 1 and count 2, which is 4. Now when we are at this index, we are going to add count 2 and count 3. So we are going to get 0 plus 4, 4. Now when we are at this index, we are going to add count 4 with count 3. So we are going to get 4 and 2. So we get 6. So these are the values we get count. And now if you take a look at this count array, count I indicates how many elements in our input array are smaller than I or equal to I. For example, count of 3 indicates 3 is 4. How many elements in our input array are smaller than or equal to 3? There are 4 elements, 3 ones and 1 0. Count 1 also is 4. So how many elements in our input array are smaller than or equal to 1? We have 4 elements, 1 0 and 3 ones. Count of 4 means 6. So how many elements we have smaller than or equal to 4? We have all 6 elements. That's why we have the value 6. Now how do we use this count array to get our sorted array in another array output? So we are going to use this ARR and count to build this output array, and this output array is going to contain all the elements in sorted form. And once we have built this output array, at the end, we are simply going to copy this output array back to our original array. Now, the most critical part of this algorithm is building this output array. I have cleaned up the board now. Let us now build the output array step by step. So we are traversing this input array from n minus 1 and we are going till 0 in this loop, right? Please note that we could build the output array by traversing from 0 to n minus 1 also. The reason we are doing from n minus 1 to 0 reverse way is to make sure that our output is stable. This sorting is stable. Stable means if there are two elements with same value, they should appear in the same order in the output as they appear in our input array. So if this last one appears last in your input array, then it should appear last in the output array as well. That's why we are traversing from the right. Let's see how does this work. So we begin from the last index or last element in our input array. We use this value as an index in our count array and we get the count as 4. So we know that there are 4 elements smaller than or equal to 1 in our input array, which means this 1 should go at the 4th position in your output array. And 4th position means index 3. That is why we have subtracted 1 here. So we put this 1 at index 3. After putting 1 at index 3, we reduce its count also. We make it 3. So that when you see next time 1, you do not put at 4th position, you put it at 3rd position. Now we go to the next element 0 and 0's value is 1. It means there is only one element which is smaller than or equal to 0. So we use this 1, subtract 1 from it and we put 0 here. Basically this 1 tells you the position of 0 is first position in your input array. And we reduce this count to 0. Now we go to the next element and we notice that this is 1. We use it as an index. We get the count as 3 now. Which means there are 3 elements smaller than or equal to 1. So we need to put it at 3rd position. And when we are putting it at 3rd position, we need to put it at index 2. So we put this 1 at index 2 and we reduce its count further to 2. Now we go to the next element 4 and we use this 4 as an index and we get the count value as 6. That means there are 6 elements smaller than or equal to this 4, which means we need to put it at the 6th position, which means at index 5. So we put 4 here and we reduce its count to 5. Now we go to the next one. This one is 4. We use this 4 again as an index in this array and we get the count as 5, which means this should go at the 5th position, which means index 4. So we put 4 here and reduce its count to 4. Now we go to the next element, which is 1. We use 1 as an index and we get the count as 2, which means it should go to the 2nd position and we reduce its value to 1 and put it at 2nd position, index 1. And that's how we get our output sorted array. After we have got our output sorted array, we are simply copying this array back to our original array. So our original array becomes 0, 1, 1, 1, 4, 4. And we have got the sorted array. It's a stable sorting algorithm because we are traversing from the right side and it takes care of objects when you want to sort them according to a particular key, because we are never putting indexes as values in our output array. We are putting actual objects in our output array and then copying these actual objects back to our input array. Right? We are not putting indexes that we did in the naive solution. Let's now see one more example to get a better idea of this algorithm. Let's see, we have our input array of size 4 with elements as 5, 6, 5, 2 and our range is 0 to 6. So we make a count array of size 7. We put counts of individual elements. So count of 2 is 1. Count of 0 and 1s are 0, 0. Count of 5 is 2. 5 appears 2 times. And count of 6 is 1. After building this count array, we build a cumulative count array where we have count I means number of elements which are smaller than or equal to I. So we simply do a cumulative sum. So this element we get 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 2 is 3, 3 plus 1 is 4, right? And after this step, we are going to build the output array. Let us see now how do we build the output array for this example. We have an output array of same size as our input array. Now we are going to traverse our input array from last index. We have the element 2. We use this element as an index in our cumulative count array. We get the value 1. It means this 2 is going to be there at first position in our output array. So we put it at first position and we decrement the count of this 2 in our count array from 1 to 0. Now we traverse through the next element and we use it as an index in our count array 5. We get the count as 3. It means this next element 5 should go at the third position. So we put it at the third position and decrement its count from 3 to 2. Right? Now we go to the next element 6. We use it as an index in the count array. We get the value 4. It means the 6 should go at the fourth position. So we put it at the fourth position in our output array and we decrement its count to 3. Now we go to the next element in our input array 5 and we use it as an index in our count array. We get the value 2. It means this 5 should go at the second position. So we put it at the second position and decrement its count to 1. And that's how we get our sorted array. Let us now see some important points about counting sort. The first thing is, it's not a comparison based sorting algorithm. If you take a look at this implementation, we never compare array items like we do in comparison based sorting algorithm. The next thing is, it takes theta n plus k time. The first part takes theta k time, then theta n time, then theta k, then theta n, and then again theta n. So overall, it's theta n plus k algorithm. The third is, it takes theta n plus k extra space. We need theta k space for count array and we need theta n space for the output array. So it's going to take theta n plus k extra space. It's a stable algorithm because we were traversing our input array. We are traversing our input array from right side to left side. So we always put right elements first at their last positions, right? That's how it's a stable algorithm. It is used as a subroutine in Radix Sort. Please note that counting sort is useful only when k is really small. If k is linearly proportional to n, like it's n by 2 or n or 2n, but if k is large, like n square or n cube, then counting sort becomes n square algorithm or n cube algorithm. And that's where Radix Sort is a better algorithm. It works in linear time even if your input range is from 0 to n square or 0 to n cube. We'll talk about Radix Sort in a separate video. Counting sort is used as a subroutine in the Radix Sort. Here is an exercise for you. In this implementation, we have considered elements in range from 0 to k minus 1. Now please extend this implementation so that you can handle the elements from a min value to max value, and we know that total items in this from this min value to max value are only k, and this min value can be negative also. Let us talk about Radix Sort algorithm. Radix Sort algorithm, like counting sort, is also a linear time algorithm if your data is within a limited range. Now we already have counting sort. Why do we need another sorting algorithm? The reason is counting sort will take time big O of n plus k, where k is the range of elements. And if k is n square, then counting sort will take n square, which is worse than standard comparison based algorithms like merge sort and heap sort. Radix Sort is a sorting algorithm that supports linear time even for a larger range. It works in linear time even if your data is in range from 0 to n square or 0 to n cube. It uses counting sort as a subroutine to sort the elements. And like counting sort, it's not a comparison based algorithm, because if you have a normal comparison based algorithm, then you cannot sort the elements in time complexity less than n log n. And this is an algorithm that sorts the elements in linear time if they are in small range. Let's now see the working of Radix Sort algorithm. Let's say we have these elements, we want to sort them in increasing order. So first thing is, we'll make sure that all the numbers have same number of digits. And how many digits every number should have? It should be equal to the number of digits in the largest number. So the largest number is 319 and it has 3 digits. Now, how do you find out largest number in an array? You can simply traverse through the array and find the maximum element in linear time. And how do you find out number of digits in the largest number? You can use logarithmic, right? You can take the log in base 10. So you figure out there are 3 digits in the largest number. So what you do is, you consider that even the single digit and double digit numbers have a 0 appended to them at the beginning, right? For understanding of the algorithm. So I've rewritten the array with zeros appended at the beginning or pre-appended at the beginning, right? After we attach zeros, we have now all the numbers with same number of digits. What we are going to do now is, since every number is a 3-digit number, we are going to do 3 passes. In the first pass, we are going to sort all the numbers. We are going to use a stable sort. Basically, we are going to use counting sort to sort all the numbers according to the last digit. Then we are going to sort all the numbers according to the middle digit. Then we are going to sort all the numbers according to the first digit. Suppose we had 4-digit numbers. In that case, we would require 4 passes. So let's see what happens when you run the first pass. What are the last digits? 0, 0, 8, 6, 2, 9. And we want to sort them in a stable way, right? So which number will come first? 100, because it has the smallest digit value and it appears with this number before this number, right? It also has the smallest value, but this appears first. So we write 100 first, then we write 050, and after that 212, then 006, then 008, then 319. You can notice that we have all the numbers now sorted according to the last digit. This has the smallest last digit, then this also has the smallest last digit, then 2, then 6, then 8, then 9. Now we sort these numbers according to middle digit, and again we do a stable sort. So which numbers have the smallest middle digit? These 3 numbers, right? These 3 numbers have the smallest middle digit. So we'll put these 3 numbers in the same order as they appear in the input, because we are doing a stable sort. 100 appears first, then 006, then 008. Now we put 212 because 1 is greater than 0, right? Now we put 319 because this one is also greater than 0. So these 2 numbers have the same middle digit, but 212 appeared first, so we are putting 212 first. Now we put 050 at the end. This has the highest middle digit. And after sorting according to middle digit, we sort according to the most significant digit or first digit. And after you sort, stable sort according to the first digit, you get these numbers. And you can notice that your input is sorted. We got the sorted array. Now please pause this video and try to write down an implementation of this approach. Please note that we are going to use counting sort as a subroutine to sort numbers according to individual digits, and we are simply going to call counting sort for all the digits. Let us see the implementation of Radix Sort. This Radix Sort function can be divided into 2 sections. The first section finds out the maximum element in the array. It's a very simple logic where we initialize maximum as array 0. We compare it with all the other elements, and if an element is greater, we update the maximum. The second section of this Radix Sort function calls counting sort for every digit in the maximum number. So we have a variable called exp. This exp represents a power of 10. We initialize it as 10 raised to the power 0. Then we go to 10 raised to the power 1, 10 raised to the power 2, 10 raised to the power 3, and so on. We keep incrementing the power while mx divided by exp is greater than 0. So if your maximum number mx is 319, then how many times this loop will run? This loop will run for exp equal to 1. This will run for exp equal to 10. Then it will run for exp equal to 100. It will not run for exp equal to 1000, because when exp becomes 1000, 319 divided by 1000 will be 0. So that's the logic we have implemented here. We have an exp variable which is a power of 10, and we run this loop only equal to the number of digits in your maximum number. So if we consider this example, our mx is going to be 319. Then we are going to run a loop, and inside this loop, we are going to call counting sort first with exp equal to 1, then exp equal to 10, and then exp equal to 100. So this is all we do in the Radix sort. Now comes the counting sort part. The counting sort code that we have written here, it is similar to the counting sort implementation that we discussed in the counting sort video. The only difference we have in this implementation is, instead of using array I directly as an index, we use array I divided by exp modulo 10 as an index. Now, if you do some mathematics using pen and paper, you can notice that if exp is 1, then this expression will give you the last digit of array I. If exp is 10, then this expression will give you the second last digit of array I. And if exp is 100, then third last digit of array I. Let's see how. Say exp is 1, then what you will do? You will divide array I by 1, which means array I only, and array I modulo 10 gives you the last digit. Now say exp is 10, then you will divide array I by exp, which means your last digit will go off, right? For example, if array I is 319, if you divide by 10, what you will get? You will get 31. And if you do 31 modulo 10, you will get 1, which is your second last digit. So these expressions here give you the digit according to value of exp. When exp is 1, it gives you the last digit. When exp is 10, it gives you the second last digit. When exp is 100, it gives you the third last digit. And the rest of the logic is exactly same as counting sort. We are making a count array, then we are making an output array, and we are filling this output array using the expressions here. Let's now see the step-by-step working for this particular example. So this is our example. Our first step is to find the maximum element mx, which is 319. Now we are going to run a loop, and inside this loop we are going to call counting sort 3 times with arr. Size of array is 6. So this 6 value is actually n is 6, and exp is 1 in this call. In this call, n is again 6 and exp is 10. Here n is 6 and exp is 100. Right? So these 3 calls we make inside this loop for exp equal to 1, exp equal to 10, and exp equal to 100. Now for this call, what we do is we sort the numbers according to the last digit because exp is 10. And this is same counting sort logic. It is strongly recommended that you see the counting sort video first. And if you've not seen now, then you can refer this counting sort video now and you will get the idea how does this code work. So first thing that we do in this counting sort algorithm is we make a count array, right? And we initialize this array as 0. Now what we do, we traverse through our input array and we fill the counts of individual elements according to the current digit. So current digit is 1 that we are considering because exp is 1 at this moment. So how many numbers we have as last digit as 0? So we have 2 numbers, 150. That's why we have count of 0 as 2. Then we have no number with last digit as 1. Then we have 1 number with last digit as 2. So the count is 1. Now we do not have any numbers whose last digits are 3, 4, 5. Then we have a number where last digit is 6 and the number is this 6. Then we have one more number with last digit as 8, this number. Then we have one number with last digit as 9, which is 319. So we built our count array. Now we do a cumulative sum in this count array in this particular step, right? And this is all part of counting sort. And cumulative sum we do to get the last position where this particular element should be put, right? So if you see this count array, you can notice that the element with last digit at 9 should be put at position 6. The element with last digit as 8 should be put at position 5. And the element with last digit as 6 should be put at position 4. And the elements, there are multiple elements with last digit as 0. The last occurrence of such an element should be put at position 2. Position 2 means index 1, right? So we build this count array, and using this count array, we fill our output array, right? We find out the positions of every element using this count array. We subtract 1 from this position to find out the index, and we put those elements at those indexes. And then we increment the count so that if there are multiple occurrences of a digit, for next occurrence, we get the correct position. So this is what is done in this part, and we have the correct output array. Then we copy this output array to original array. So our original array becomes this. And then when we call counting sort 610, our original array changes to this. Now this array is sorted according to second digit. First time we sort according to first digit or last digit, then we sort according to the second last digit, then we sort according to the third last digit or the most significant digit, and we finally get our sorted output. Let us now talk about time complexity of Radix sort. So first step of this algorithm takes theta n time because we are simply finding the maximum in an array of size n. Now the second step, it runs for every digit in the maximum number. Let's say there are d digits in your maximum number. Then inside this loop, we call counting sort, right? How much time counting sort takes? If you have n numbers and these numbers are in range from 0 to k minus 1, then counting sort takes theta of n plus k time. Now here we have n numbers and range of these numbers is greater. It's not actually from 0 to a small number k minus 1. Here we have a larger range, but what we are going to do, we are going to sort these numbers according to a particular digit. And these digits are in range from 0 to 9. So we have actually k as 10 in this counting sort. In general, if the numbers are in base b, then we can say it's going to take theta n plus b time. And in this particular implementation, b is actually 10. So this step takes theta n plus b, and here in this example, our b is 10, base is 10. So this is the overall time complexity of Radix sort. It's theta n. So we can ignore theta n because this part is anyways n multiplied by something. So we can say that overall time complexity of this Radix sort implementation is this much, which is this part. Here is an interesting fact about Radix sort. If you increase the value of base b, for example, if you increase from 10 to 20, then this loop will run less number of times. Then your d will decrease, right? Because you will have less number of digits in a bigger base. Now what will change? Your extra space required by the counting sort will increase. Here we need extra space of size 10, but if you are using a bigger base, then that size will increase. So this is an interesting trade-off between space and time in the implementation of Radix sort. If we want to reduce the time, we can increase the base, right? And then this d value will decrease because it's in multiplication, but your extra space required will increase. Let us now see extra space required by Radix sort. So it requires this much time and it requires theta of n plus b extra space. This much extra space is required by the counting sort implementation, and it is using counting sort, so it's going to need this much extra space. So this much extra space and this much time required by counting sort, Radix sort algorithm here that we discussed. So Radix sort is an algorithm that works better than counting sort if your range is bigger than linear. It uses counting sort as a routine, and it's a stable algorithm because counting sort stable is used, and if you have two numbers, say 100 and 100, then they'll be remained in their original order, right? The first 100 will remain at the first position because for every digit we are using a stable count sort. Let's talk about bucket sort. Let's understand these two problems to get an idea of bucket sort. In the first situation, we have numbers in range from 1 to 10 raised to the power 8, and these numbers are uniformly distributed in this range. In the second situation, we have floating point numbers, and these numbers are again uniformly distributed in range from 0.0 to 1.0. So 0.0 is included and 1.0 is excluded. So all the numbers are greater than or equal to 0.0 and smaller than 1.0. Now let us clarify what do we mean by uniform distribution. If you have 100 numbers, for example, then these 100 numbers will be like this. Around 10 numbers will be in range from 0.0 to 0.1, 0.1 being excluded. Around 10 numbers will be in the next slot from 0.1 to 0.2, 0.2 being excluded. So if you have 10 slots, then around 10 numbers will be there in every slot. And if you have 5 slots, if you have distributed a whole range in the 5 slots, then around 20 numbers will be there in every slot. To give you more idea, for example, if you have 1000 numbers to be sorted and you have this range, and if the numbers are uniformly distributed, and if you have divided this range into 10 equal sized parts, then every range is going to have 100 elements around. And if you have divided the range into 5 equal parts, then every range is going to have around 200 elements. So this is what uniform distribution is. A simple solution to sort these numbers is to use any n log n comparison based sorting algorithm like merge sort, heap sort. And with these sorting algorithms, we can get the time complexity as n log n. But we are not using the fact that numbers are uniformly distributed in a given range. We could think of counting sort. We could try applying the counting sort, but counting sort would not work in this example particularly because we can't use elements as indexes because elements are floating point numbers. In this situation also, if you try using counting sort, then you would need a lot of extra space. Suppose you have only 100 numbers to be sorted, then you would need extra space for a range of 10 raised to the power 8, so which is too much. So counting sort would also not be a good fit. Bucket sort is a sorting algorithm that works in linear time when your data is uniformly distributed across a range. Now please pause this video and think of a sorting algorithm that will use the uniform distribution fact and will sort the data in linear time. In case you are aware of hashing with chaining, this is going to be similar to that. If you are not aware, no problem. We are going to talk about detailed algorithm now. Let us now get an idea of bucket sort. With this example, we have these 9 elements which are uniformly distributed across the range from 0 to 99. So in bucket sort, we first divide the range into multiple buckets. So we have a range of 100 elements from 0 to 99. Here in this example, I have created 5 buckets. Now, why are we creating 5 buckets? Why not 10 buckets? Why not less buckets? We'll talk about that. It's actually all about time versus space trade-off. So I've just taken a number 5 and divided this range into 5 ranges. First range contains the elements from 0 to 19. The second range contains the elements from 20 to 39. The third range from 40 to 59. Fourth range 60 to 79. And fifth range 80 to 99. Once we have created these buckets, what we do is we traverse through the input elements, and for every element we decide in which bucket this element should be going, and we put that element in that particular bucket. So 20 went into this bucket because this is 20 to 39. 88 went into this bucket. 70 went into this bucket. 85 here, 75 here, 95 here, and 18 into this bucket, and so on. So once we have moved all the elements into appropriate buckets, the next step that we do is we sort individual buckets. So this bucket has only one element, no change here, no change here. This is empty bucket, so no change here. This bucket has 3 elements and this was the original order. We sorted them and got this. Now this bucket has 4 elements. We sorted this bucket and got this, right? Once we have sorted individual buckets, our last step is to join these buckets. So we first put elements of the first bucket, which is 18, then second bucket 20, third bucket is empty, fourth bucket has elements 60, 70, 75. We put these 3 elements. Now last bucket has 4 elements, so we put the last bucket elements. And you can notice that all the elements of array are sorted now. Now the question arises, how do we sort individual buckets? We can use any standard sorting algorithm to sort the individual buckets. If we are sure that individual buckets are going to have less number of elements, then we can use insertion sort. Insertion sort is the best suitable algorithm for small amount of data. Let us now analyze bucket sort in more detail. The question arises, how many elements are going to be there in individual buckets? See, if we have total n elements in our input array, and if we have k buckets, And if we are assuming that our data is uniformly distributed, then how many elements we will have in individual buckets? We will have n by k elements on average, if the data is uniformly distributed. If every element is equally likely to go in any of the buckets. So if we have k close to n, for example, if k is equal to n, then we will have approximately one element in every bucket, which means we are going to take constant number of time to sort the individual buckets. Even if k is half of the n or 1/3 of the n, in those cases, you are going to have 2 elements on average in individual buckets or 3 elements in individual buckets, which are again constants. And even if you have slight variation from uniform distribution, say you have 5 elements or 6 elements in individual buckets, even then you are going to take the constant time to sort the individual buckets. And the final step is to simply join these individual buckets. So joining is going to take linear time. So we took linear time to distribute these elements into individual buckets. Then we took linear time to sort all the buckets, assuming that sorting individual buckets take constant amount of time because we have uniform distribution and we have number of buckets proportional to input number of elements. So overall, we are going to take the linear time to sort the individual buckets under these assumptions, uniform distribution and number of buckets are almost equivalent to n or half of the n or 1/3 of the n. And once you have sorted, joining them will again take linear amount of time. So we are taking total linear time to sort the elements if we have n of buckets and we have the data uniformly distributed. Please note that this algorithm might work really bad if your data is not uniformly distributed. For example, if all the elements, they go into the same bucket, what will happen? If you are using insertion sort to sort the individual buckets, assuming that you are going to have uniform distribution and less number of elements in every bucket. But if this does not happen, then you are going to take big O of n square time to sort one bucket, and which is a worst case situation for the bucket sort. Let us now talk about implementation details of bucket sort. What we actually need to implement as a bucket sort program. So for simplification, we are assuming that we are given number of buckets as input, so that we don't need to decide how many buckets to use in this program. So we are given an array and we are given number of buckets. In this example, number of buckets is 5 and number of elements of the array are these. Now, how do we find the range of the elements? We can find the maximum element in this array, that is going to be the upper limit, and lower limit we can assume as 0. So in this example, our maximum value is 99 and minimum value we are assuming as 0. So we have total range from 0 to 99 and we need to divide this range into 5 buckets. So we'll divide this way. All the elements that are from 0 to 19, they will go into the first bucket, 20 to 39 second bucket, and so on. And that is how we'll put these elements into the individual buckets. Let us now see this example. Here we need to divide the range into 4 buckets and our range is from 0 to 80. So this range has 81 elements in total, and this becomes slightly challenging program to implement yourself, so that you divide these 81 elements into 4 buckets. So one of your buckets is going to have an extra element in the range. And once you have decided the ranges for the 4 buckets, then you need to put these elements into individual buckets. So this is all you need to implement. You need to decide the ranges for individual buckets. Then you need to put these elements into individual buckets. Then you need to sort the individual buckets and then you need to concatenate them. Now please pause this video and write a function that takes an array as an argument, number of buckets as another argument, and then sorts the array using bucket sort. Let us now see the implementation. This side we have Java implementation and here we have C++ implementation. So in these implementations, we take an array as an argument. We also take number of buckets as another argument. And inside these implementations, we are first finding the maximum value in the array. Once we find the maximum value, we are creating k buckets. In C++ implementation, we are using an array of vectors, right? The size of this array is k and we call this array as bkt. In Java implementation, we are using an array list of array list. And once we have created k buckets, we traverse through every input array element. For every element, we decide in which bucket this element should go, and we put this element into that particular bucket. We'll discuss this process in detail. This has been demonstrated here step by step. We'll talk about these steps. Once we have added elements to individual buckets, we sort the individual buckets. So this is where we sort in C++ code, and this is where we sort in Java code. After sorting individual buckets, we concatenate all the buckets. And concatenation or joining of all the buckets is really simple. We simply traverse through all the buckets, and if a bucket has elements, we traverse through all the sorted elements one by one and put these sorted elements at the next index. So we have used an index variable, we initialize it as 0, traverse through all the buckets, traverse through all the elements of the current bucket and put the elements at the next index. That's the simple concatenation task. Let us now see how do we decide bucket index for every element. Let us see this example array. In this array, our maximum element is 80, but we initialize the max value as 81. I'll shortly discuss what is the reason for incrementing it by 1. After we have initialized our max value as 80 plus 1, we traverse through all the elements, and for every element we use this formula to decide the bucket index. So when I is 0, we are going to get the bucket index as 4 into element at 0 index 30 divided by max value. So we are going to get 4 into 30 divided by 81, which is 120 divided by 81, and we are going to get the index as 1. So we put 30 at index 1. Now we come to the next element 40, and we get the index again as 4 into 40 divided by 81, 1. Then we go to the next element, we get the index as 0. Then we go to the next element, which is our maximum element, and we get the index as 3. And suppose we did not do max value plus plus, what would have happened in that case? We would have got 4 into 81 divided by 81. We would have got the index as 4. And we have valid indexes from 0 to 3. That's the reason we increment max value by 1, because there exist max values in the array, and for these max values, we are going to get a new slot. So if your range of elements is from 0 to x, then we divide by x plus 1. We choose the maximum value as x plus 1 to get the appropriate indexes. In this particular example, if we apply this formula for any element in range from 0 to 80, this is how these elements are going to be divided. For elements from 0 to 20, we are going to get the index 0. For elements from 21 to 40, we are going to get the index as 1. For these elements, we are going to get the index as 2. For these elements, we are going to get the index as 3. So every element goes into one of these 4 indexes. And why is this happening? Because we have taken this as 81. If we do not increment it by 1, then for 80, we are going to get the index as 4, which is out of bound. After we have put all the elements into individual buckets, we sort these individual buckets, right? We are going to sort these individual buckets using sort function in C++ and collections.sort in Java. So after sorting individual buckets, you will get the first bucket as 5, 10, 12, second bucket as it is 30, 40, and third bucket after sorting will become 70, 80. And once we have sorted individual buckets, we are going to concatenate them, right? So we begin with index equal to 0, and we traverse through all the buckets. Then we traverse through all the elements of current bucket. So we put 5 at index 0, and then we increment the index. Then we put 10 at the next index, and we put 12 at the next index. Then we traverse through this bucket and put elements of it. Then we see next bucket is empty. So we traverse through the final bucket and put elements of this bucket into the array. So this is how our array becomes sorted using bucket sort. Let us now talk about time complexity of the bucket sort. In this time complexity analysis, I am assuming that number of buckets are approximately equal to number of items in the input array. In the best case, we'll have perfectly uniformly distributed data. And when you have perfectly uniformly distributed data, and if you have n buckets, then every item is going to be in a different bucket. So sorting individual buckets is going to be big O of 1 time or constant time, because there are 1 elements in individual buckets. Even if there are slight variations, that's constant. And then we are concatenating all the buckets, which is big O of n operation again. So our overall time complexity is going to be big O of n. Even if you use insertion sort to sort the individual buckets. Why do we use insertion sort? Because insertion sort is the best algorithm when you have small number of elements to be sorted. Now in the worst case, what will happen is your data is not uniformly distributed and everything goes into a single bucket. And if you use insertion sort here as well, then you are going to have big O of n square time in the worst case. But if you use an n log n algorithm to sort the individual buckets, then your worst case can also become big O of n log n. But please note that if you're using n log n algorithm to sort the buckets, then it won't be a good idea if your data is uniformly distributed. So bucket sort is the best suitable algorithm when your data is uniformly distributed across the range.